1.5 lakhs for 35,000 EV up to price of 15 lakhs. Then hybrid four-wheeler e-buses, etc. Various incentives were there under FAME 2 and 2,700 charging stations in metropolitan cities and on highways as well. Then this is then after FAME 2, because of election in 2024, for a short period, this electric mobility promotion scheme was undertaken. Naturally, time was short and capital outlay was very small. And target was for two-wheeler and three-wheelers. And not all the vehicles fitted with advanced battery, I mean lithium ion, they will only get the incentives. Then at present, this scheme is under operation. PM e-drive, electric drive, Pradhan Mantri electric drive. So total outlay 10,900 crore, incentives for 2, 3-wheelers, trucks, e-ambulances, buses, and charging infrastructure. And there are various kind of financial support for different types of electric vehicles, two-wheeler, three-wheeler, etc., etc. There are other programs under Mission Life. They are also promoting electric vehicles to reduce air pollution. Now, there are various other initiatives. You see, sometime back, the Ola and Uber, they have the target to convert 40% of their fleet. I don't know whether by April they can make it or not, but there is a target and they are gradually adding more and more electric cars. Now, initially this was the target, all new commercial cars and motorcycles to be EV, but now, as of now, the situation is it will be delayed. And all cars sold are EVs by 2030. Now, under e-mobility program, 30% of vehicles on road would be electric by 2030. Provide impetus to the entire e-mobility ecosystem. Then Ministry of Housing and Urban something more, I just forgot. Then so they have a guideline that 20% parking space will be for EV in large residential or commercial buildings. There is a guideline. So then ESL, Energy Efficiency Services Limited. So it is undertaking by the government of India. Then they are promoting energy efficiency. Initially, they have many schemes like CFL, then later on LED distribution, and various other, promoting municipal DSM, then DSM for distribution companies, then DSM for large industries, etc., etc. So they have a program to procure 20,000 electric vehicles, etc. That will save so much of oil and reduction. It will help reduction of so much of CO2, etc. Then Niti Aayog, so they have a national mission for transformative mobility and battery storage. So there are various schemes by various departments from various angles to promote electric mobility. That is regarding schemes and promotion of electric vehicles. Now, coming to the point on developing the charging infrastructure. See, Ministry of Power has published a guideline and standards for, so there are some amendments. So initially it was, I think, 21 or 2. Then there are various amendments and made by the Ministry of Power that regarding guidelines and standards for charging infrastructure. There is a question, you see, selling electricity requires license. Nobody is permitted to sell electricity without license. So distribution companies, they have the license to sell electricity. If somebody wants to sell electricity, he is required to get license from the Regulatory Commission, State Electricity Regulatory Commission. There were various debates, etc., meeting, etc., etc. Later on, it was decided that charging of battery of an electric car is not selling electricity. So there are various pros and cons, discussions, etc. Finally, it was decided that it is not selling of electricity, so no separate supply license is required for setting up public charging station. In fact, it is just to promote so that private investments come towards installation of public charging station. So you may ask question that in shopping mall, etc., etc. So they also sell electricity to various shop owners, etc. There is separate meter by the owner of that commercial building, etc., etc. So there is some difference that they are not just selling electricity, they are also selling service because they are maintaining the network and other activities are undertaken by the shopping, say, mall owner, etc., etc. So it is not directly only sell to electricity. So it is kind of service that they are providing. But that is why it is not required to get a separate, to take a separate license by that mall owner or, but similarly here the logic is that charging battery of a car is not selling electricity, so separate license is not. Then private charging is allowed. Private charging means, say, through my meter, own meter, domestic meter, I can always charge, no issue. I will pay the same rate that I am already paying. Similarly, any commercial commercial offices, so it is permitted. It is for captive. For captive, charging is allowed, and whoever will put up a charger, he will pay at the same rate that he is already paying. No separate rate. And under that guideline, that in all mega cities, so under phase 1, so much charging stations will be installed. Public charging station will be set up. Public charging station means anybody can set up a charging station and he will provide charging for any electric vehicles. So now in Kolkata, in and around Kolkata, there are some public charging stations in various petrol pumps. And also similarly in some other places like Khidirpur, the New Town, many places there are public charging station. Anybody can go and get the charging of his car. Now, under this guideline, the charging stations to be set up on expressways or highways, charging station every 25 kilometer on highways and one public charging station in an area of 3 kilometer by 3 kilometer. Then under phase 2, big cities, state capital or union territory headquarters targeted. Then for developing such charging stations, state distribution, electricity distribution companies, they would be the nodal agency in respective state. Now, under that guideline, it is mentioned that there is a requirement of exclusive transformer for public charging station. But I don't think so, because you see, in case the transformer is, so big, like in Kolkata, most of the transformer capacity nowadays is 400 kVA or 500 kVA. Then to provide 100 kilowatt load from a transformer is not a problem. But in case of, say, rural area or smaller towns where the state utilities, most of the cases, they use 63 kVA or 100 kVA. You see, they are using DC charging, that the power requirement we'll see later on will be, problem, because you see DC charging requires 50 kilowatt or more, and with a transformer of 63 kVA or even 100 kVA, so there could be problem regarding voltages. Now, for public charging stations, adequate space, naturally adequate space for entry and exit of vehicles required. Then tie up with online network service provider, it is required, because you see, so that, Airtel, Jio, BSNL, whatever, you see, so that, so any EV owner, he will know while driving his car that these are, one thing is payment online, another is that he will check that these are the public charging stations where there is a space or where he can directly go and charge his vehicle. There will be no waiting. So, and in his dashboard, car dashboard, he will know what is the position of public charging stations around him. So, and also the shared charging station data with state nodal agency, it is initially required to assess the growth projections, etc., etc. EV equipment, supply equipment should have been type tested, obviously, by accredited laboratory, NABL laboratory. Then public charging stations may be installed by housing societies, malls, offices, etc., hotel as well. So they can set up public charging station. There is no bar. Distribution company will provide a separate supply for such public charging station. For long range electric vehicle or heavy duty electric vehicle, there should be at least 2 charger with minimum capacity of 100 kilowatt, because they require larger power, and to reduce the charging time, minimum, this provision is there, so that the minimum capacity of the charger is 100 kilowatt and should be at least 2 chargers. Now, electric bus, initially the buses we see on road in Kolkata, the battery capacity was not much, 125 kWh. You see battery capacity, that the smaller battery till date we see the lead acid, etc., all are rated at voltage and ampere hour. So voltage multiplied by ampere hour gives us the energy. And in case of this larger battery, so it is in terms of kWh. And the batteries that those are used in power system, I mean in grid. So they are in the range of megawatt hour. You see, they come in a container, and so large capacity. Initially it was 5, 10. Recently I have seen that even 14 megawatt hour battery in one container, 20 feet container. So battery capacity for vehicles is rated at kWh. Now bus that we see mostly 200 and 300 kWh battery, larger energy in the battery, so larger vehicle, and they can run longer and range is longer. And to charge the battery, power requirement is 120 kilowatt, 200 kilowatt or 240 kilowatt. More power if we can provide, time takes shorter. However, battery should be designed to take that power. For 2-3-wheeler, capacity is very low, 2-3 to maximum 7 kWh. And charging power requirement 2 kilowatt, single phase supply is good enough. And one full charge, the range is 60 to 100 kilometer. 4-wheeler, you see battery capacity that we see in our country presently, you see in the range of 20 to 80 kWh. And power requirement is 12 kilowatt to 80 kilowatt to charge, fast charging. And range is 100 kilometer to 500 kilometer. So charging level, so there are various levels. So we can charge through AC. Level 1 power requirement is very small, 3.5 kilowatt. And naturally, time requirement is high, because you see, if we provide 3.5 kilowatt and if the battery, let us assume we need to charge 40 kWh, then so more than 11 or 12 hours time it will take. So for home charging, it is good. So throughout the night, battery will get charged. Then level 2 AC charge. AC relatively fast charge. So their power requirement is 7 kilowatt, 7.2 kilowatt up to 22 kilowatt. And naturally, since power is more, the charging time is quite less. Within 4 to 6 hours, we can get the battery charged. Again, it is suitable for home or workplace, offices, etc., etc. During daytime, we can charge. Now you see, then DC charging. DC charging is fast. So power supply, say up to 400 kilowatt that we see in some advanced countries, even in China. Then naturally, within 1 hour, or in some cases, I have seen even 15 minutes, you can charge battery, and normally it is prescribed to charge under DC up to 80%. Beyond that, you can charge, no issue, but battery is degraded if you charge beyond 80% with fast charging. Now, what is the difference between fast charging and slow charging, or AC charging or DC charging. Under AC charging, the rectifier is in the car. And you see, while charging through the rectifier, so there is heat, and we cannot keep larger rectifier inside a car, so it is a safety hazard. So that is why the power is limited under AC charging. Supply is AC, and DC charging, rectifier is outside at the charging station, and DC output is given directly to the battery. There, rectifier in the car is not used. So the rectifier outside the car in the public charging station, mostly, normally people at home, they do not put this fast charging. Now, under DC charging, so DC power is directly put in the battery of the car. So you can supply more power directly to the battery, and that is why it takes shorter time. Normally DC charging we see on public charging stations, on highway or commercial buildings, etc., etc. But at home or workplace, we see AC charging. Now, these are the some of the cars that we see around us. So DC charging requirement is 180 kilowatt for Mahindra XEV 9e or Mahindra B6, and highest Kia EV6 260 kilowatt, not highest, Hyundai Ioniq we can charge through 350 kilowatt charger, but this charger we don't normally see on the road. In India, mostly up to 80 or 100 kilowatt max. And similarly, for say Tata cars that we see mostly on the road, you see, they have option of both 3.3 kilowatt and 7.2 kilowatt under AC charging. And under DC charging, you see 25 kilowatt Tiago up to say Tata Harrier, bigger car, say 120 kilowatt. And there is a small car, perhaps you have observed on the road, you have seen MG Comet EV. So only AC charging is provided. No DC charging option is there. It is a smaller car. You see, even with 7.2 kilowatt, so purpose is served. Now, before I go to that impact of EV charging, should I stop or continue? If you have any questions up to that. Hello. Hello. Hello.
Yes, sir.
Are you hearing?
Yes, you are audible, sir.
Yes, yes. So my question is, should I continue, or if you have any question, also later we can have a question and answer session. You can stop me now. I can stop.
No, sir, you can continue after finishing your session.
Okay, then, okay, fine.
Last 15 minutes, sir.
Okay, fine. Then what are the impacts of EV charging on grid? One is increase in harmonics. Since there is a conversion from AC to DC, whether it is AC charging or DC charging, and power requirement is quite high, even say AC charging level 2 or DC charging. So there is a chance of harmonic injection into the grid. And we all know the effects of harmonic on the grid. You see the conductor cables or overhead lines. There will be some overloading on distribution transformers. Then power factor will be deteriorated. And voltage waveform, that is the, effect of increase in harmonics in the grid. And more line losses or transformer losses or transformer failure. There are chances of transformer failure. Then voltage profile will be degraded. You see, with sudden load, if the transformer capacity is not large with respect to DC charging, you see DC charging, if it requires 100 kilowatt and transformer capacity is 200 kVA, then with sudden that 100 kilowatt or more load, so there is chance of voltage instability. There will be voltage dip. Another issue is, you see, we have seen for that AC level 1 charging, so 3.2 kilowatt power requirement. Now it is single phase supply, 3.2 kilowatt. Now you see, if lot of people, they put electric vehicles on charging in a local network, so there is a chance of unbalance in the load. Heavy chance, because you see, normally in a home, load requirement is not much. So 1 kilowatt, 2 kilowatt, normally we have seen. And now here additional 3 kilowatt and in one phase. So there is a chance of unbalancing, load unbalance, and hence voltage unbalance in the network. And if the unbalance is quite high or voltage drop, higher voltage drop, then there will be reliability. Reliability means interruptions problem. Then because of large scale penetration, though it is welcome from a distribution company point of view, because they will sell electricity and they will earn money, their revenue will increase. But there will be increase in peak load. If it is not well managed, then there could be problem in the network, not only problem in the power purchase cost. So that we'll see later on. So demand estimation from EV charging is very much essential from electricity distribution company point of view. So some of the impacts, you see, graphs are visible. Hello? Hello?
Yes, sir. Yes, sir. Graphs are visible.
Visible. Okay. On our left,
Graphs are visible.
on our left, it is showing the load curve in a commercial area. You see, in commercial area, the blue line, this blue line is normal load curve. Let us assume there is no electric vehicle charging. This is the daytime load. You see, from say 10:30, and it is up to office area. Office, commercial means office, not shops, etc. Office load, 6:30. Now, if lot of charging is done in that particular area, Now you see the load will be the red line, this here. So there will be stress in the local network. So we have to assess, we means distribution company will have to assess it in time so that he can add the lines and transformer, etc., to combat the situation. Now, on the other hand, on your right, you see, again, this blue line, this one is the load curve. And during summer, we see the peak load during night time. And during daytime, load is relatively at a low level. Now we see in domestic area, this electric vehicle charging will happen during night time. People, when they come from office, and they will put on their electric vehicle on charging mode. In fact, I reside in a residential area. So, and it is quite big. I mean, 13th total area is quite big, and about 1,000 accommodations are there. And a number of electric vehicle I see there in the garages. And in the morning walk, I see that these cars, they are on charging mode. They come in the evening and they put on. Now you see, so in domestic area, this charging will happen when the load is already high, and it will again put pressure on the network, and it may cause overloading in the area until and unless the distribution company, they plan in advance. Now, this is an exercise that I talked and I did it with Kanpur IIT. The impact of EV charging on grid. So on the left, this is the EV charging. Most of the EV charging will happen during night time. You see, the private owners, they will do during night time. The buses in Kolkata, about 80 or 90 buses are there, electric buses. Mostly they do the charging during night time, and during daytime they do the opportunity charging just to fill up. So most of the loads for EV charging will be there during night time. Now, what will be the, let us assume the blue line is the normal load curve. So there are two peaks. One is during daytime for a normal, most of the cases that we have seen. And there is one evening peak, the blue curve. Now with EV, the red line, there will be, the curve will shift to in the night time more than during daytime. So daytime addition is not much, but during night time addition is quite high, and during this time, you see, peak will occur in the late evening time. This analysis, with large scale EV penetration, etc., this would happen. So load will be shifted. So earlier we have seen that locally during daytime, in commercial area, you see night time in residential area, but overall on the grid will be during late evening time. It is expected that peak will occur with large scale penetration of electric vehicles. Now, you see, one thing is the effect on the grid on harmonics, voltages, peak load, then heating effect, high losses, failure, etc., etc. So that is one thing. Another is on economics. You see, in our country, there is a market, power market. Every day, power is, there are people, I mean generators, or even maybe distribution company, if they have surplus power, they go to market and sell their power. And on the other hand, there are distribution companies, some big consumers, they go to the market and they buy power. And power rate is settled for, let us say, every hour. It is not fixed throughout. Now, rather every 15-minute time, a rate is determined on the basis of demand and supply. If supply is more than the demand, rate is low. If supply is less than the demand, then naturally a rate is high. So the simple on economics. Now, this is the situation that most of the day we see during daytime, rate is low, 2 rupee, 2.5 rupee, and during evening, when sun sets, rate is 10 rupee. So and this situation is expected to prevail in the coming years until and unless measures are taken. Now again, that will cost. Now you see, with large EV penetration, with more load during night time or evening time, so distribution company will incur more cost towards power purchase. And there is apprehension that electricity rate, if we cannot do it through commercial signals to the EV charging station or EV owner, so there could be impact on electricity rates. Now, this is the situation in a day where you see the yellow car is the supply during daytime. You see, it is, if you follow, so during daytime, now in our country, more than 100 gigawatt, maybe 110 or something like that, gigawatt solar plants are there. And they are in operation during daytime. And these solar plants, solar and wind, etc., even hydro, they are must run. Hydro, other than the large reservoir, having large reservoir, all are must run. Whenever source is there, they will run, they will generate, and they will inject into the grid. So during daytime, supply is more and load is not that much. So result is that black line. During daytime, power price in the market is very low, and during night time it is 10 rupee per kWh. And during daytime, often I have seen a rate is 0. I mean 0 paisa. So if anybody has gone to the market to buy power on such day, so he will get it at FOC, free of cost. So this is the condition. You see, this is the day. So during at 13:00 hours, so 1 o'clock daytime, so rate is 0. So this situation now we see in the market because of supply and demand imbalance. So with why I'm saying with electric vehicle, it will not improve the situation, and solar will be there because of, again, solar or wind. One thing is now economics is there. Another is, you see, there is India government has committed for net zero by say 2050 or something like that. So more and more wind and solar are coming into the grid. So this situation that we are already facing, it will continue further until and unless large scale battery storage, pump storage also, of course, pump storage is a solution, but there are some environmental issues towards pump storage. So battery storage nowadays are being promoted, and in many places battery storage will see to provide the balance for demand and supply. Now this is one report by Grid Controller of India. So it's a company, Grid Controller of India, under Power Grid Corporation. So in fact, they manage the load dispatch centers, national load dispatch center and regional load dispatch centers. You see, in a report, it shows that in a day, the frequency normally in our country, now all the generators, they run in synchronism. So frequency is same everywhere. And there is a limit of frequency, say 50.05 is the upper limit and 40, if I remember, 49.97 is the lower limit. Now, because of such imbalance, one day, this is the report, the frequency has touched nearly 50.35 or a little bit more. So, which is alarming situation. Again, this is because of more supply than the demand in the overall grid. Again, supply is more because of, you see, the thermal generators, they could not back down because of, again, economics is there, and all other must run power plant, whether wind, solar, then hydro, etc., they run in full, and because of that, this is the situation. So this is purely from generation point of view. So we have to be very cautious when EVs are coming into the grid. We have to have some balancing mechanism, and for that, battery storage is almost all the distribution companies, they are now seriously considering putting battery storage installations in their periphery. Now, what are the methods to reduce harm? So you see, for harmonic control, we know passive or active power filters are there. Then, as I said, that energy storage, if we have energy storage during daytime, we can store electricity there, and during evening time, we can discharge the battery and get electricity into the grid. Not only that, even for public charging stations, say with relatively large public charging stations, so there we can put up some battery there so that you see when all the time they will not draw directly from the grid. You see, they will put some energy there in the battery storage, and parallelly they will also supply from battery so that pressure on the grid will be less. And not only that, you see, if they opt for, or if TOD rate, time of day tariff is there, I mean, if varying rate during daytime is there, then they can manage it through the battery that they will have in their charging station. So when rate is high, they will get the supply from their own battery. When rate is low, they will get the battery charged. Now, another is demand response. Demand response is demand side management, but beyond the meter of the consumer. Normally, distribution companies they do not look beyond the meter. This is their responsibility ends at meter. But this demand response program is like controlling some of the demands, of course, with permission, approval from the consumer, like controlling some of the equipment of the consumers. It is not that they will switch off the entire supply, but they will switch off some of their equipment, some of the load, of course, with consent from the consumers, and the consumers will be financially benefited for that purpose. This is demand response. Now, many countries, you see, this demand response program I have seen about 12 years back in US, in Sacramento. And now many countries, even in Thailand, so they have a separate control room for demand response for large consumers. They are approaching that in case of any emergency or in case of any requirement, I will request or I will switch off some of your load, of course, with your permission, to operate the grid in a better, I mean, managed way, commercially as well as technically. Another option, we are seeing so many words about vehicle to grid, but vehicle to grid, I have some reservation. Vehicle to grid means from the battery of the vehicle, we can supply to the grid. Technically, no issue, we can do it. But the issue is that the battery of the vehicle is designed for number of cycles. Now it is for running the vehicle. Now if we use it to discharge to the grid, then cycles for running the vehicle will get reduced. Then time of day tariff, or time, rather I will say time of use tariff, is must. Now time of day tariff, now what it is prevailing, it is there are 3 time slabs in 24-hour time block. If you draw during daytime, tariff is normal. During evening, tariff is high. During night time, tariff is low. And it is not reflecting the market price that we have seen earlier. And it is same whether it is Sunday, Monday, and almost in all months, all seasons, it is same. So that is not desirable. The situation that we are seeing, that rather time of use, it will vary. So day in advance or week in advance, consumer will be informed that your rate will be during this time, your rate will, it is not hourly, but some time block, 2-3 time block, your rate will be such, and accordingly you try to use so commercial signal. Then smart grid, another option to reduce the harmful impact of EV charging. Of course, there will be some IT/OT infrastructure and coordinated integration of EV charging. Coordinated charging means, you see, suppose a public charging station.
And can I ask you one question?
Yes.
Sir, you have written IT/OT infrastructure. What is IT/OT infrastructure?
IT, information technology and operational technology, basically nothing but some equipment, some sensors will be there, and with some software we can control. Here I am giving you one example. You see, charging, let us assume that in a charging station, let us assume that they have, say, 2 chargers. Okay, say 2 chargers. Now 100 kilowatt, 100 kilowatt charger. But the gun through which the charging we can do, that 4. For each charger, it has 4 guns, so that it can accommodate 4 vehicles at a time. Now two vehicle has come, he can allow full 100 and 100 to 200 kilowatt charging. Okay. Now you see, if he has, say, if another 3rd vehicle is there, now he can allow another gun, but he can control the output. I mean, because he has limitation that he cannot draw more than 200 kilowatt from the grid. But now 3 cars are there and they are demanding 300 kilowatt, but he will not provide 300 kilowatt. Maybe he will provide equally 60, 60, 60, 66, or say somebody may ask that, no, I am in a hurry, I need 100 kilowatt, and he will pay extra. Somebody will, and the remaining 2 will get 50, 50, etc. So these are the, through IT/OT infrastructure, not only that, but also linking with distribution network infrastructure, maybe control room of distribution station for large scale such implementation will be controlled. Like you see, sensors and various things that we put. These are the IT/OT infrastructure. Even say, I can say smart metering. Smart metering, you see, it is a combination of communication and this IT/OT infrastructure. Smart metering, it is not only receiving data, it is also to do many a thing. Like you can control the consumer's point from a remote. So switch off, switch on, controlling it's a demand response. So it is IT/OT infrastructure, smart metering.
I got it. Thank you.
Now I have seen this. So these are the by doing network augmentation. We have to, a distribution company will have to augment their network. Then first thing is there has to be planning, load forecasting, planning. Then time of use, tariff, it is good. Tariff restructure, the same tariff that we are seeing, it will not be there. There has to be some commercial signal and more collaboration with manufacturers, battery swapping, so many things now are being considered. Battery swapping is easier. You see, you go, it is now for 2-3 wheelers, it is easy. But for a car, bus, it is impossible. Even for car, it is difficult, but still experiments are being done in various countries. I have seen that I have not seen, I have read that in China, so they have successfully implemented battery swapping station. Car will go and in a minute, the existing battery, discharge battery, it will take out and they will put the battery fully charged in a shorter duration. So then the waiting time will be much less. That is number 1. And number 2, the charging will be highly coordinated. You see, according to grid condition, tariff, etc., they will charge the battery. So this is about batteries. So people will go and replace the battery with a fully charged battery. So now for 2-3 wheelers, easy job. But again, it is being experimented. So these are the technologies for the future. So vehicle to grid that we discussed, it will help for managing the grid, but from EV manufacturer point of view, I think they have reservations. Then wireless charging, now it is also implemented. Then more renewables we want, at the same time we want more renewable. And in some places where the network is not very good, I see often interruptions, like in some northeast states in Arunachal. So I went there for this EV programs. You see, so they have a plan. In fact, I suggest, because their network condition is not good, and I mean very sparsely populated area, and network is quite long, so reliability is very poor. So there I suggested better you install solar panel and battery to provide charging on the road. So that, and they are implementing one, as I have heard of. So such things you see more clean. Then of course smart grid application is a must for large scale penetration of EV. So, and India has many other greening, the green initiatives. It's a battery storage that I told you. Then RE capacity is growing at a very fast rate. Now you see thermal generation capacity is very limited, but solar, it is growing rapidly. Now we expect that offshore wind will come up in a large scale. Then there is renewable purchase obligation. I mean, a portion of total electricity distribution company will have to buy renewable power. And same thing, that there is another renewable consumption obligation by large industries. We call it designated consumers. So DCs, they are asked, they are forced, they are through regulations that you have to buy a portion of your power from renewables. Then there is various other options, renewable energy certificate, etc., etc. Then, as I said, in the market, power market, there is a separate product. We call it, I mean, green. In that area, only green power is traded. Whoever has green power, he can go solar, wind, etc. He can go and sell to the market. And whoever wants green power, he can go and buy the market. For discount distribution companies or very big consumers who opt for open access. Open access means sourcing power from outside the distribution licensing. This is off-grid solution that I talked. Battery bank will be there, inverter is there, solar panel, and EV charging, and the local load, AC load is there. So I think that's all for today's discussion. Now, if we have any questions, we can discuss. Thank you. Should I stop?
Thank you, Rajiv sir.
Should I stop
Okay,
sharing?
so you just take a few minutes, sir.
Huh?
Thank you, Rajiv sir, for sharing wonderful and resourceful presentations. We have learned a lot from your lectures. Now, participants, your turn. If you have any questions you want to ask, please write in the chat box, or you can ask directly. Thank you, sir. Any question from participant side? I think there is no question, sir. Thank you.
Hello,
Hello.
is it I'm audible?
Yes,
Yes,
audible.
Yes, sir, session was very nice. You have covered so many things in a 1.5 hours. So, and it was a very informative. So thank you, sir. Thank you.
Okay, thank you.
Thank you, sir. So, you please write your email ID in the chat box if someone have any questions so that they can contact you
Okay.
in the chat box. That has written his email ID. Participant can note down this email ID. Thank you, sir.
Okay. Thank you. Thank you very much. So happy puja for
Happy
everybody.
Puja.
So yeah.
Happy Puja also, sir.
Okay. Thank you. Then should I exit?
Yes, sir. You can leave.
Thank you.
So much, sir, joined. Welcome, sir.
Sir, you are
Okay,
not
your-
audible.
Good afternoon, madam. Good
Yes,
afternoon,
good
everybody.
afternoon, sir.
Welcome. So, shall we start now?
After 2 minutes, sir, 3:30.
Yeah. Right. Of course.
So our next speaker is Mr. Somnath Sirkar, sir, Director, Algonic Systems Private Limited. So you will start at 3:30. Happy Puja, sir.
Happy Puja to you, madam. Happy Puja to everybody. Have a nice Puja and Dashera.
You can share your screen, sir.
Right.
It's visible, sir.
Thank you. So, I think
Yes.
we were talking on this topic last class, and let me continue from here.
Okay, sir.
Now, we were discussing the electronic and system configuration of the two main parts of the EV charger. So one part is the conversion of the AC to DC, and that is done by the PFC controller. And then the other part is DC to DC, so that the voltage level of the battery can be adjusted. The current of the battery is also controlled, and there is an isolation in this stage. So these are the two stages. So we shall go deep into the different configurations available for the PFC and the DC-DC stage. So this was one of the general PFC stage that we discussed last time. And this was one of the general DC-DC stages that we had discussed. Now, this is a 30 kilowatt EV charger prototype by Microchip. So you can just have a feel of the electronics of the 30 kilowatt level DC-DC 30 kilowatt level units. So these three units are in three phases, three-phase PFCs, and this is a transformer for the DC-DC stage, and this is a total electronics. This is a inductor for the output stage, I think. So as we had already discussed, this is a block diagram of DC fast charger for electric vehicles. So we have this power factor PFC correction, which is the AC to DC stage, and then the DC to DC converter, which goes to the connector and then to the battery in the EV. And these are the auxiliary supplies, AC to DC, which is used for controlling the system, and the HMI interfaces, external communications, external networking, and all these things. Now, this system controller also communicates through these communication wires, these communication links with the controller in the electric vehicle on CAN bus generally, so that it can understand the state of charge of the battery in the vehicle and the DC voltage level and the currents that are being fed, so that it can control the charging. Now, there are quite a few power factor correction topologies used for these sort of high wattage conversions from AC to DC, where the power factor is kept at very near to unity, 0.99 or 0.98, something like that. And the input current THD is also kept below 3% or 4%. So there are different PFC topologies for this thing. These PFC topologies can be enumerated like three-phase interleaved bridgeless PFC rectifier, then three-phase Vienna rectifier, three-phase boost PFC rectifier, three-phase active front-end converter, Swiss rectifier, three-phase neutral point clamped rectifier, and matrix converter based PFC. The seventh one is somewhat experimental, but it has quite a potential. So these are the different configurations that we shall take a look. There are quite a few similarities in these things. Some of the PFCs, like some of the AC to DC conversions here, are bidirectional. That means while it can convert from AC to DC, it can also convert from DC to AC. And that conversion is generally required for like vehicle to grid systems, where the transfer of energy is both ways. This is a three-phase totem pole bridgeless PFC rectifier. So here you can see after the EMI filter, these are the three lines, say, or the three-phase supply. After the EMI filter, there are three half bridges, and these three half bridges work at a frequency of say 20 kilohertz or 30 kilohertz, and there is a fourth half bridge which works at a frequency of about 50 hertz only. So these three are generally implemented on high-speed MOSFETs like silicon carbide MOSFETs for higher efficiency. This 50 hertz thing is generally implemented with maybe some slower switches is also fine. So here, what happens? We can show the similarity of these things. So after this conversion, this goes to the bulk capacitor. So this is the AC to DC stage. Here we also see the AC sensing circuit and the current sensing circuits. These can be CTs and these can be PTs also, since these are three-phase AC components. The voltage is of course sensed with a isolated sensing like linear optocoupler or something like that. Generally, we use linear optocouplers. Now, the three-phase totem pole bridgeless rectifier features are that each phase consists of two active switches in a totem pole arrangement, uses synchronous rectification for efficiency. Synchronous rectification means that both the switches are the switches work in complement as per the flow of the current. Often employs wide bandgap semiconductors like silicon carbide, gallium nitride for high frequency operation. Can operate in CCM, that is continuous current mode, or critical conduction mode for high power. These have the advantages like very high efficiency, up to 99% with silicon carbide MOSFETs, reduced conduction losses due to bridgeless design. Bridgeless design means in this case there are no diodes, only active switches are used. Supports bidirectional power flow with appropriate control, lower EMI, and smaller passive components due to high frequency switching. These are generally applied for DC fast chargers of rating up to 200 kilowatts, particularly in designs leveraging wide bandgap semiconductors for compact high power density systems. Next, we come to another configuration, the second one, that is three-phase Vienna rectifier. Here you will see that these are the three phases and these are switches. Like the boost here works like this, that whenever these switches closed, you will see that there is a sort of short circuiting within them, which increases the current, and whenever the switches open, the corresponding current shall flow through this diode half bridge. So with the switching adjusted such that the current in the inductors can be made to sinusoidal currents in phase with the voltage, that is how the control is done here. This is another configuration. This is also for three-phase input. The three-phase Vienna rectifier features a three-level operation, reduces voltage stress, lower switching losses, optional bidirectional power flow, stable DC output with reduced ripple. These can also have very high efficiency up to more than 98% and reduced EMI and compact design. These are also of the same range. These can be used like 50 kilowatt and above. But in case you see for these advantages here, we are using many more, like all these diodes are coming extra in comparison to the last configuration, that is the totem pole bridgeless PFC rectifier. This is the three-phase boost PFC topology. This is, I think, most common. Like it is most natural for it's a simple boost PFC, like the boost configuration that we are very conversant with. Here the current from all the three phases is controlled such that the input current remains in phase with the voltages, and there is only one switching MOSFET with this three-phase diode configuration. This is a three-phase rectifier configuration. This is the switch of the boost, and so this is a simple boost configuration. This uses IGBT and MOSFETs in a 6-switch topology. Boost inductors on AC side typically operate in continuous conduction mode. This, as I told, is simple design and control, suitable for a wide power range, robust and reliable. These are generally used up to 100 kilowatt, 20 to 100 kilowatt. Next, we can see a three-phase active front-end rectifier converter. Now, in this thing, you will see that
All participants, please mute yourself.
hello, yeah. So this is a three-phase active front-end converter. Here you will see that each of the phases with this inductor, here is a simple full bridge converter, like a single phase full bridge converter. This is for a H bridge inverter, we also use the same configuration. So basically you will see that this phase and this neutral is making this is just a sort of inverter. Now inverter makes DC to AC. In this case, it is making AC to DC, but the switching strategy is more or less same. So here it is basically, you will see that there are individual full bridges in each of the three phases, individual inductors, and this is a three-phase active front-end converter. Here, of course, it is bidirectional. Like AC can become DC and DC can also become AC, because this is actually a inverter, H-bridge inverter. But in this configuration, the number of switches used are much more, and also we are using three inductors are there in all the configurations, but the number of switches are much more. So for three-phase active front-end converter, we have full control over input currents, supports vehicle to grid functionality, that is, power can flow both ways, operates in CCM and DCM, that is continuous conduction mode and discontinuous conduction mode. The advantages are high flexibility for grid interactions, low harmonic distortions, and suitable for high power applications. Advanced DC fast chargers up to rating of 350 kilowatt with vehicle to grid capability. Now 350 kilowatt means as is normally available today, this is a highest rating. This is a more uncommon thing, but this has some like similarities with one of the earlier configurations. This is called the Swiss rectifier. Here also you will see that these inductors and here there are these switches. Whenever these switches close with the neutral, there is a sort of shorting and the current will increase. And there are also all these diodes as was the, but there are two extra switches to control the other harmonics. So this is a hybrid buck boost rectifier with fewer active switches than AFE, balancing complexity and performance. This combines active switches and diodes, wide output voltage range, high efficiency, and low harmonics. These have advantages of reduced switching losses, simpler control than active front end, and high power density. These switches are actually used for the buck control if required. So here there is boost as well as buck. This is a 3-phase neutral point clamped rectifier. This is like a 2-level inverter actually. So here you will also see that basically this is a 3-phase inverter, but with neutral point clamped configuration. This is for higher voltages. This is just like a 2-level inverter. This is 3-phase neutral point clamp rectifier, a multi-level topology using clamping diodes to reduce voltage stress and improve efficiency. This is 3-level operation. The normal ones are 2-level. So 3-level operation with neutral point clamping, low harmonic distortion, and high power factor, suitable for
low harmonic distortion.
Yeah, and high power factor, suitable for high voltage applications. Now here the advantages are also quite similar: high efficiency and reliability, reduced EMI, scalable for ultra high power. Since we can have much more voltage here, this can go up to 500 kilowatts. This is a matrix converter based PFC configuration. This is somewhat novel. Here we have these 3 inductors, and these are switches with like it can the full switch configuration. Then here is another inductor. I am not very conversant with how this actually works, but this is somewhat experimental and niche for DC fast chargers. This directly converts 3-phase AC to DC without a DC link using a matrix of bidirectional switches. This eliminates DC link capacitor. Direct AC to DC conversion with PFC supports bidirectional power flow. The advantages are high power density and compact design potential. I think this is quite interesting to observe, that there is no DC. All these things are bidirectional, and there is a sort of table according to which these switches to make this AC to DC conversion. This is also bidirectional. So this is a comparison of the things that we came across. That first was a Vienna rectifier, efficiency high, power range up to 350 kilowatt. This is bidirectional, limited bidirection. Applications are high power chargers. The boost PFC is for the medium power range. Efficiency is also moderate. Complexity is low. That is not bidirectional because there is a diode in the path. And these are for mid power level chargers. Then we had the active front end, which is the efficiency is high. This can also go up to 350 kilowatts. It is bidirectional. And since it is bidirectional, it can have V2G high power chargers. Then came the Swiss rectifier that can go up to 200 kilowatts. Complexity is moderate. The bidirectional is limited, and it's compact and high efficiency chargers. Then the neutral point clamped rectifier. This one, since it is a 3-level rectifier, it can go up to 500 kilowatt, and efficiency is also high. But the complexity of controlling all the 12 switches is high. It is optionally bidirectional and it can be used in ultra-fast chargers. Then we came to matrix converter. The efficiency is moderate. It is up to 100 kilowatt. Complexity is quite high. And this is experimental and niche chargers. And we also talked about the totem pole bridgeless PFC. That is up to 200 kilowatts. Complexity is high. Bidirectionality is limited. And it is high efficiency compact chargers. So any overall question on these configurations, and then we can move to the DC-DC converter stage topologies.
Participant, do you have any questions?
Thank you, everybody. So let us move to the DC-DC converter stage topologies. So there are only two actual very important topologies in this stage. The most important is this one. This is a full bridge LLC resonant converter. Nowadays, this gives the highest efficiency for its size. Now, what happens is here is a full bridge inverter, which makes high frequency AC, like say of 30-40 kilohertz. And this circuit is called the LLC tank circuit. So what the voltage that comes in this transformer, unlike most of the configurations, are not square waves, but these are like sinusoidal waves of that 30-40 kilohertz level, whatever is the switching frequency. So by this switching, here the switching is of course DC current, but this LLC tank makes it into a sinusoidal voltage. And so the transfer is much more smoother. And since AC current flows here, the switchings are also like zero current switching and zero voltage switching can be achieved. And that is how the switching losses can be reduced to a very great extent. Here then we have a full wave rectifier, and this is the output DC. So this is the input DC. This is the full bridge inverter, which is giving an output of 40 or 50 kilohertz. This LLC tank makes that DC switching into a AC wave, and the transformer faces just a AC voltage. The current also becomes AC in this circuit. So the switches can be operated in zero current or zero voltage switching with very minimal switching losses. And this is a full wave rectifier as the output. Another interesting thing that you will see is you need not have an inductor over here. Like in generally converters, you need an inductor here, but here the inductor may not be there. But generally, people put an inductor and capacitor to smoothen it out. A resonant converter using a full bridge topology with an LLC, that is inductor, capacitor, resonant tank. It operates at high frequency to achieve soft switching. That is zero voltage switching or zero current switching, minimizing switching losses. The key features are it provides galvanic isolation via a high frequency transformer, operates in resonant mode for high frequency, wide output voltage range, that is 200 to 1000 volt for EV batteries, typically uses MOSFETs or silicon carbide or gallium nitride devices for high frequency switching. The advantages are that with this LLC topology, we can achieve efficiencies up to 98%, more than 98% for this stage. Wide voltage range suits various EV battery types, and compact design due to high frequency operation. This is widely used in DC fast chargers up to 350 kilowatts, for high efficiency and flexibility. The main challenge here is to make this LLC tank. This needs some experimentation so that you can find the exact resonant frequency and the LLC resonance. That finding is more or less somewhat dependent experimentally, like you can have the maths, but ultimately some experimental fine tunings are required to achieve that resonance. Here you will see that it is more or less similar with the last configuration, but there is no capacitor here. Here is only an inductor. So this is a phase shifted full bridge converter. This is slightly simpler than the last configuration. With this configuration, you can have like a phase shift, and so you can have zero voltage switchings. A full bridge topology with phase shift control to achieve zero voltage switching, reducing switching losses. This does not give zero current switching also like the LLC circuit, but this can give you zero voltage switching. It uses a high frequency transformer for galvanic isolation and regulates power by adjusting the phase shift between bridge legs. We generally do it. This is somewhat simpler for our power levels of up to say 10-15 kilowatts. We generally use this configuration, phase shifted full bridge converter. This provides galvanic isolation, operates at fixed or variable frequency, and suitable for high power application with stable output. This is slightly less efficient, like high efficiency up to 98%, 96 to 98%, robust and well-established topology, simpler control compared to LLC resonant converters. This is common in mid to high power DC fast chargers up to 150 kilowatt. Now, this is a dual active bridge converter. Here you will see that basically there are two symmetric full bridges on both the sides of the transformer. So this is somewhat symmetric. So in this case, the energy can flow both ways. This is a main advantage of this configuration compared to the last one. So the diodes in the output has been replaced by active switches in this case. Like these are the active switches of the secondary. A bidirectional DC-DC converter with two active full bridges, one on the primary and one on the secondary side of a high frequency transformer. It uses phase shift control to regulate power flow. So basically this is exactly same level of the phase shift controller, only here these two things are symmetric. So power can flow from this side to this side or this side to this side, from primary to secondary or secondary to primary. This is the main advantage by replacing the diodes with active switches. So the key features are bidirectional power flow, enabling vehicle to grid functionality. So in case you want to take energy from the vehicle battery and push it into the grid for grid stabilization, those sorts of application need a dual active bridge converter like this. This also provides, of course, galvanic isolation, and like the phase shifted configuration converter, this also operates with zero voltage switching for highest efficiency, wide voltage and power range. And similar to the phase shifted, we'll see this is slightly more efficient. There's a reason for this. Since we have replaced the diodes with the active switches, so the diode drops are not there and the active switches losses are lesser. So it is slightly, maybe 1% more efficient. So that was 96 to 98%, but this is 97 to 98%. This also has bidirectional capability for vehicle to grid and energy storage, flexible voltage regulation. This is used in advanced DC fast chargers up to 350 kilowatt with vehicle to grid or high power capabilities. This is again the extension of the last configuration, but this is with 3 phases. This 3 phase has nothing got to do with the 3 phases of the general power supplies that like power systems 3 phase. This is of course of much more higher frequency, but here also with 3 phase configuration, it can be advantageous. So this is a 3 phase of the level of 50-60 kilohertz. These transformers are ferrite high frequency transformers, but these are in 3 phase configuration. So basically there are 3 transformers arranged in 3 phase configuration. And here also you will see the primary is symmetric with the secondary. So power can flow from this side to this side, that is primary to secondary, or reverse. The 3-phase dual active bridge converter. This is an extension of the single phase dual active bridge converter using 3 sets of active bridges with a 3-phase transformer to handle higher power levels. It is designed for ultra high power applications. As discussed, it is also bidirectional power flow with galvanic isolation. 3-phase transformer reduces ripple and component stress, and this can operate with 0 voltage switching or even 0 current switching for high efficiency. This is scalable for ultra high power chargers up to 500 kilowatts. This also have very high efficiency and low ripples. And since power can flow both ways, this supports vehicle to grid functionality. So these can be applied for ultra fast DC chargers like 150 to 500 kilowatt and with vehicle to grid systems. This is a comparison of isolated DC-DC topologies that we have discussed just now. So first, the full bridge LLC resonant converter. Here the efficiency can grow. This is the most efficient, as we had discussed. The efficiency can be higher than 98%. The power range is up to 350 kilowatt. This is, of course, complexity is high because you have to find the resonance. These are all these topologies that we have discussed are with isolation. But this LLC is not generally used for bidirection. It is very limited for bidirectional approach, but it can be used for high power chargers. The phase shifted full bridge is efficient up to 96 to 98% with the power range of 150 kilowatts. Complexity is not so much as a LLC resonant converter. It is moderate. This is not used in bidirectional configurations, and the applications are from mid to high power chargers. Then comes the extension of the PSFB, that is a phase shifted full bridge. That's a dual active bridge. It's a basically same thing with the secondary diodes being replaced by active switches. Here the efficiency is slightly higher, 97 to 98%. Power range is up to 350 kilowatts. And since power can flow both ways, this can be used for vehicle to grid or high power chargers. And 3-phase dual active bridge is an extension of dual active bridge. The efficiency of is same, but the power range gets enhanced up to 500 kilowatt. Since there are so many switches, complexity is high, and this can be used for ultra-fast vehicle-to-grid chargers. Any questions on this DC-DC topologies that we can go more into depth? Okay, let's go forward. Now, last day we had also discussed about wireless EV chargers, the upcoming technology. So here is a block diagram for the wireless EV chargers, where you will see that the thing is that there is a transmitter pad and there is a receiver within the car. This coil remains within the car, and this transmitter remains in this platform where the car comes and stops. And then there are certain configurations so that the electromagnetic field can be concentrated in this zone only, and there's not much leakage outside, since the distance is about, the distance between this platform and this car remains about, say, up to 200 millimeters. And then the power gets transmitted through this air gap. So this is a 85 kilohertz 85 kilohertz power coming here through this capacitor. This is a AC thing, and here also it's a AC, and here it is converted to DC. AC to DC is converted synchronously. And there is, of course, the wireless communication between the car and the station. So there is actually, we have done away with the connecting cable in this case. If this technology gets very common, then it is very simple that there is no connection, nothing. Only the car goes and parks at a certain place, and without any physical connection, it gets charged. Here we see that the three-phase mains is coming. It is getting converted into 85 kilohertz power and getting transmitted through these coils to the car. So wireless charging technology overview uses electromagnetic induction or magnetic resonance to transfer energy without cables. Induction is efficient for short range. Resonance allows positional flexibility. So even if the car is parked, say, 5 or 10 centimeters here and there, still the efficiency is quite high. Now, this is a big technology that efficiency up to 96% has been achieved. These certain companies, Vitricity and Oak Ridge National Lab, they have demonstrated that efficiency up to 96%, even with 200 millimeter of air gap and a power transfer of the level of, say, 200 kilowatts or 150 kilowatts, this is achievable. These pilots by Vitricity, BMW, Nissan, and retrofitted vehicles like Ford Mustang, Mach-E tested successfully. I do not know if anything of like this is being done in India, but these are global events and global advancements that are going on. Dynamic charging tracks in South Korea achieved 90% efficiency with cost-effective wire networks. In India, early adoption for 2 3-wheelers, Tata Power, Ether exploring solutions. So this is in our exploratory phase in India. By 2030, widespread adoption in parking lots and highways, dynamic charging lanes by 2040 to 47 in India with 5,000 kilowatt green energy stations. That is the prediction. Integration with autonomous electric vehicles and V2G systems, cost reductions via coil optimization. These are happening. Wireless electric vehicle charging, also known as wireless power transfer, primarily relies on inductive power transfer using magnetic resonance coupling. This involves transmitting power across an air gap, typically up from 100 mm to 250 mm, between a ground assembly or GA or transmitter pad and a vehicle assembly VA or receiver pad. Standardization efforts focus on ensuring interoperability, safety, efficiency, and electromagnetic compatibility across global markets. This is a big thing here, electromagnetic compatibility, because so much wireless power, I think, can disturb other wireless systems if not properly designed. The key organizations driving these standards are ACE International, IEC, and ISO, with harmonization through joint working groups. As of 2024-25, the topologies being standardized emphasize circular and double D, that is DD coil configurations for the GA and VA pads, operating at a nominal frequency of 85 kilohertz. So two antennas are getting standardized, that is circular and double D. Here is a comparison of these two antennas. One is single spiral coil and another is 2D shaped coils. So the first one has a vertical range of 250 mm. The second one is also similar, but the horizontal tolerance of the first one is 100 mm, but for the double D, it is 150 mm. Power levels are up to 3.7 to 5.0. So power levels are quite low as of now. Efficiency is 92 to 94%. Some advantages and disadvantages, like it's obviously convenient. Cable-free charging ensures user experience, ideal for urban and home setting. Revenue streams, dynamic charging enables new business models, pay-per-use on highways. No physical connectors, reduce wear and tear costs, and market appeal attracts EV buyers, especially for autonomous and fleet vehicles. For autonomous vehicle, this can be very good because the autonomous vehicle can itself go and charge itself and come back probably by itself. Since you do not need a man to come out and connect the connectors, everything. So everything can be done automatically in the autonomous vehicles. But of course, these are very highly costly as of now. The pads, expensive infrastructure limits widespread adoption. The market penetration is also limited to premium EVs, and this is generally pilot projects now. And investment needs, since this is very expensive, requires significant funding for public and highway infrastructure. These things we have already covered. I think safety, of course, this eliminates cables, so this is quite safe. This is flexible, and this allows a misalignment when you are parking the car. A misalignment of up to 20 centimeters is okay. This also can have V2G capabilities, enables bidirectional power flow, and since there are no mechanical wear and tear, so it is durable. But certain disadvantages that this is less efficient compared to the other topologies. Slightly lower efficiency, 90 to 96%, compared to wired systems, which is 98% efficient. And compatibility also requires vehicle retrofits or OEM integration limiting universal use. Because the secondary is always in the car, so the car must have sufficient electronics in it. And there is also, of course, installation complexity. Embedding coils in roads or parking lots requires significant engineering and maintenance. Now, I think we should also discuss another EV charging system, which is known as megawatt charging system. The megawatt charging system is an emerging high-power DC charging standard designed primarily for heavy-duty electric vehicles, such as electric trucks, bus, and other commercial vehicles with large battery packs. Developed to address the limitations of existing standard like combined charging system CCS, which tops out at around 350 kilowatts for passenger cars. MCS, that is this megawatt charging system, enables ultra-fast charging at megawatt levels to minimize downtime and support long-haul operations. Now, it is really surprising that megawatts of powers are going to be exchanged on these vehicles. Like probably it is like a small power plant or something, but not only currently we are up to 150 or 350 kilowatt, but these megawatt charging systems are also coming up where energy of the level of megawatts can be exchanged between a vehicle and the charger. So you can imagine how much infrastructure needs to be changed, like for an infrastructure consuming megawatts of power. I think nowadays these data centers that we see consumes about 2 to 3 megawatts, and what a huge power supply is required for that, the whole infrastructure. So each charging station will be equipped with such a huge power supply infrastructure to make these megawatt charging systems operational. This is something really of the next level. Core goal is MCS aims to provide rapid charging for vehicles that roll, fly, or float. That means the very big things, including class 6 to 8 trucks, buses, marine vessels, aircraft ground support, mining equipment, which are probably the biggest vehicles that people make, and rail and agricultural applications. It supports charging rates far beyond current infrastructure, reducing charging times from hours to minutes. Example, 80% charge in 10 to 20 minutes for a 1 megawatt hour battery. Now, even nowadays, as you will be probably knowing, that there are submarines which we use only batteries, and those submarine battery chargers are also of the level of this system, this megawatt level. Nowadays, these submarine battery chargers are being done by thyristor-based systems, and those are, I think that these chargers are so huge that each charger is located on this trailer truck. One trailer truck consists of one charger or something like that. It's so huge. So those are also megawatt chargers for classical batteries. But now these are going to come in much more compact, power dense applications with this megawatt charging system for all big vehicles with electric batteries. The power capabilities rated up to 3.75 megawatt, that is 3000 ampere at 1250 volts, that is 1.2 kV DC, though initial deployments start at 1 to 1.5 megawatts. This is scalable and future-proof for even larger batteries. Compared to CCS, MCS builds on CCS, combined charging system principles, but uses a larger, more robust connector for higher currents and voltages. It's DC only, no AC support, and focuses on commercial heavy-duty use, not passenger cars where CCS remains sufficient. Now, it is an engineering challenge, I think, to make connectors for such megawatt power transfer with sufficient cooling arrangements and safety arrangements. So just think of a connector which can handle 3000 amperes of current at 1.2 kilovolts of DC. Generally, these sort of things require very robust DC bus bars in our case in industry. So the key technical specifications and challenges of the megawatt charging system is connected design. A liquid-cooled manual plug and socket system for user-friendly operation without robots or machinery. So it has to be light enough for a human being to handle, and still it should, to make it feasible, I think it should be liquid-cooled. It features larger conductor cross sections for high current handling and emphasizes robustness for industrial environments. Voltage and current range, as we had discussed, it can be up to 1250 volts DC from 200 volts DC, with currents up to 3000 amperes. Then there are communication protocols for this also. Physical layer can be automotive single pair Ethernet, and application layer can be as per the software and all these things. There can be certain protocols. Now, safety and compatibility issues complies with holistic CCS system approach, including foreign object detection. Foreign object means within the connector, if there is some dirt or something, it can be quite dangerous. Electromagnetic compatibility issues are very high because with such currents flowing, it can create a huge magnetic disturbance. And high voltage isolation. It is designed for interoperability across manufacturers. Cable and cooling, liquid cooled cables, example up to 1800 ampere prototypes to manage heat and high currents. This is a really challenging engineering going on for these megawatt charging systems. The manufacturers involved in this megawatt charging system, at least 18 electric vehicle supply equipment manufacturers are developing MCS compliant stations, including Siemens, Kempower, and connector firms like Tobuldi, Amphenol, Cavotec, Phoenix, Rima, TE Connectivity, Huber, and these internationally known brands. Siemens have made a prototype, first megawatt charge on a production prototype in March 2024. Kempower has done something with 1.2 megawatt peak, upgrading from existing 600 kilowatt units. Then there's Hola projects in Germany, 4 stations along A2 Autobahn, starting at 600 kilowatt and upgraded to 1 megawatt in 2023. There is also Argonne National Lab in US, coordinating interoperability tests with 8 cable makers. Market readiness. As of September 2025, prototypes are in validation with commercial rollouts expected in 2026 or 27. It's not yet plug and play certified, but over 100 professionals are involved in global testings. Now, I think we can just touch upon the EV batteries, what the options that are going on. So the standard technology that is worldwide adopted now mainly are lithium-ion batteries. Lithium-ion batteries dominate the EV market due to their high energy density, that is up to 250 watt-hour per kg. Efficiency is 90% plus charge discharge efficiency, and ability to handle hundreds to thousands of charge cycles. This is a very big thing, thousands of charge cycles. I think the Tesla nowadays gives you a warranty up to 20 years or something. So that is very big. They use lithium compounds in cathode and anode with a liquid or gel electrolyte facilitating ion movement. Common cathode chemistries include lithium, nickel, manganese, cobalt oxide, NMCs. This balances energy density, cost, and stability, widely used in EVs like the Tesla Model 3, Nissan, and Chevrolet. Lithium iron phosphate, LFP, offers lower energy density but greater safety, longevity, that is up to 3,000 cycles, and lower cost, used in Tesla Model 3Y, some models, BYD vehicles, and budget EVs. And also nickel, and also lithium, nickel, cobalt, aluminum oxide, NCA. High energy density but less stable, used in Tesla vehicles for performance models. So we can have an idea of the batteries generally used in EVs. The small EVs use batteries up to 62 kilowatt hour. The most of the EVs in India also use batteries up to this level. For mid-range EVs, it is up to 82 kilowatt hour. High-end EVs can have up to 135 kilowatt hour, and heavy-duty EVs like the Tesla semi-truck or something, those can have EVs up to 900 kilowatt hour. And when it is up to 900 kilowatt hour, that is nearing 1 megawatt hour. So you understand that we shall need megawatt charging systems. The advantages of lithium-ion technology is high energy density, fast charging capabilities, and widespread production infrastructure. The disadvantages are mainly nowadays that we see is cobalt dependency, thermal runaway risk, as we see some fires and hazards of such in some cases, and high production cost for some chemistries. There are some other technologies also. These are emerging technologies like solid state batteries. Emerging technology using a solid electrolyte instead of liquid one, offering higher energy density up to 500 watt hour per kg, faster charging, and improved safety due to reduced flammability. As of 2025, solid state batteries are in early commercial stages with companies like Toyota, QuantumScape, and Solid Power testing them for EVs. Capacity is not yet standardized in mass market EVs, but prototypes suggest capacities similar to or exceeding high-end lithium-ion batteries, that is up to 150 kilowatt hour for passenger vehicles. Advantages are higher energy density, longer lifespan, and safer operation. Disadvantages, of course, initially high production cost, limited scalability, and ongoing challenges with manufacturing and durability at scale. There is another technology that we have all heard, I think, that is a nickel metal hydride technology. This is an older technology using nickel-based cathodes and a metal hydride anode, once common in hybrid like the Toyota Prius. Nickel metal halide is rarely used in modern pure EVs due to lower energy density. Here the energy density is up to 120 watt hour per kg, and efficiency compared to the lithium-ion technology. Typically 1 to 10 kilowatt hour in hybrid EVs, not used in modern battery electric vehicles. Advantages are these are durable, safe, and less expensive than lithium-ion batteries. A few other emerging technologies are lithium sulfur, LIS batteries, offers theoretically energy densities up to 600 watt hour per kg. Very high. I think that is more than thrice of the lithium-ion energy density, but suffers from short cycle life. Still in R&D with no widespread EV use. There are also sodium-ion batteries which use sodium instead of lithium, reducing costs and reliance on rare earth materials. Energy density is lower, 150 watt hour per kg, but companies like ATAL are developing them for budget EVs. Capacities are not yet standard, but expected to be 30 to 60 kilowatt hour for compact EVs. Now, there is another important thing with this battery is the battery management system, which always goes with the lithium-ion battery system. And we can just touch upon this battery management system also. Now, here you will see in the left that there are n number of cells. Each cells are about 4 volt, and there can be many cells depending on the capacity of the full battery. Now, this is the BMS. The BMS measures the temperature, voltage of all these cells and makes a capability estimation, state of charge, state of health, and thermal management. And this is conveyed through the CAN bus to the charger. This charger can be onboard charger or the EV charger that is directly charging the battery. This measurement also helps in cell balancing so that the voltages of each of the cells are very near. So cell balancing is also done by this BMS. This BMS electronics is fundamental to every lithium-ion battery system. A battery management system is an electronic system in an EV that acts as a brain of the battery pack. It monitors, controls, and protects the high voltage lithium-ion batteries or other types that power the vehicle, ensuring they operate safely, efficiently, and reliably. Without a BMS, batteries could overheat, degrade quickly, or even cause fires due to imbalances among the hundreds or thousands of individual cells in the pack. So the core job of a BMS is to optimize battery performance while prioritizing safety and longevity. It continuously tracks key parameters like voltage, current, temperature, and charge levels across all cells, making real-time adjustments to prevent issues. So we can just check the functions again, that it monitors, tracks state of charge, state of health, voltage, current, temperature for each cell. It does balancing, equals charge level between cells via passive or active balancing to ensure uniform performance. Protection, guards against over voltage or under voltage, overcurrent, short circuits, or thermal runaways. Thermal management regulates temperature by activating cooling, heating systems, example liquid or air cooling, and limiting power if temperature rises. Charging, discharging control manages fast charging rates and discharge during driving. This it does by communicating with the vehicle ECUs to limit torque if needed. And of course, there's diagnostics and communication, logs data for predictive maintenance, interfaces with vehicle system, dashboard displays, and external tools. So these are the, we have so far discussed the EV topology, that's a PFC and the DC-DC stage. The other emerging technologies like the wireless charging and the megawatt charging systems. We have touched upon the different battery chemistries and the BMS system. Is there any overall questions regarding these technologies that we can discuss further? Okay, let us go ahead. Now let us get an idea of the EV market globally. What is the context of this whole EV ecosystem? We shall look into some very interesting figures. So the global market present, the global EV charger market, the EV charger market is valued at 32.26 billion US dollars in 2024. Is driven by rising EV adoption. As of 2023, there are 4.5 million public chargers worldwide, with China leading at 2.7 million, followed by Europe at less than a million, USA 64,000, DC fast chargers up to the rating of 350 kilowatt are growing with 800 volt architecture and silicon carbide MOSFETs enhancing efficiency. Now the global market near future is by 2030, the market is projected to reach USD 125 billion. That is 24, it was 32 billion, and by 30 it will be 125 billion. With a CAGR, that's a growth rate, cumulative annual growth rate of 25.5%, with 12.9 million public chargers expected. So there are 4.5 million public chargers now, and that will go threefold to 12.9 million public chargers. Innovations like wireless charging, V2G, megawatt charging systems will support heavy-duty EVs. A bit geographic breakup of the market. China, over 2.7 million public chargers, as we have discussed, with 85% of global fast chargers and 55% of slow chargers. So China is a leader in EVs by a far margin. Europe, with 882,000 public chargers, with 70% in urban areas, mostly Type 2 CCS connectors. USA 64,000 public chargers with 20% DC fast chargers. And India, currently up to January 25, I think the figures have changed now. India is 25,000 public chargers by January 2025, up from 1,800, only 1,800 in 2022. So 2022, it was about 2,000, and 2025, it is 25,000. 10 times within 3 years. So the global installed capacity of EV is 2.4 kilowatt per EV. So this is a rating of how many EVs are there and what is the installed capacity. In Europe, it is 1.2 kilowatt per EV. In Korea, 7 kilowatts per EV, highest globally due to fast chargers prevalence. Even in India, it is more than Europe, that is 1.5 kilowatt per EV, with a focus on 2 and 3-wheeler chargers. In India, of course, the 2 and 3-wheeler chargers is quite a big market. Future projections, as we are discussing, globally it is about 12.9 million public chargers by 2030. USA, it will be about 0.5 million public chargers by 2030. India also nearly 0.5 million, that is 444,000 public chargers by 2030, which is expected to support 90 million EVs. And for heavy-duty vehicles, 2,000 gigawatt of charger capacity by 2035. That is for the megawatt charging systems. Now, I think we should take a look into probably one of the big innovators of EV technologies, that is Tesla and Tesla fast chargers. Here you see a photograph of the typical EV charging stations from Tesla, quite smart looking. Nowadays, the Tesla charging system is such that in a Tesla car, it will automatically tell you how far it will go and what are the chargers on your way. It will give you options where to charge, and as per your option, it will block the time in that specific charger for you to charge when you arrive at that charger. So it is very smooth. So the software and the networking manages everything for you, and you do not have to be very tense about how much, when you can charge your car or how much time it takes. So while a stop for 15-20 minutes can charge your car, and you can again continue your journey. Now in fast chargers, one of the problems is the heat management, of course. So high power generates heat in cables, converters, and batteries, risking thermal runaway. The solutions are liquid cooling, used in power electronics and cables to dissipate heat. Battery thermal management, advanced systems regulate battery temperature to prevent overheating and ensure longevity. And cable cooling, essential for high current applications to maintain efficiency. Here we see same thing what we have already discussed, sort of world map for EV charger deployments. You will see that the Asia Pacific is 51% because it is China is leading it, and Europe is 27%, while North America, being a very big country, it is 13%. Otherwise, it is very less in Africa and South America. So let us see the figures for the leader in EVs. The leading country is China. China's national rollout 2022-25, over 2.7 million public chargers deployed, with 85% being DC fast chargers up to 350 kilowatt, driven by government subsidies and NEV mandates, focusing on urban highways and rural expansion. The technology used are silicon carbide MOSFETs-based converters for high efficiency DC charging. The challenges are grid overload in high density areas requiring medium voltage upgrades, interoperability across manufacturers. And the successes are something like achieve 55% of global slow chargers and 85% of fast chargers, reducing charging times to 20 to 30 minutes for 80% battery fill. As I was telling you, they are also having data-driven planning via AI for load forecasting, improved grid stability by 15-20%. The technical details like 800 volt architectures minimizes loss, renewable integration, solar powered stations, offsets peak demand. Deployment in USA is like in 2024-25, 4,000 DC fast chargers up to 350 kilowatt across highways, part of NEVI program with $5 billion federal funding. Again, the technology used are liquid cooling cables and 3-level converters. That is what we had already discussed, the neutral point clamped topologies for heat management, NSEC protocol adoption for Tesla compatibility. Challenges are rural coverage gaps, USA being a very huge country with less, like huge rural areas. Grid capacity constraints with only 62% of needed level 2 chargers met by announcement. Covered 182% of required public DC fast chargers. Partnership with retailers Walmart boosted utilization to 70%. Technical details are similar. Silicon carbide or gallium nitride semiconductors reduce switching losses by 50%. Dynamic pricing via apps optimizes off-peak usage. Now let us come to the Indian market. What is the scenario in our country? India has about 25,000 public chargers, as we had discussed. Figures of January 2025, up from 1,800 in 2022, led by Tata Power. Tata Power has about more than 5,000 public chargers and more than 60,000 home chargers. Static has more than 7,000 public chargers and others. Battery swapping is very prevalent in India, is prominent for 2 or 3 wheelers. Now, India near future is targeting 30% EV sales by 2030. That is 90 million EVs. India aims for 444,000 public chargers. Government schemes like Prime Minister eDrive is investing INR 20 billion, and players like Exicom, Ather Energy will drive growth with apps enabling slot booking and UPI payments. Key trends are OCPP adoption, as we had last day talked about, renewable integration, and smart charging apps are shaping both markets, with India poised to become a sustainable mobility leader. Now, in this regard, I think last talk we had a question about the billing of the EV charging. So what I inquired and found out is that the EV charging is generally, if you want to find out how much will be charged in the public chargers, then you have to download their app and then find out what is their EV charging, which changes quite dynamically. So the charging system is, but it is these charging systems are the charge taken by the DISCOMs, that is the distribution company like ACDCL or CSC or whoever is the distribution company, plus the network charge, the company who has installed these EVs puts up a margin on that, and then it is charged. Like in Delhi, the charges are about 6.5 rupees, 6.5 per kilowatt hour. In Maharashtra, the charges are higher, 8 to 10 kilowatt hour, 8 to 10 rupees per kilowatt hour. But in Maharashtra, they give a discount for off-peak. So if you are charging it in the night time, when the peak demand is low, then you get a discount. So that is how you have to find out the charges for EVs in India. It differs from state to state and from a company to company. For a real rate, you have to download their app and check how much you are going to pay. These are some of the leading EV charger manufacturers in India, that is Tata Power. As we have said, that they have more than 5,500 installations. Then there is Static, Gurugram based, manages 7,000 plus chargers in more than 63 cities, offering AC chargers and DC fast chargers. There is Servotech Power System, Delhi based again, provides high power AC and DC chargers. There is Exicom, again Gurugram based. They have deployed more than 20,000 AC and DC chargers. And there is Ather Energy, Bangalore based. Ather specializes in two-wheel fast charging with Ather 550 plus grids in 56 cities. Now this EV charging, since it's a huge power consumption, the grid stability is always a question. So to install any EV charger, you have to plan the whole grid capability as per the EV chargers. So key facts are by 2025, EV adoption is expected to surge due to environmental policies and tech advancements, potentially increasing grid load significantly. Importance is balancing EV integration with grid reliability, ensures stable energy supplies, reduce outages, and supports renewable energy goals. So this whole EV charging strategy should be balanced with time of day charging and those sorts of incentives, so that most of the EV fleets can be charged at the night, and it should be also integrated with renewable energy goals. Impacts on grid stability. Transformer and infrastructure overload. High EV penetration can overload transformers and cause voltage drops. Renewable integration challenges. EV demand interacts with variable renewables, potentially destabilizing clean energy grids. real-time operation effects influences power quality, harmonics, and system balance in distribution networks. So resilience during events, managing charging excavates instability during disasters or high demand periods. Now, I think as Madam had asked, we have made a small video about power electronics development at Algonics. I can show you a small video of that. This is a setup for our grid-tied inverter system that we are currently, it is on the test bench. We were developing some features on that system. Here you will see that this is a computer system. This is a grid-tied inverter setup. Here, these parameters, DC bus voltage, VAC, AC grid voltages, inverter voltages, all these are being conveyed from the system to the terminal. It is not connected to the grid as yet when this setup was running. So DC bus voltage and inverter voltage are being shown. This is the MPPT boost converter part of the grid-tied inverter. So the photovoltaic cell voltage comes here and gets a boost, and MPPT, that is maximum power transfer algorithms, are implemented in the controller so that the solar photovoltaic cell can operate at its MPPT point. These are the sine wave, full bridge sine wave inverters. So this changes the DC voltage into the AC voltage. This is our from Microchip. This is a in-circuit debugger. So this is used to program the controller as well as communicate with the controller when it is running. So it is a in-circuit debugger cum programmer. This is a current clamp. This is an isolated current clamp. This is used for measuring the currents. This is a DSP control board with microchip microcontroller. That's a DSP IC, and this is the controller board. This is a waveform of the boost converter switching pulses for the MPPT controller.
ठीक है, सही लग रहा है?
हाँ बढ़िया लग रहा है। मेन लास्ट में 28 आना चाहिए बस।
डीसी में कौन कौन पढ़ाता है भाई?
लेक्चर राउंड में कर ले लिया।
बीसीए में खाली पढ़े हैं।
Thursday. Please mute your microphone.
ट्यूसडे
This is a output voltage and current with unity power factor. As you can see, this red is a voltage line and the blue is the current line. This is a 2-channel digital power meter from Yokogawa. So here we are seeing the output voltage. This is the current harmonics. So 1.195 is the current harmonics. This is the output voltage, and this is the output current. So it is 94 volts AC now, and the output current is 1.8 amperes. The input DC voltage is 111 volts, and the current THD is 1.195. So you see the THD is shown in percentages like this. This is the third channel, and this is the first channel. This is a power supply that we had made to simulate the PV cells, which is feeding to the grid-tied inverter. So this has got the characteristics of the photovoltaic simulator, so that we can check the MPPT points. This is also developed by us for our internal use. These are some of the other modules that we had recently made for railways. This is a DC-DC converter module. Here you see all these DC-DC converter modules mounted on the panel. Here it is the individual DC-DC converters. So these many configurations it can be configured for. This is actually inverters for Indian Railways. This is of the rating 1.5 kVA. Here we are. Here there are two inverters. These are actually configured in dual redundant mode, so that if one fails, the other can take up automatically. These are FRBCs, that is float rectifier cum battery charger, float rectifier battery chargers. So these are basically battery chargers, the same thing that we are talking for last 2 days, that is the EV chargers. So these are also battery chargers. These have exactly same characteristics like normal EV chargers, but these are of rating only, I think these are rated 3.5 kilowatts only. So that was all that was from my side. So if there are any questions, please let me answer you. I think we are already at 4:58, but if you have any questions, please raise your questions.
Any questions from participant side?
Thank you, madam.
You can write.
In that case,
You can write in the chat box. I think Shindula madam will ask some questions.
Hello, sir. Good afternoon.
yes, please. Good afternoon.
Thank you so much for this elaborative discussion, sir.
Thank you very much for that you are satisfied. I'm so happy.
Thank you, sir.
Thank you, sir, for your wonderful presentations. We have
you,
learned a
madam.
lot. I think faculties already noted your email ID. They will contact you. Thank you very much, sir.
Thank you. So we can leave now?
Yeah, yes, sir. You can
Okay.
leave.
Okay, thank you, everybody. Again, a happy Puja and happy Dasharat for everybody.
Same to you, sir. Thank you, sir. Yes. Our next session will be at 5. So now is 5 p.m. So Professor Dr. Ankur Bhattacharya he is our next speaker, and he will tell you about AI for smart grid and storage applications. Sir, over to you, sir.
Yes, am I audible, madam?
Yes, sir. Absolutely audible.
Good evening to everybody, and then also in
Good
this
evening.
puja and festive mood, still on Saturday evening, I'm happy to see almost 90 participants in this program. So it motivates me as well to start something new. Maybe let us, without wasting time, we can share the screen and I'll present that. Okay, thank you. Just a moment, let me share the screen. Can you see the screen now?
Yes, sir. It is visible.
Okay. Okay, thank you. Okay, so today's discussion is regarding the AI for smart grid and storage applications. I will be talking about mostly the applications of the AI in our electrical engineering, assuming most of the participants are in the domain of electrical and electronics engineering, it seems. So we will talk about different applications and how to choose different algorithms, suitability in different predictive analysis for the renewable energy based application, as well as the performance predictions specifically. And moving on to the content, today we are here to discuss about, first of all, the motivation means why should we go for the artificial intelligence and machine learning algorithms in renewable energy. And the second is the applications, as I said. Couple of sectors I have chosen here in this 1.5 hour lecture or session, you can say that the solar PV system is a major renewable source in India, countries like India, and backed up by storage systems. It has also a lot of capital investment, as well as the lifetime, the performance losses, typical behavioral issues are there, thermal managements of batteries, and also large scale storage supercapacitors also. And we will talk about how the AI applications and machine learning models can help in predicting accurately, where the modeling is always not possible. Mathematical modeling has some limitations where the data-driven models can play a great role. So here also further, moving on to the integrated systems from the renewable and the storage, we are having the smart grid applications where the renewable energy, where the ML algorithms can play a great role in performance prediction, techno-economic viability prediction and all, and followed by future scope and conclusions. So as I say, the need of this AI or machine learning or predictive analysis in renewable energy, most of the renewable energy sources are intermittent in nature, as we all know. And moving on to the further need, that exact physical model, as I said, of these energy systems are not accurately or accurate enough to establish or to you can say estimate the performance prediction under practical scenarios. Mostly random and nonlinear scenarios are there. Therefore, data-driven models are preferred to study the system performance. And machine learning models are, you can say, it's a subset of AI which can perform the better prediction and forecasting analysis when the data randomness level is higher and the feature selection or feature engineering faces challenges. Means there are important feature of a system when we extract its parameters. Let's say, for example, efficiency or losses or any kind of say, voltage fluctuation or power production from renewable energy under the impact of environmental impacts or the parameters if you want to predict. I hope I'm audible, right? Hello, am I audible properly?
Yes, audible.
Yeah.
Yes, sir.
Yes.
Yes, sir,
Okay,
you're
okay,
audible.
fine. Thank you. Just a check. I just thought of last day we had a problem. Anyway, so you can see the feature selection is an important parameter to be faced by the challenges faced by the ML engineers or the data science engineers mostly, where the mathematical model or the empirical models are not sufficient to extract the all the features as input to the model to predict it. And there comes the role of machine learning models, which can help immensely in data analysis as well as the features, data pre-processing, raw data removal of the negative values and say zero value imputations wherever there is a practical data set is available. I think there is some noise anyway. So in those cases, I think there is some disturbance. Somebody is on mute.
Please, participants, mute yourself.
Okay, yeah, it happens in a public forum, especially on Saturday evening. So let's move on to the next motivation, where it is important that as we are talking about the energy sector, the machine learning applications in energy sector, specifically, if we talk about the energy, you can see nowadays last decade and so we have taken also from this resource of the latest 2024 of an article that the energy sector has penetrated into greatly in predictive performance and techno-economic viability and societal effects, impacts. So there comes the accurate prediction of such kind of largely growing solar and as well as the renewable industries performance as well as the revenue should be predicted. There comes the machine learning plays a great role in these sectors, in addition to the existing engineering sectors. Last couple of decades, the energy sector has greatly drawing interest of the machine learning and AI models in predictive analysis. Moving on to the basic background of the AI-based predictive models, it means you can say if we talk about machine learning methods, classification-wise, it is broadly in supervised and unsupervised learning. And where in supervised learning, we have further couple of important areas to focus on. Here, this slide actually focuses on a couple of important aspects in the in all engineering problems, where we will choose an important applications of such cases, where the supervised learning further can be taken into regression analysis, different kinds of regression analysis, linear regression, and then support vector machines, different kinds of, and also the decision tree, different kinds of boosting techniques comes under regression analysis, where we can estimate its behavior of any system given some parameter as input as a sufficient data. And then you can see right from market forecasting to life expectancy. This is important where we go for the battery and solar panels. You know that these are finite life and a lot of capital investment is involved. So we need to have these life expectancy prediction accurately. Then we can have the proper ROI, return on investments, and the LCOE, different economic aspects we can think of. And then this is also one more important part for the renewable energy people, that is weather forecasting. That it depends, that impacts mostly in the renewable energy generations, that is the solar and wind, as we all know. So there comes the prediction of different parameter variations, radiation, temperature, then rain fall, and then also the moisture content, the wind speed. There are different cases which impact on the both solar and the wind power, specifically in the energy generation, which further can be utilized for our power systems. And now, population growth is another one more societal impact of this, but we won't go into that. We will mainly focus on the weather-based renewable energy generation prediction formulations, as well as the energy storage aspect and the integrated energy systems in this lecture particularly. Moving on to the classification side, there are different classifications of the this kind of supervised learnings. That is the image classification, diagnostics. Again, this diagnostics is an important parameter where the battery health monitoring, the solar PV health monitoring, and wind also. Those things are important to keep in mind, that the diagnostics matters a lot. Then one more important part is the unsupervised learning. That is the dimensionality reduction is important, because unsupervised learning, what happens, the ongoing process or online, it has to be trained and then followed by the prediction is needed. For that, we need a couple of data pre-processing in the raw data collection when it is from the field or from the actual system or the device. Then we have this data compression, then feature detection, as you were telling in the previous slide, that feature selection, feature engineering is a challenging task. And then big data visualization, the structure discovery. These are the data management and handling process. And then further, the clustering is also one more important part, where there is, you can see a microgrid. The moment all of our engineers here present, I am expecting we have this decent idea on microgrid and the smart grid areas, then we can utilize the AI tools in predicting its microgrid performance prediction. For example, there are multiple small microgrids are there. They are interconnected in a village or any community scale. Then the clustering is important, that where the types of only, say, prosumers means production and consumers both, types of the consumers only, where only loads are connected, where only generating stations are connected. That means the generators, producers, and prosumers and the consumers. The different kinds of classifications are needed based on the data generation as well as the mixing of the parameters, and then thereby training and of the ML models, and further testing on the different data of the same system we can think of. So these are the areas which we can focus on. And one more important or special area nowadays people are using in renewable energy applications, where randomness is more, there is a reinforcement learning. Reinforcement learning is one such case where more nonlinearity can be handled. And you can see not only renewable energy, but also robot navigation, means there is a dynamics of the robot is concerned, and its nonlinearity is concerned, where it is in different defense applications. Also the say skill acquisition of in a learning class, or the game theory is also one more optimization technique, where we can go for reinforcement learning based AI techniques in say cooperative energy sharing of multi-energy system, or say community-based energy systems. Those kind of applications we can apply in the machine learning techniques extensively in those cases, if we as electrical engineer, because nowadays only construction, only operation and control is not a factor. It has a level of saturations. Now electrical and computing is a big area of research, as well as especially for the faculty people who are faculty members, young, and also the people like us who are working in this area. It will be helpful for them if we can merge our mathematical background as well as the computational knowledge in the different kinds of mapping of parameters of renewable energy, and thereby classification and prediction. Choice of ML algorithms are important for such applications. So here comes the actual say step-by-step or a layered operation of the ML deployment, machine learning deployment, layers in energy applications. Let's say, for example, the generating stations, different generators are there. First level, data acquisition from there, data collection. In the second layer, there are a lot of data pre-processing is required in the next stage. That is the third level, where comes the data cleaning and pre-processing. Cleaning is important, especially for the renewable energy generation as well as the randomness in the load. Because of the data logger which you are using, quite often they do not follow the higher accuracy in measurement, as well as the calibration errors are there. For that, we need to have sometimes a negative value may come in the picture, which should not be there. There are some zeros comes in the null points come in the picture because of the improper calculations and calibrations of the data logger on field. So in such cases, we have to pre-process the ML algorithms, the data set, because the ML algorithms has to be properly tuned, and then it should be trained. Then only the randomness of similar kind of system we can predict accurately. So data cleaning and pre-processing will if we do not do it, will misguide the models while training. And then the data analysis of the new, say, different plottings techniques, further followed by training. And then optimization is also required for different, let's say, for example, iterations in machine learning models. They keep on iterating over the time. And then that also can be optimized, that how the good training of a data set, sufficient data set should be there, of course. That's one challenge in practical applications of the ML algorithms. And then the sufficient data of the field data should be used for the training, and then followed by the optimization has to be done. Different optimization techniques are there to optimize the ML performance, machine learning model performance, and then thereby deployment in the actual validation of the machine learning models. Means the prediction on the similar kind of systems, but with a new data set, or the similar cluster of data with a different data set. That is the idea of what we do in the layered cases. Yes, please. Any query? Okay, I think it's not. Okay, so you can see here one by one, if we talk about, as we discussed. Is there any problem at the other side? Anyway, okay, so you can see here this. Any queries, please let me know. Can I just request something? Please have any query. If you have, then let me know.
Otherwise, please participate. Mute yourself.
Okay, so you can see here this, as I discussed about the last slide, for example, here, the steps of the model training and prediction, that can be further elaborately discussed here. Let's say, for example, renewable energy generating stations, solar, wind, and hydro, biomass. These are power generation stage, followed by the power distribution. And I mean, of course, transmission has to be there, but these are distributed energy sources. So we are not interested in too much in transmission here. In this case of renewable energy, we straight away go to the power distribution sector, the load side, and then the consumption at where we can analyze. Followed by, you can see the raw data we first of all take from the, or acquisition is done from the real field. Remove the noise. That is important. As I said, data pre-processing and tuning is important. Step by step for any kind of machine learning users. They should follow these steps one by one. Not necessarily always all the steps will be important, but some cases, these are the thumb rule. We can go through these processes so that the tuned data can be used for training of the machine learning models. See, missing values, as I told you, that the data logger is an important factor of continuous data logging and then acquisition. And then there comes the missing values may appear, and also negative value also sometimes may appear, where we do not need those kind of values, or unrealistic values, or outliers, you can say. Outliers can be removed, and then also can be imputed with a missing values can be imputed. Then normalization is also one more important factor. Data normalization is important to keep it in the same platform to train it properly. Then processed data. See, from the raw data to the processed data, that is the flow of the work. And using this processed data, we divide into training and testing of the data set. That is also judiciously you have to do, that how much of data or percentage you have to choose as a training, and how much of data you have to choose as a testing. Or sometimes a new data set also can be used for the same system to have a more robustness check of the machine learning models. Because in reality, nobody will allow you to handle the similar kind of or same set of data, whether you can have a overfitting or the actual accuracy cannot be tested on the lab scale. That has to be always tested on the field data. That's why the data is a challenge. So now this is a power generation prediction, and it's a sample case where a couple of kinds of evaluation metrics based on which we choose the system, the machine learning model, which one is accurate, more accurate out of, say, multiple machine learning models. And also empirical model-based estimation also we should do. Otherwise, not necessarily always the machine learning is useful. Some of the cases where there is a more linearity in the system, there the models, the empirical model or mathematical model are sufficient. There forcefully you should not use the machine learning models. There comes the judicious decision where the machine learning model should be taken into consideration. There are some mean absolute error. R square is basically close to 1. It should be. It's called a correlation coefficient. as high the values towards 1, from 0 to 1, the accuracy is taken as a mode. Then root mean square error. Also, there are different mean absolute errors, average errors are there. So these are the evaluation metrics of the machine learning model performance. Also, the computational time, which I have not shown here, but later we can discuss about it. The computational time is an important factor. Well, not only the accuracy. If to get a better accuracy, let's say in a deep learning method, you are having multiple layers of a deep learning method. In those cases, accuracy may be higher compared to the regression analysis, but sometimes we need to have a more number of iterations and more computational time also taken to analyze or to validate those models and to come to a decision. That decision is always not so easy to do it offline. Sometimes we do it online or real time. So there is a very less amount of time is available to judge and to decide that prediction analysis as well further the actions. So in those cases, we prefer the faster response algorithms, even if we are compromising a little bit of errors, the accuracy. So that is important factor where the machine learning models can be chosen or optimization comes in the picture. If you remember, we have discussed an optimization. That optimization depends on only one is the model optimization, another is the performance based choice optimization, where the choice should be based on the ideas where you can say the choice of the machine learning model, which is more proper based on the different error metrics and also computational time. Moving on to the examples, I would like to hear today, mostly in this lecture or in this content, I have given you different ideas on where we have applied in our my research students and in our research group in this machine learning models in the last couple of years in different renewable energy sectors. And it will give you an idea of where to apply and how to choose those kind of machine learning model comparison studies for different kinds of renewable energy applications, and followed by energy storage and smart grid in this session. And remember one important part here, I am not to say discuss the any theoretical lecture of a machine learning model, how it is developed or how the mathematically model can be constructed. Those things we want to do it here. That is not the focus. Mainly focus is AI in renewable energy and smart grid. That has a specific separate session can be taken where the mathematical model of the machine learning algorithms can be understood. And there's a generalized lecture sessions. Those are not connected to any specific or dedicated area. But here, considering electrical engineers, we electrical engineers are not focused that much into the development of the algorithm. Rather, we can use the judiciously or choose suitable AI tools for our predictive analysis in different renewable energy or power system applications, where we can say, or power converter applications, where we can see the predictive analysis is important and followed by optimization of the process. We are more interested in the system integration level and rather by developing a new code for the machine learning models. But yes, of course, there are areas where people are more interested in the development of machine learning models. Those are different sector of research as well as the separate lectures. And we can definitely see there are multiple nowadays online sessions. And in NPTEL as well as the MIT course, there are different platforms are there where the generalized Python-based coding, how to write, or MATLAB M-file-based coding for the AI toolboxes usage, how to input the training data, how to declare the variable, how to choose the iterations, and where to stop the iterations, and how to use those kind of training. Those are available. But here our focus is the application or how to use these AI tools in the renewable energy. It will give you an idea. You can see here in this slide, we have taken one solar power generating stations where it depends on the weather parameters of sensors, and then monitoring stations where we are monitoring continuously the weather parameters, followed by the generation of the solar power and accurate data. Here you can see different types of layers are there we have used. It's one of our recent work in 2023 December, where we can see here the parameter selection, the missing value imputation, and negative value removal. As I said, the solar is a random power generation. That time, the data logger is not always in picture, where it can take continuous data or also all positive data. There are calibration errors. There are the electronic hazards, which can have the data acquisition impact for longer time. Let's say 1 year complete data, seasonal variations we can have for the solar, or the daily variation, weekly variation, monthly variation of an area of a solar PV power generation under the impact of renewable weather conditions. Let's say wind speed, radiation of the, and then also the say temperature, ambient temperature. Those are the things which we can definitely, consider. And here we have considered those weather parameters, and then we have written the equation of the solar power generation, and that as a function of those weather parameters, we have taken, and then finally we have cleaned the data and pre-processed based on the negative value removal or missing value imputation. These are important part, and there are a couple of tools to justify the pre-processing, and finally the processed data can be, as you can say, the meteorological feature analysis. This is important. Meteorological feature means, as I said, the weather parameters as a important function here, and dimensionality reductions. There are some outliers. We can reduce those things. Say, for example, 10 kilowatt solar power you are putting. Sometimes the 1000 watt per meter square radiation, it becomes more than that, the capacity which actually is not generating. Those outliers you can remove. And then that's called a feature selection and feature engineering, which is an important integral part of a machine learning model. That is important. And then the process data we are putting towards some deep learning like ANN, artificial neural network, and then some ensemble-based learning like random forest, XGBoost, adaptive boost, then light GBM. There are different types of learning techniques or boosting techniques which gives a faster response and can handle the nonlinearities. And deep learning is, of course, superior than this in terms of accuracy level, because it takes more number of layers of check, but it takes more time to analyze. So computational time is more in such deep learning methods compared to the boosting techniques. There comes the choice of the machine learning model, which should be chosen for a particular applications. Do you need the highest accuracy with a longer time duration of the computation, or you need a faster convergence with a little bit of errors are also can be handled. Those kind of things should be optimized in terms of the computational part, in terms of electrical part, in terms of the financial part as well. Everywhere the finance is involved for the such kind of investments and the return of investments. You can see here the performance prediction, as I said, techno-economic analysis of the installed solar and the new solar projects in the same area. Why same area we're talking about? Because the regional weather matters a lot. In this case, we cannot just use the same ML algorithm always. Let's say in Rajasthan or in Hyderabad or in West Bengal, the same algorithms might not always work based on its meteorological data pattern and solar power generation. So it's preferable to use the similar region for the wind and solar, so that the randomness can be somewhat predicted, not by too much random or too many randomness in the data pattern. The ML models cannot work in those cases, especially in the supervised learning methods. If it is unsupervised learning or the reinforcement learning, there comes the reinforcement learning methods. There comes the different game theory optimization. There comes the unsupervised learning, where such randomness in renewable energy sector can be utilized other than the statistical data-based analysis, which we quite often do. And now this, you can see here, this power prediction of the solar based on the weather parameters. If the prediction is correct, it will followed by the demand side management. That is one more important part in the microgrid or the smart grid applications, where the community-based demand side management can be done further if the proper prediction of the generation and the storage is done. So that these are all interlinked. So proper prediction is, of course, important. Accuracy is always important with the quicker convergence. If you see here, the couple of equations we have written just for the sake of understanding, as I said, that weather parameters, you can see here not only the weather parameters, but also there are elevation angle of the solar panels, tilt angle, latitude, and the radiations, the direct radiation, diffuse radiation, different kinds of the radiation also. Then there's the albedo, different effects are impacting the power generation of a solar power. And those are, we have taken one model considering all the such weather parameters possible, or the major, there are still more, but major contributors of the solar power generation, which are the radiation, the ambient temperature variations, as well as the different soiling loss. Means sometimes dust is a factor in countries like India or in desert areas, where dust is a big factor. 30% of the losses can come out from the soiling loss, which can impact the generation, and impact the power generation means impact the return on investment also. So those are quite linked or interlinked with the prediction of the solar power. Remember that the countries like India, where the cleaning of the solar panel is also an important and challenging task, also is a cost, a high cost is involved because manpower or robotic cleaning nowadays people are using. Everything needs power and the finance. That means those can be proper scheduling of the cleaning in an area can be predicted if the power generation pattern is predicted over the time. So using machine learning models can help us a lot because of the statistical data for say over the period of 1 year, entire seasonal variation we can have, train the models, and then for a new season for the next year, we can year ahead prediction or month ahead prediction we can do, and we can accordingly plan our cleaning schedule of these solar power panels to avoid this or to reduce the soiling loss and to increase the generation yield of the power. So these are the important parts. So these are the interconnected, how these variables are used as a solar power prediction in terms of the weather parameters. And followed by, we have used a couple of machine learning models here in the, as I said, the ANN, you can see first one is a artificial neural network, then it is the XGBoost and the random forest. So the three algorithms we found out to be somewhat nearby the actual and the predicted, where you can see ANN is to some extent not that much with accuracy compared to the other two, because it has especially the time series model. Because of the time series means with respect to time is the x-axis in the time, and the power generation is y-axis. Remember, the power generation y is further as a function of different weather parameters we have discussed, and then we have given those as input feature. So what happened to the ANN that because of the randomness we have introduced in the model, and it has multiple layers, it could optimize further towards the higher accuracy. But what we have done is that to optimize the time, we did not give it a longer time or longer epochs of the neural network. As a result, we have given, see, rate 1 is the slope of the predicted power. Of course, it's not a linear because of the predicted and the actual. We are y-axis is predicted power, x is the actual power, and we are putting one linearized line where the scattered plot we have done. This is basically a scattered plot where the actual power is here and the predicted power we have done. So you can see here a couple of, coming to this one, this slide will give you more better picture, because that slide was the x and y axis are the actual and the predicted power. Here is the with the observations. You can see here the pattern. You can see here the same ANN neural network. The boosting techniques are also put where the ground truth or the actual values are the blue graph, and the yellowish or the orange graph is the predicted value. You can see here for the ANN, you can see we have taken one real data over the time, and you can see the randomness appeared here. It's a somewhat sunny day where towards the end, of course, there is a fluctuation because towards the end of the day and the beginning of the day, this is the peak time where sudden cloud came. You can see there is a dip in the there's a dip in between the peak time. So that's the cloud passing. It's a real field data. There comes the importance of proper training and optimization and also tuning of the machine learning models to have a better predictions. This ANN, you can see here quite a lot of errors are there compared to these boosting techniques. XGBoost performed a lot better compared to the other two because of these mathematical properties and handling the boosting techniques. They handle the ensemble learning, means they handle nonlinearities, and they have also self healing property. As a result, you can see here the performance comparison which we have done. As I remember, R square is called R2 score. R2 score or R square, sometimes it is told as. Correlation coefficient, it basically correlates as it is close to 1. So that means the actual and the predicted are very close to each other. That means it is well predicted. Then mean absolute error, the root mean square error. These are important parameters which are the major metrics of the machine learning models. As I told you that time required is a very crucial factor for the machine learning models, not only the accuracy. Sometimes accuracy we may find it is a better accuracy, but with more time required. Sometimes less accuracy with lesser accuracy compared to that, but with quicker convergence time. You can see in microsecond if you talk about the data training time and the average required for prediction time also microsecond. But remember, there are other factors also where the computer configuration, where the processor speed, that also matters a lot. So what we are doing we always compare in the same platform so that we can actually compare their performance. We should not allow the ML programming coding in different computer platform. That would be a problem because we cannot then analyze the computational time actually, because there are different other factors other than the mathematical complexity of the algorithm. So you can see here the XGBoost, as from the result also it is shown that here this is more accurate compared to these two, and closely it is this. But however, the time required for the training as well as the testing or prediction is quite long compared to the XGBoost. It's a extreme gradient boosting. It is a very important gradient boosting technique which works under the ensemble learning, or you can say the proper handling, this anomalies in the data. Not only the pre-processing, but also after pre-processing as well, there are some anomalies there in the data. So those are not ideal case, but these boosting techniques, adaptive boost or extreme gradient boosting, can handle such cases in electrical engineering domain, specifically renewable energy, where randomness is more. You can see here 98.4% accuracy we can talk about nearby. 0.984 is somewhat like 0.1, I mean, close to 1. This is also close to 1, but the problem is, you can see here the computational time is more compared to this. So here comes the superiority of the XGBoost. So for these cases, we have also used a couple of other algorithms, but these are three are the nearby, which gives us somewhat decent accuracy. And then we have chosen the XGBoost for these cases as a best algorithm for this particular case. Remember, if it is actually, this was done on a scenario in Hyderabad and in a day profile, definitely this algorithm may not be working same as in other states or other regions based on their randomness and their profile of the climatic conditions, also the randomness in the weather condition, I mean radiations profile also, it will be varied. So that's why the statistical data and the training data is so important. We cannot generalize a machine learning model for any kinds of say prediction of renewable energy performance at any, irrespective of the regions. It is actually region specific for such kind of renewable energy applications, specifically the solar and wind. Now, here comes the one more important portion of the transmittance. Moving on to the solar power prediction. One more interesting part, as I tell you, that is the light trapping. As you know, that solar cells, the moment we are thinking of the power generation, light trapping is, or light penetration is most important part, or called the transmittance. So optical performance of the solar panels are very crucial for the power generation aspects. So that's why, thinking that in mind, in our BITS Pilani Hyderabad campus rooftop of our departmental building, we had different tests, and we have collected the data over the seasons that natural dust deposition, because it's a rocky soil nearby. So a couple of the dust grain size is quite more, not like normal desert or the beach areas where the dust is also there are different grain size of the dust are varying, and they are accumulated on the solar panel surface. These are called the glass surface, which glasses are actually custom made glass. It's called low iron glass, which are the glass sheet on the top of the silicon cells. If you have seen the real solar panels, you might be understanding that there's a glass sheet on the thin glass sheet on the it's called low iron glass. It has high transmittance capacity, and put on the silicon solar cells. Primarily monocrystalline, polycrystalline, those are the silicon solar cell we use for our commercial applications. And here you can see that experimental data set we have decided for this particular case as 80% of the training and 20% for the testing. Why it is given there as a thumb rule, but definitely it is not always true, because to understand the more randomness and the robustness of the machine learning models, we have also done is 60%, 40%, 50%, 50% training testing to check how the inaccuracy can impact the model performance, and based on the lesser training and more testing data. This is also in reality, randomness is more for those cases, because natural dust deposition has no pattern. It has over the time, it goes on. Of course, seasonal variation, wind speed also one more factor, which very much windy conditions, natural dust might not sustain on the solar panels for longer time, because those are not flat always. Those are somewhat inclined. So if there is a wind flow sufficient, those natural dust will not be sustainable on the glass surface of the solar panel. Thinking that, you can see, as I told you, that data logger has couple of anomalies happens. So we need a feature extraction and the selection, input feature, output feature, and the control feature we have to understand. Then machine learning models are fed with the process data. This is the data processing and tuning, where we have taken a couple of algorithms here. For this case, again, it's a time series data. Where we can say that the nearest neighbor of the algorithm is one more important part where the time series data can help. Decision tree are the regression techniques, random forest, and gradient boost. You see, XGBoost we have used in earlier cases. It's called the extreme gradient boosting. And this is also the gradient boosting technique, where these random forest boosting techniques are actually helping in time series data, and where there is a chance of getting outliers still after pre-processing, where there is a chance of getting missing value imputation. Those automatically they can adapt from the iteration process, and they can help in better prediction. Those kind of cases we use random forest and then the boosting techniques. And you can see here, as I said, low iron glass. This is one typical terminology here. Why low iron glass? Because this is a typical glass material which we use for the covering the silicon solar sheet on the panels. And you can see here horizontally placed, just for the sake of case study, we have done vertically placed and inclined. You can see inclined is there. These samples we have taken from the commercial solar panel manufacturers, where we have liaison and projects with them, funded projects. And then locally inclined solar, I mean, this kind of the glass irons, glasses are important, where you can see here the actual panels are kept there. We cannot do the optical tests in the spectrophotometry with a real panel there in these machines. So we have to use the sample glasses of the same material which we are using in the surface of the solar panel, and we are typically putting it aside, and then we are exactly beside the solar panels. We keep those glasses and the same inclination angle, or the say the total flat or the horizontal axis, vertical as well as the inclined, we keep those things just beside the solar panels. And then what we do is that we observe over the time, like 15 days each interval we have taken, and then the data of the dust accumulation, natural dust accumulation on the rooftop solar, you can see here. So we are testing its under the light beam, the visible range of the 300 to 1200 nanometer. We are putting those range of the optical inputs, and then we are taking the light transmittance data of the glasses, assuming this is the same condition also happening in the real solar panel. Those are the issues where the power generation also we are measuring. At the same time, we are making a map with the radiation, with the power generation of the solar panel and also the optical parameters, light trapping or the transmittance of the solar, glass sheets just kept beside the same area, so that this similar kind of dust grain also comes on the glass sheets. And we are over the time, say 15 days, 30 days, 6 months, 1 year, like that, we are testing. And then what we have done, we have understood, we have gathered thousands of data points over the time, as you see here, with a 1 year sort of impact, where 30 days, 60 days, 120 days, and so on. And horizontal, vertical, and local tilt angle, we have seen the average transmittance, you can see, goes decreasing. You can see here over the time, if you do not clean that, carefully you have to handle this. We had to handle this glass sheets so that the dust particle are as it is and keep on accumulating on this sheet. You can see here it is decreasing in nature, the transmittance with the time of the dust accumulation. And what happens, we have used these data points. It's an average data here. That's why it's average. Basically, it's more than 10,000 data in each column. Then we applied different machine learning models to train the data of, say, 8 months, and rest 2 months we have used for the testing data to understand the accuracy of the prediction of the transmittance profile, how it is nearby. Then we can conclude that if it is somewhat nearby 1, the R square, you can see here for some algorithms, then we can assume that the transmittance prediction is accurate, means the power generation prediction also will be accurate, because transmittance and power generation is somewhat directly, almost closely proportional to each other. Of course, there are other nonlinearities there, like for example, wind speed, as I said. There are sudden rain may come, there are sudden cloud may come. Those are weather dependent cases. But if we talk about majorly for the soiling loss, This work specifically one of our previous work which we have done in IEEE, we have published in a conference there. So what we have discussed about with my students is that the impact of the soiling loss on the power generation using machine learning models. Here also a couple of, as I said, the boosting techniques and the nearest neighbor algorithm we are thinking of. We can see here the superiority aspect wise, these are quite neck to neck, but at the cost of the root mean square, still it is less. This mean absolute error is less. This should be high because it should be close to 1, and others should be lesser value in the error aspects. So these are important factors which we have to consider. And this is the graphical approach. If you remember, we have discussed about the predicted value and the actual value. The actual value is this one, and the predictors are the scattered plots. You can see here, this is the algorithm where gradient boosting and random forest, which are quite close to each other. But again, based on the other error parameters like root mean square error or the mean absolute error, also the computational time, which have chosen the gradient boosting techniques for this particular case. So there are, as I said, this we have done it for our scenario here in this region, southern region. Definitely in different region cases, the dust particle, the dust grain size, the pattern of dust deposition will be changing. So those region-based, there is no generic or no universal model of machine learning model which can predict all possible areas under the impact of the environmental cases. For the battery, for example, batteries cases are different. Those are having somewhat application to application. It can be almost predictable, but for the renewable energy generation like solar and wind, those are region specific and weather dependent parameters. So there comes the customized machine learning models are chosen based on their performance, and then followed by scaled up in the same area, but different. Let's say if you train for a Hyderabad-based data and want to test for West Bengal data, definitely there will be anomalies and that won't be that much accurate in prediction. Pattern may be same, season to season. Let's say summer season you do here and summer season also there. Pattern may be same, but polynomial pattern may be same, but there are a lot of anomalies are also. The phase mismatch over the time. There will be those issues of mismatch and also underfitting of the machine learning models. You can see here, if we talk about, as I discussed, that this is the horizontal glass. 3 cases we have taken. One is horizontal glass plane. If you remember those slides, we have just now visited the slides. And one is the vertical one, vertical positions, where we can see that very less amount. Why you have taken? There are a couple of cases we have seen. Why vertical? Practically, it is not possible. It seems that vertical solar panels, why it is possible. But there are some cases called the BIPV. It's called a building integrated photovoltaic systems. Those BIPV applications, especially in India, it is not that much popular, but in countries like UK and Europe, there are multiple cases. We have seen that the BIPV is also in the wall. They are fixing the solar panels to have the at least coverage area of the weather dependent solar radiations. Not much radiation is available, but wherever they are getting some chance, they are generating power with the green sources. So they are using these solar panels on the vertical position as well, and also the flat position on the rooftop based on the coverage area. But in India specifically, where abundance of solar radiation is there, we can say abundance is there. So we can use the either tilted in an inclined angle, or we can use the different say trackers of the solar panel throughout the day. Sun trackers we can use by motorized, but that also needs power from the solar panel itself. But we can have a fixed south-facing solar panel, and where inclined angles based on the region to region, latitude to longitude, it varies the angle of inclinations. So you can see here the vertical position also we have discussed, and we have analyzed the data which we have taken from the actual setup. And then we have analyzed the optical parameters, the transmittance, and we have used for the next, say, couple of months, which are unknown, but the same area, then how to predict those generations. So based on the data set acquired, we have understood that this is the gradient boosting. Further also for this case, it is giving the superior result. So same area, horizontal and vertical positions, although very less dust can be accumulated, but still that is important to analyze how good it is. But also at the same time, power generation wise, it won't be good, because the horizontally placed solar panel means it is hardly getting any, at the peak time, peak sun time, it won't get the power generated. And only in the morning and towards afternoon, it can generate the power as per the sun path. That means the inclined one will be the best solution for the power generation. But provided here in this work, we have this soiling loss only, the dust particle analysis only, which can impact the power generation of solar energy, that we are predicting using machine learning models. As I said, this is also one more such picture where it came from the vertical positions. And then comes the horizontally, the locally inclined, which is actually most popular in countries like India, where you have done in the same area. We have used the locally inclined based on the calculated angle around 13 degree. We have used this glass sheets, and at the same inclination, we have also used the actual solar panels on the side by side. And we have taken every 15 days samples. And then we have taken the dust samples, and then we have processed the data, and we have analyzed the optical parameters by putting the glass under the light beam and as the visible light beam. And then we understood that the transmittance, if we train it and then further test, we can see that the predicted transmittance after, say, 1 year, the actual and the predicted is 99% accuracy. That means with respect to this, if we talk about then the nearest data is gradient boosting, which is coming. Also, quite a lot of nearest data, these two are having random forest and decision tree. The K nearest neighbor algorithm could not perform much. You can see here the scattered has the pattern, which is more on the actual values, less on the outlier for the gradient boosting. So gradient boosting is actually giving you a better result in terms of accuracy and also the time we have analyzed. So these are the important where the locally inclined glass sheets are there. Now, these are the cases where we think of the solar power generations and predictions. Coming onto the energy storage part, that is important. Total, say you can say energy systems mainly we look into the BMS, battery management systems, or the supercapacitor energy management systems, or the fuel cell energy management systems. Here we will focus on a couple of important points for the machine learning, why machine learning models are so important for the energy management of batteries or the health management of the batteries. So power loss inside the battery pack during charging, discharging is also unpredictable. Thermal behavior of the battery storage under different operating conditions, remaining useful life, state of health are the major parameters to be predicted. Now, thermal behavior, if we look at, now, if you remember, maybe in 23rd, those who are present, I do not know how many of them are here, but on 23rd September in the session, we discussed about the special type of batteries, where we specifically work on the renewable energy sector, where the large scale energy storage comes into picture called the redox flow batteries. If you remember, the redox flow batteries are there coming up in a big way, where the large scale solar power and the wind power generations can be managed in the power system side to smoothen the voltage frequency fluctuations by proper charging discharging of such large scale batteries. But the problem is they cannot be used for the mobile applications, for the automotive applications. They have to be used for the charging infrastructure or the stationary storage applications, the telecom sectors, say data centers, where we can use these with the renewable energy integrated, or smart grid applications where storage is a stationary part here. But here majorly the scaling up and the long life we are using those cases. So here, if you remember this one, I have discussed for a quick recap for a couple of seconds we can take. If you remember, we discussed about this stack of the battery, which is containing the electrodes and the membrane. And this is the two tanks where we can improve the capacity of energy, means how long it can discharge, by adding more electrolyte. And this is the one which dimension-wise, if you improve, it will give more on the power side, power capacity side. So power capacity and energy capacity can be independently scalable for this redox flow batteries. Reduction oxidation happens in both cases. The anode, the cathode side, while charging, discharging, and vanadium is a solution which is making the electrolyte, which is the most costly part. That's why capital cost is still high. But the moment we are having the number of cycles we are considering, then definitely it is 5 to 6 times higher than the lithium batteries. And also the chance of getting the thermal explosions are less. But remember, in those cases, the thermal management is done by electrolyte flow control. If you remember, on that day we discussed. But how to know about the electrolyte flow control, how to optimize them, for that we have to need prediction of that. If you cannot predict accurately, you cannot optimize accurately. Those are very connected things. Now, for that, we have done some predictive analysis using machine learning models. Why machine learning models again? Because there are more randomness. The actually empirical model, mathematical model cannot always help in handling those anomaly of the data, as well as the nonlinearities in the performance, randomness in the performance. Those cannot always handle. Those exponentially decaying, exponentially rising, different pattern of the discharge may happen. Mathematical modeling based prediction or estimation that cannot always accurately meet those demands. Thereby, we are using the AI techniques or the tools where the data-driven models are more important. See, this is one such schematic we have used for one of our recently published papers in energy storage Elsevier, and with our PhD students and BTech students also there who helped in the algorithm portion with us. You can see here the 6 kilowatt hour community scale flow battery storage we have used in our lab scale, where the flow battery power loss versus state of charge of different cases. So here we have done for the system power loss, because we know that while we're integrating the battery storage with the system, its battery also has internal power loss. If you remember, on that day we discussed about the equivalent circuit model. So in 23rd session, we have taken the equivalent circuit model just to understand the internal impedance, estimate the internal impedance as a matter of fact of the different chemical reactions happening inside the battery and discharging rates. And also for the flow batteries, additional parameters, electrolyte flow rate. So those are impacting the internal impedance of a battery, which is very important for calculating the losses, because the lossy system, if you integrate and the battery power loss cannot be predicted, then we cannot use the control action to control these losses, so that where the less current is important, where soft charging, where fast charging, where the high level of discharging is allowed, or whether the slow discharging is allowed, or whether moderate discharging is allowed for the battery, thinking of the thermal as well as electrical aspects. Now, this is important. You can see again, as a thumb rule, we have used the 80%, 20%, but not necessarily those will be using those. There is always not 80, 20%. Quite a popular method it is as a thumb rule, but it can be 60, 40, 70, 30 also as per your choice. If you see the accuracies are quite significant for different ranges. But it is always recommended that the higher it should be the training data, so that the ML models can be properly trained and they can follow the pattern for the prediction time. Remember, in on-field application, there are multiple randomness which you might not have predicted in advance. So in the training side, there are these gaps, as well as a result, the accuracy level is also less in such cases. Now you can see here the prediction which you have done. This is the data pre-processing, cleaning and imputation. As I said, the feature extraction, feature selection. What are the input features? Like in flow battery, there are flow rate, there is a current, there is the internal resistance. Those mainly impact on the battery power loss. So we have taken those features inside, and we have taken the different multiple algorithms into consideration, like adaptive boost or ADA-boost. Long short-term memory algorithm. This is also an important algorithm where the long short-term memory means every time it matches with the previous memory data, and for the long data, large number of data for the time series, it is preferable. So definitely the battery state of charge is a function of time only. With time, it degrades for the discharge. For the charging, it increases. The state of charge increases with time. So power loss versus state of charge is also again a sort of a time series data, you can say. And then XG-boost, extreme gradient boosting, we have already done earlier. We have seen it for the solar applications. Random forest is again one tree-based, where multiple trees are there, make a forest, and it is basically continuously it is handling the data of the previous data. And then ANN, these all are supervised learnings, you can say. These are not unsupervised learnings. We are typically using for the electrical engineering aspects. There are applications of the unsupervised learning also for those randomness and nonlinearities we can handle in online processes. Again, artificial neural network is also a important model for such kind of applications, where we can see here the results. See here, we can say as per the whenever comes the nonlinearity cases, the handling capacity of the XG-boost is better for those kind of adaptability, internally, imputation and then managing is done by XG-boost, where the actual values are the this one and the scattered values are the predicted values. So if we superimpose to have an idea on the accuracy level, you can see XGBoost gave us the better performance compared to the ANN and other cases. But remember, not necessarily always this battery storage based on the data training data matters a lot. That is the takeaway of the slide, that not always the XGBoost will be best algorithm as per the training perspective. But the same battery we can think of if the data training is has a say, it depends on the data pattern. Always data pattern decides that what is the algorithm suitable to be chosen. That is important. For this case, we got it XGBoost, fortunately, but that may not be ANN also. Like wherever this kind of boosting techniques fails, there comes the deep learning methods where we can take more time to layer by layer prediction. I mean formulation and further prediction, but the deep learning methods are effective for those kind of work where there are the boosting techniques or the regression techniques fails sometimes, but it needs more time to compute. That is important. As I said, this is the table. If you remember, for earlier cases, those were understood by a simple table, but it is somewhat a complex table where battery stack current means battery charging, discharging current, the electrolyte flow rate. Electrolyte flow rate is the second column. If you can minutely see, electrolyte flow rate, say for the 6 kilowatt hour battery, if you remember, we have taken our 6 kilowatt hour battery here, 1 kilowatt 6 hour battery we have taken, where the manufacturer specified algorithms are 40 to 50 ampere, and then the electrolyte flow rate is having 3 to 18 liter per minute. Typically 0 to 20, we have taken 3, 6, 12, and 18 liter per minute as the flow rate electrolyte. And you can see here the performance comparison of the ML algorithm we have done for the loss prediction. So the moment adaptive boost and random forest is there, you can see there, look at their R square, means correlation coefficient, which has to be close to 1, mean absolute error and root mean square error. You can see here in these cases, the R square is closest for the to 1 for the XGBoost. Compared to the next level is somewhat the AdaBoost and random forest also nearby, and LSTM is even poor, as well as the ANN. So these are the somewhat deep learning methods which are having different iterations, but somehow they are not eligible in this case because we are getting more accuracy in the boosting techniques, of course, based on the data pattern, as I said, and also the mean absolute error and root mean square error. And anyway, XGBoost technique will be faster convergence, but not always suitable because of the accuracy might be compromised in some cases where the deep learning methods do better compared to that. We'll also show such cases where deep learning methods are better algorithms, but that's why there is no thumb rule of choice of the ML algorithms. We have to choose. First of all, you have to go for the basic model-based predictions. Then we'll go for the, if that fails, then we'll go for the different models. If provided data is reliable, data is there. Reliable source of data is also important. Any data, open source data is not always reliable. That is important. Now, if you talk about the thermal behavior, the moment we are talking about the power loss is not sufficient because the battery management system, as we remember in the 23rd day's class or the session, we have done the power loss is actually well connected to the temperature rise or the thermal behavior also, because the battery management system includes both the electrical as well as thermal parameters. So for a result, you can see here, the same battery you have taken 1 kilowatt 6 hour or the 6 kilowatt hour, the same battery storage, because the electrochemistry cannot change in the one test. Otherwise, the validation cannot be done properly. So again, data preprocessing and tuning, which you have done here. Similar kind of things we have done here as well. And then machine learning models here we have seen that the temperature rise. Remember, for lithium-ion battery, it is more sensitive. As we discussed last time, it's compact design, lithium-ion battery compared to these flow batteries, but it's a mobile application, very useful for EV applications. So there are more randomness in the charging discharging. But as I said, data availability is important. Because of the data availability is important, the sufficient data point, if you not get, synthetic data generation is also one way in lab scale, but the reliability is less in those cases where, because of the overfitting chances are more, because those are synthetically generated data, not the actual field raw data. There comes the data preprocessing techniques. This is not always used if it is a synthetically generated data, but that algorithm we cannot claim as a robust algorithm, because in reality, in real field, there are only more randomness. That might not work always with better accuracy, which we are claiming here in the lab scale, the synthetic data wise. But that's why the real data is so important. And to generate in the lab also to generate the noise in between the smooth data. Even if it is smoother, we have to use some noises. Otherwise, the real picture of the data will not come out. Now you can see linear regression. Here we have used support vector regression and the extreme gradient boosting techniques. These are the things which I have done for 1 hour work is the energy storage widely recently, and with our students. Where you can see these are the algorithm which we have done. The training and testing over the time with the thermal parameters, means the battery temperature, electrolyte temperature. Basically, if you see electrolyte temperature versus time for different charging discharging rates. As I told you that this is the case where we can see the charging discharging cases. Left side is the charging graph for multiple current ratings. If you remember the same current, 40 to 60 is the manufacturer specified, 60 is maximum current allowable for the battery given, and 40 is a moderate. So we did not go for the slower charging because that is anyway within the limit. Our target is to have wherever there is a higher level of temperature beyond the tolerance limit, there we need to have a proper prediction and timely prediction. Then only we can optimize the thermal management of the battery. That we remembered last time, I hope. So this discharging data is again the same time of charging, same current of charging discharging we have discussed. You see 40 ampere to 60 ampere, same as 40 ampere to 60 ampere in discharging we have done. And we have seen that the temperature rise is also somewhat more in case of the discharging, more than 45 degrees Celsius. And here it is within that. For the C4, C4 is the 60 ampere charging. So as we remember, charging is an endothermic reaction and discharging is exothermic reaction for the batteries. So heat generation is more for discharging, and moreover, discharging depends on the consumer side. So battery charging can be used by a proper charge controller, 3-stage or 2-stage or multi-stage charging to control its temperature within the limit. But for discharging, it is random. So that's why the discharging experiments are more important than the charging experiments for the ML-based predictive analysis. Here you can see here the initial there is exponentially increasing, then it saturates up to some point. So here comes the matter of prediction. And if you see, remember in lithium-ion batteries we had 15 to 35 degrees Celsius is the limitation of the safe operating limit. But for the flow batteries, we can think of that as a 5 to 40 degrees Celsius. But still, for higher or faster discharging, 40 degree also crossed. So we have to bring it down by some means. But for that, we need to understand whether predictability is accurate or not. You can see here we use different methods. Again, the red color is the actual values and scattered points are the predicted values. Linear regression LR for charging and discharging. Support vector regression is for charging discharging. You can see it is better than the linear regression. Quite natural. The green one is the predicted value, which is in and around the red for the support vector machines, support vector regression, and then XGBoost giving better accuracy compared to that. So you can see here, XGBoost has a very important feature of handling those kind of dynamicity as well as the missing value imputation in between and self-adaptability, which can faster convergence, which can lead to with a better accuracy compared to the other regression techniques, as well as sometimes better than the deep learning methods also. So here you can see the green side is the profit line, where you can say the different current we have tested for charging discharging, because 40 to 60, and you have understood that different current levels, the temperature profile you have taken, as you can see in this graph, we have extracted the data points, almost 6,000 data points in each cases, total 24,000 data, which is sufficient for the machine learning model. And we have understood that the accuracy is close to 100% close to that for the XGBoost. Compared to that, SVR is the next one, and linear regression is having poor performance compared to these two. But if you talk about the mean absolute error and the root mean square error, RMSE, of course, you can see it is well below than the SVR. That's why this XGBoost is chosen as the better algorithm for prediction of this kind of cases of thermal operations. As looking onto the storage side, supercapacitor is one more aspect where the batteries are having limitations of the dynamic discharging, dynamic charging. Supercapacitor, if you remember that, or if you must be knowing that for faster charging, discharging, supercapacitor is very useful in those cases, but supercapacitor cannot hold the charge for longer time. So in electric vehicles nowadays, people are also using the fuel cell battery as well as the supercapacitor or ultracapacitor battery hybrid storage. The steady operation battery can handle, but the dynamics means wherever there's an uphill or sudden acceleration, sudden deceleration of the electric vehicle, those cases, the power managed by the supercapacitors. The small time, but with a large power quantity that can handle by supercapacitor. So it has a high power density, battery has a high energy density. Those are the interesting factors of the energy storage which you need to think of while doing this kind of ML algorithms choice. You can see here one such work we have done recently in the energy storage again in our research group, where in 2025 we have done quantum capacitance. That is one more important part, where quantum capacitance is basically the factors where the actual capacity of the supercapacitor can be handled, can be understood, so that the volume of the supercapacitor or the size of the supercapacitor can be estimated, and we can fit into the power pack that this much of load is connected, and to have a management of this kind of transient loads, this much of volume of supercapacitor we should need. That is the idea. For that, we need to have a prediction of quantum capacitance with respect to biasing potential. What we have done, basically, one of our research group here, we have a material simulation. Of course, I'm not a material scientist here, but we have taken the data generated by different doping. Graphite super.
I would like to welcome you all and express my gratitude to our esteemed resource person. Today, in this session, we will explore about power electronics and electrical vehicles. I am confident that the discussion and interactions will be insightful and thought-provoking. Today's first speaker is Dr. Marta Zurek-Mortka. She is recognized scientist in the area of electrical engineering and works in mechatronics and prototyping center in the Yukosovich Research Network Institute for Sustainable Technologies located in Radom, Poland. She obtained a PhD at the Faculty of Transport, Electrical Engineering and Computer Science at the University of Technology and Humanities, Kazimierz Pulaski in Radom in the field of electrical engineering. She has been a lecturer at the Sopot University of Applied Sciences. She is a member of the Polish Association of Electrical Engineers and a member of the expert team of the European Commission and the National Center for Research and Development in Poland. She is also a member of the organizing committees of international conferences, mainly organized in Asia, as well as a keynote speaker from the STEM area. Her scientific interests include, among others, electromobility, renewable energy, power electronic converters for electromobility and renewable energy sources, sustainable technology and development, waste heat conversion, and hydrogen technology. She collaborates on an innovative solution related to modular hydrogen production and storage systems, waste heat conversion, and industrial scenarios of renewable energy based electromobility using AI. She is an author and co-author of over 40 publications indexed in Scopus, Web of Science, IEEE, as well as a co-author of 5 patent applications. She has teaching qualifications and has a function of internships supervisions from Poland and India, and conducts training in the field of electromobility and electrical engineering. So, ma'am, please start your session.
Good evening. I think I'm visible and hear you. Do you hear me? Everything is okay with connection?
Yes, sir, ma'am.
That's good.
You
That's
are
good.
visible and audible also.
So fine. Thank you so much. Thank you for introduction about me, some words about me. That's it. And I would like you. I'm really happy that you invited me to this how to say, training session that I can share my knowledge and about my research that I'm doing in the institute. So thank you so much for that, and thank you for Professor Pradeep Kumar Sathu also for this invitation.
Yes, sir.
Okay, so I will share my screen. Just a minute. All right, I think it's visible. Okay, so let's move to the next. Oh, all right, it's visible. Yes,
Yes, ma'am, it is visible.
that's good. I will switch off my camera because sometimes there are interruptions during connections and maybe my voice can be not heard so clearly. So as you see there, I have been visited in India almost several times, and recently I was this year in March in NIT Jalandhar. And so what I can say, it is a very exciting and interesting experience for me traveling to the India and visiting most places and colleges as well as other institutions like in Delhi, Kolkata, or other city. So thanks our excellent guides, I could visit some places in West Bengal, and of course I would like to come back again when it will be possible in the close future. So let's go to the next slide. Today I will talk you about my research area related to integration of electric vehicle charging station with microgrids. And first, I would like to present my institutions and talk some about the research areas, the centers where I work every day. And then I will go to the topic of integration of fast charging station for electric vehicles with the power system and the troubles, the assumptions, how to do it, and then I present the models hybrid electric vehicle charging stations because it is divided or AC and DC. Looking on the connection on power supply systems. And next, I will present some simulation and experimental tests of charging station with microgrid and tell more about the integration with renewable energy sources and energy storage with DC microgrid because I will consider only this one power supply system. And present at the last, present our projects related to hydrogen technologies and waste heat recovery conversion that we make in our institute, in our department. So first, what is the Lukasiewicz Research Network? It is very, how to say, maybe not very, with a long tradition, but it is the youngest research network in Poland, not in Europe, because we have approximately 7 years. And we have 22 research institutes located in 12 cities in Poland. And the Lukasiewicz Research Network provides attractive, comprehensive, competitive business solutions in fields of automation, chemicals, biomedicine, AICTE, materials, and advanced manufacturing too. With almost 8,000 staff and 22 research institutes, it is a third largest research network in Europe, but young. So we are the part of the scientific community who work to promote business and support the development of Polish companies and also foreign companies. What I can say more, we are concentrating in these 4 main areas: chemistry for industry, energy transformation, circular economy, and defense industry. Of course, the last one, looking at the recent situation on the east border of Poland. You know about this. So my institution for almost around 40 years already has been specializing in building up innovation performance in the areas of machine construction, maintenance, technical and environmental safety. Additional areas of my institute include model solution in the field of technology transfer and continuing vocational education. So here you see this is the view of the main buildings of my institution. It is located rather in exact, not in the center, but close on the east side of Poland in European Union. So we employ approximately 170 persons, approximately 18 researchers, and collaborate with different research centers located in European, and not only, we also cooperate with Mexico, Israel, or Chile, for example. And here are research areas of institute, because we have 5 main centers and the one additional is a scientific publishing department. I work every day in the prototyping center, especially in the control system department. And prototyping center is also divided for other departments such prototype structures, architectures, optomechatronics, and prototype manufacturing. Briefly about the other centers. For example, here is Surface Engineering Center. They focusing on designing dedicated PUD coating material solutions and technologies for the development and specific areas of applications. As you see here, they mostly focus on coatings, materials, solutions, and design of functional materials, the photo coatings or layers. And here are examples of devices that they used for their everyday work. And what is interesting, our department made this devices, especially I mean the control systems. Okay, Tribology Center. They analyze the friction wear, lubrication, and machine parts and tool components with particular focus on research method and devices, as you see here. They focusing mostly on the analysis, friction and wear processes, and surface engineers, imaging, elemental phase, thermometric, and any other related with physical and mechanical analysis. The third one, Bioeconomy and Eco-Innovation Center. They do some research on new methods and research instruments aimed to increase durability through new materials and industrial waste conversion. And for example, our department collaborate with the centers in hydrogen technologies because they focus on the first part of hydrogen production. I mean the waste water treatment for supplied electrolyzer. And the prototyping center, as I said before, divided for 4 different departments, and we focus on to make new devices, increasing durability of technological objects, expanding their service life. And there are some examples of our projects, test apparatus, or other technological devices or lines for industrial uses. Optomechatronics research mostly focus on this part of scientific science, such computer model, hybrid optical imaging methods, 3D imaging methods, and any other related to hyperspectral analysis. And they are here. There are research center devices that use it in their everyday work. And here there are some devices and advanced control system for innovative research technological devices that might make in our department. For example, chemical reactor for microwave hydrothermal synthesis of nanopowders, or plasma nitritic devices with an active screen, as you see here. And Center of Vocational Education, Research and Innovation Management, they mostly focus on the area of work pedagogy, job competence profiles, and others which is related to vocational education, andragogy, and or career counseling. We make some different unique industrial and technological devices, as you see here, for example, helicopter drive elements, device for strengthening the barrels, or system of after impact resistant tests, because we also collaborate with defense industry and also schools. For example, here there are also different types of climatic chambers and technodidactic stands, as you see here. Okay. Let's go to the topic, the main topic of my presentation today, how to integrate the fast charging station of electric vehicles with the power system. So I can say that today there's no real alternative to significant reduction of the harmful effects of traditional transport that is based on used combustion vehicles than the rapid acceleration of use of electric vehicles for the transport of goods or people. And use the renewable energy to power the fast charging station for electric autonomic work machines, for example, transport, means is also particularly important. So electromobility has been developing at fast pace in recent years. As you see here, I also noticed it in India, in Delhi mainly. This applies to both means of collective car transport, motor vehicles, as well as the vehicles for individual use, for me or for you. And I can say that it is a result of attempt to reduce air pollution and carbon dioxide emissions. A large and rapid increase in sales of electric vehicles forecast in the following years. So the functionality of electric vehicles is often assessed by potential buyers in terms of range and speed of refueling compared to vehicles with internal combustion engines. So does the range and speed of charging of modern electric cars or machines make them practical and fully competitive means of transport or work in comparison to this with internal combustion engines? So that is the answer is affirmative, assuming that there is provided a suitable fast charging infrastructure, so that the driving time and charging times are similar to those of an internal combustion vehicle. So here you see, and the reclaimed and next to the picture is the prototype of electric drives used in this type of machines. So this project was made in my institute too. On the right, you see the electric heavy-duty truck with pantograph and under electric rod. So the lack of proper charging infrastructure for electric vehicles is still a problem that makes it difficult to own, enabling on long intercity routes. So currently, focus should be on the construction of electric vehicle charging infrastructure at reloading and parking sites for company vehicles. Why, you can ask? Because there is a solution which until now was not presented in any literature. Nowadays it is from several years. It is related with my PhD thesis. Public car parks at expressways or highways often require large investments outlays to provide a power network adapt to supply high power when charging vehicle batteries, for example, with 300 kilowatts, let's say. And situation is different in industrialized regions, where an extensive industrial power grid provides industrial electric vehicle drives with high powers for daily production. And electromobility is a key factor in the development of sustainability due to its high growth potential which may also positively affect other sectors of economy. And moreover, has positive effect of air quality and reduce smoke in many cities. You know that nowadays the car and light commercial vehicles are responsible respectively for around 12% and 2.5% of total emissions of carbon dioxide. So pursuant to regulation of European Parliament and the Council has an intermediate target of 55% net reduction in greenhouse gas emissions by 2030. It is estimated that by 2050, exhaust emissions will be reduced by over 90% and to drastically reduce the emissions of carbon dioxide to the atmosphere. So this figure shows the extent to which the carbon footprint of electric vehicle will be reduced compared to the internal combustion at the operational stage. For some models of electric vehicles with an annual average mileage of, let's say, 15,000 kilometers, charging with energy from renewable sources reduce carbon emissions by over 3.5 tons. So providing energy from renewable energy sources, the charging of electric vehicle battery significantly reduce carbon dioxide emissions. And fast battery charging system should be integrated with industrial power networks in such a way not to increase the electricity demand of the power system. So this can be achieved using additional renewable energy sources and energy storage. This is a model of smart transformation and energy storage. And here you see the solar plant on the left and on the right, ground electrical switchboard that connects the energy storage and renewable to the power system. So this type of system is just implemented in Polish enterprises and also abroad. So the search for a solution to the problem of electric vehicle batteries charging with electricity obtained without the participation of solid, liquid, gaseous fuels was the subject of my research carried out in my PhD dissertation. A basic assumption here is not to use conventionally obtained electricity. The electric vehicle battery charging energy is to be obtained from renewables, different types. So to meet this assumption, I propose a hybrid electric vehicle fast charging station. In addition to renewable energy generators, the station uses energy storage. And this model. And the work of the station is controlled and monitored by availability tools. And additional important feature is its beneficial effect on the power system through the use DC microgrid and filters, improving the energy quality indicators of the power system. Energy produced and stored in this type of station additionally increase the clean energy resources in the power system, acting as the sources of power for the renewable energy system. And the industry is ready to significantly increase the use of renewables to power drive converters and use them to charge electric vehicle batteries. It is presented solution. The power of battery chargers is a derivative of drive power frequency converters and can reach 2 megawatts in industrial low power voltage networks. Usually, low voltage AC grid is used to charge the batteries of electric vehicles. An example of a network with this is shown in this figure. I analyzed the possibility of using a low voltage DC microgrid as it can be connected directly to the power supply system of intermediate circuits of frequency converter, which are commonly used in industry. It will be further shown that in the solution with the AC microgrid, with the use of transformer separation, high frequency common and differential disturbances are introduced and must be filtered in this type. So then I decided to use this type of grid. Okay, let's go next. Hybrid microgrids. DC voltage provide the possibility of obtaining additional energy. Figure on the right shows a local 600-volt DC microgrid attached to the intermediate circuit of voltage frequency converter. The ability of use this type of converter, I mean drive frequency converter, as a converter for fast battery charging is the main purpose. It can power drive sets in which some of them work as generators. It's present on this figure. It shows a multi-engines power set in which one of the engines is an energy generator. In typical load-sharing drive application in which each voltage frequency converter supplies normally power to a motor via the AC supply line. If one or more motors are driven into regenerative mode, they deliver power to the common DC bus. This power is often used by other voltage frequency converter, and in this way the installation is more economical because in many situations brake resistor can be omitted. In this situation, the DC voltage can be slightly different in each converter. It is due to minor differences in rectifiers, different temperature, output power, and this small difference in DC voltage makes it necessary to use small line reactors in AC main supply and fuses in DC bus. A large number of voltage frequency converters located in various places of the enterprise enables the location of electric vehicle battery charging points as close as possible to places of use. For example, autonomous electric walk machines and various types of electric vehicles. Currently, all drives in which the engine speed is regulated, they use indirect IC-DC-AC converters. And enable to transmission of excess energy from DC microgrid or the supplied energy from AC grid, I use an active front-end inverter. With the structure shown below with LCL filter. The principle of operation of this inverter for the rectifier and recuperative operation mode has been present of single-phase simulation models in which the direction of energy flow is realized by the phase shift angle between the voltage generated by the inverter and the voltage of the power supply network. And the converter is supplied from a voltage source with a sinusoidal voltage with a non-operational operating frequency. And the converter system generates the voltage and difference between these two voltages applies across the both choke, which is used as an energy storage element. A positive voltage across this choke causes the current to increase, while a negative voltage across the choke causes it to decrease. And to achieve sinusoidal main currents in phase with this voltage, the converter system must generate a voltage that shows a small phase shift to mains voltage. And this is common among all active rectification topologies, as you see here. The main disadvantages of this approach are that some of PWM harmonics from this input switching can appear on the power system, and some additional harmonics appear on the output of drive to the motor. So at a given moment in time, when the network voltage is greater than the transformer voltage, the energy from the network flows to the converter while maintaining the power factor, cosinus phi, is equal to 1. Otherwise, the current supplied from the converter flows to the supply network. All right. So LCL filter acts as a limitation of the content high-frequency disturbances produced by active front-end inverter. For example, the differential mode and common mode voltage are suppressed. And these formulas determine the values of the filter parameters. Use these filters enables the power system to be supplied both phase and phase-to-phase sinusoidal voltage. It is necessary to use a filter at the inverter output, this side. Due to invert signal, which contains harmonics at the switching frequency and its multipliers. And the most important reason for selecting this filter is that it can be used at low switching frequencies. Its advantages in the filter dimensions compared to conventional L and LC filters. And also its lower voltage drop and better damping compared to conventional filters. So in order to obtain a three-phase sinusoidal voltage after the PV inverter, solar inverter, without the use of transformer galvanic isolation, I built a model of the local AC network grid in which I applied the inverter differential mode and common mode voltage filtration. I use a half-bridge three-phase inverter controlled by PWM sinusoidal modulation, presented here. In PWM modulation parameters, yes, they are presented here. So, however, to limit the harmonics of the current produced by the output rectifier of the drive converter, I use a resonant LC filter of the fifth, you see, 5th, 7th, and 11th harmonics. In the study of this model, I demonstrated the possibility of supplying a diode rectifier from a drive converter without the use of transformer galvanic isolation. And this figure on the left shows the inverter phase-to-phase voltage, the black one. After filtering out the inverter differential voltage harmonics, it shows that the harmonic component filter of the inverter differential mode voltage approximates to phase-to-phase voltage of the PWM inverter to the sinusoidal waveform. And figure on the right is the result of simulation tests of the filtration efficiency of common voltage harmonics. A harmonic component filter of the inverter common mode voltage also approximates the inverter phase-to-phase voltage to the sinusoidal waveform. Not phase-to-phase, phase voltage. Sorry. And the location filter is shown in the figure on the upper left corner. Here. My additional solution here is to use the possibility of disconnecting this filter when there's no load of the frequency converter. A resonant harmonic filter, the 5th, 7th, and 11th harmonics, is connected to the power supply system on the AC voltage side with a signal of the inverter load current value to reduce the capacitive power consumption from the power supply system. If energy is taken from the storage or renewables via DC microgrid, then the filter is disconnected. And this slide presents simulation tests of the effectiveness of suppression current harmonics by a resonant filter. And the figure showed the phase current and phase voltage distortions of the inverter without the use of harmonic filter, this one, and with attached filter. The spectral analysis of the rectifier phase current waveform shows that without activated filter, the total harmonic distortion of current it is approximately 40%. while after switching on the filter, it decreases to 7. An experimental test of effectiveness suppression of current harmonics by resonant filter in IC microgrid are presented in these figures. There are phase currents, the yellow one, and phase voltage distortion, the turquoise blue one, of the inverted waveout, and the use of harmonic filter and with the harmonic filter turnout. An inverter phase voltage is obtained by applying common mode voltage filtering. A characteristic feature of the use of this type resonant filters is the increase of capacitive power consumption of the capacitors placed in the filter. This results from the influence of the voltage with a 50 Hz network frequency. For this frequency, the power consumptions of the capacitive branch, the filter increases. And widespread occurrence of drive voltage frequency converters prompt me to modify them to the needs of fast and ultra-fast charging stations of electric vehicle batteries. To check the possibility of using components of drive voltage frequency converters to create a DC-AC-DC converter supplying to electric vehicle battery by DC voltage, model of integrated circuit with rectifier unit was built. And feature on the left shows the percentage share of cost in drive system with a voltage frequency converter. And cost of rectifiers is so small. See here. So it is justified to build a battery charging point from low voltage and low cost modules. A mathematical model of PWM inverter of this type of converter, which is connected to a 6-pulse diode rectifier, was built using ANSYS Simplorer, and it is shown in this video. The bipolar PWM voltage inverter is supplied by 600 volt DC microgrid, and its control is shown as stated graphs above the model. The modulating sinusoidal frequency wave of 300 Hz is used for rectifying process to mitigate AC components of rectifier DC output voltage. And new type of converter for fast electric vehicle charging. Battery charging were developed, which uses a voltage inverter of drive frequency converter. And this is a solution that has never been seen in world literature so far, and I presented it the first time. And simulation tests, and this simulation test carried out confirmed the possibility of using the proposed solution to generate direct current to charge battery according to a strategy that consists in maintaining the set values of direct currents during charging, and usually it is Hurley current or tripled Hurley current in the range of from 200 to 80% state of charge battery. When charging battery in this range, the voltage in a single cell increases by 0.2 volts, which results from the data sheets of battery manufacturer. So these figures present the simulation results of that model. Figure on the left shows a near linear dependence of the battery DC voltage value on the modulation factor and the voltage of the converter. The voltage value at the rectifier output is controlled by setting the appropriate value in the modulation factor from 0 to 1. And this figure shows that regardless of the current value, the output voltage of the battery is constant. Only the voltage value is variable depending on the modulation factor, but it is, in this case, it can be treated as a different type of batteries. And obtained results of the simulation test presented model confirm that it is possible to control this voltage and current value of the diode rectifier changing the electric vehicle battery. And confirm the results obtained from the simulation test, I built a laboratory stand in which I use 2 voltage frequency converters. And the first converter powered from the AC grid generates a three-phase voltage with constant parameters, with a frequency of 50 Hz and voltage 500. And this reflects the power supply to the receivers from the solar converter without the use of transformer galvanic isolation. And secondary inverter with a diode output rectifier reflects an AC-DC converter in which the voltage of rectifier is controlled by the value of three-phase voltage produced by inverter of this converter. By using drive converters, a constant battery charging current can be ensured. So the battery charging voltage here is given by the resistance value of the power resistor. And this feature presents a complex laboratory stand for testing cooperation of PWM voltage inverter with the rectifier of electric vehicle fast charging station. And the converter used in the test stand didn't allow the use of frequency in the range of 500 to 1 kHz, as is the case with other types of DC converters, because it was made on another type, the oldest one. So the maximum frequency of 300 Hz was achieved, which is a six-fold increase in the fundamental harmonic frequency of the inverter voltage compared to the industrial grid voltage frequency. And DC-AC-DC converter using a drive voltage frequency with converter with a 6-diode rectifier connected to the PWM inverter was built and is shown in this figure. In the laboratory stand, the possibility of controlling by the voltage of the equivalent resistive load of the rectifier was tested in such a way as to ensure constant current flowing through the substitute power resistor, because we haven't any original battery from electric vehicle. And the rectifier load current was stabilized by the use of software built-in function of limiting the inverter current of drive converter to a given value. It is here is 2 amps and it is a current limit. It's called a current limit in drive frequency converter. And the value of maximum phase current of this inverter with the value of 2 amps have been programmed. And power balance of inverter and the rectifier shows that the maximum rectification current with them will then be approximately 2 amps. So basic harmonic frequency of the inverter phase-to-phase voltage rectified in a 3-phase diode rectifier is approximately 100 Hz. Use of specially shaped characteristic of phase-to-phase voltage waveform as a function of frequency allows to maintain the frequency close to 100 Hz in the full range of 0 volts to 400 volts in PWM inverter phase-to-phase voltage changes. And measured values of the rectified voltage and load current of diode rectifier for the assumed values of the load resistance are presented in the diagrams. And this also with the video, as you see here. The figure below, this, shows the measured maximum voltage of 500 volts DC of the rectifier with a current consumption of 2 amps DC through an equivalent resistor reflecting a 140 cell lithium-ion battery. This test indicates that it is possible to charge a lithium-ion battery pack with a maximum nominal voltage of 500 volts with 2 amps if in DC microgrid is 506 volts. The figure above shows the measured voltage of 300 volts DC at the load current of 2 amps for the equivalent resistance symbolizing the 90-cell battery. These studies indicate that the converter can automatically regulate charging voltage of battery so as to ensure a constant charging current. So this experiment also confirmed the results obtained on the simulation tests. Figure on the left shows the conceptual model of grid-connected solar and energy storage system, and it is well known in literature. So the idea is to convert each non-dispatchable solar unit to dispatchable one with combination of solar and energy storage units to retain the system active and reactive power losses for each load level at the lowest levels. And this combination can produce a daily amount of dispatchable energy, as you see there. And here in 24 hours die cycle, the solar unit is generating energy amount, and this energy amount, you know. A portion of this energy is delivered then to the grid. So the redundant energy of solar units is used to charge the energy storage unit. And rather than curtailing it when the solar output is high during the day. So this stored energy is then discharged to the grid when the solar output is small or zero during the night. And the solar energy storage units are placed in the same location, of course, to avoid grid energy losses during the charge of energy storage unit. Generalizing the total output power balance equation of the main components can be described as power model. So this expression represents the renewables capacity in a time period, for example, in 1 year. And figure on the right shows that the quarterly energy production of rooftop solar plant on a sunny day, taking into account storing energy in the energy storage and delivering it to loads connected to the DC microgrid or to the AC grid, it can be. The actual annual energy production of this power plant is 6 megawatt per hour. What's a fantastic thanks to this small plant? Over the indicated period, it was possible to reduce over that 16 tons of carbon dioxide, you see, impossible, which is also reflected in the range of electric vehicle powered by solar energy in this range. If I would like to have an electric vehicle, the energy produced meets the energy demands for this vehicle. So the expression below shows that the minimum energy should be provided by renewable energy sources during the year for charging electric vehicle batteries, and it should be not less than energy required for charging station. So energy storage is a way to increase network flexibility, and it will also support the implementation of smart grid, as it will allow operators to use electricity when it is needed, not when it is produced. So reducing emissions and reducing dependence on fossil fuels related to greater use of renewable energy, ensuring energy supplies is an economically viable manner. So at the local level, in particular in large urban agglomerations, there are spaces of unused energy, for example, tram or rail power networks. And here, streaming regulations and structural changes in municipal companies can generate investments in electricity storage and thus improve energy security for cities. As you hear there, that is the energy storage it is needed to here to connect it, because so I think that the development of energy storage technologies may in the future also radically change the lives of people living in islands far from the mainland, which for technical reasons often cannot be connected to the grid. And here I present briefly about these models of lithium-ion battery. data used to the simulations, but it is also well known Thevenin models with this type of parameters, as you see here. I'll use it in this microgrid. Okay, and this is a strategy of electric vehicle battery charging. So during the charging, several different strategies can be, or physical implementations have been employed. For example, here, this is a CC, constant current strategy, charging strategy, that provide a constant current to charge the battery to 80% of state of charge. And this an alternative strategy, and it extends the charging time by 50%, but reduce the charging temperature of the battery. So the rest of 100% charging is carried out by attaching nominal battery voltage. For example, 320 volts DC for 100 cell lithium-ion batteries connected in series. And in this range, the charging current disappears. So the battery is considered to be fully charged when the charging current drops from 3% to 5%. So both strategies can be implemented by converter using a drive frequency converter. So in order to integrate the electric vehicle charging station with power system, there should be provided a suitable selection of the topology of local system supplying infrastructure of the station and taking into account its stages of expansion in order to ensure charging electric vehicle batteries with renewable energy, of course. So the annual balance sheet demand for renewable energy may be used here. And topology includes, for example, local DC voltage renewable energy plants, or solar, or wind, and energy storage. It can be a lithium-ion battery. And this type, is often used and is characterized by ability to fast deliver high power energy to the local DC voltage microgrid, and it can be mixed. It can be a hybrid technologies connected with supercapacitors, for example. And the hybrid charging power supply system can be developed in these stages. The first is the adoption of the derived voltage frequency converter to the battery charging function through the use of rectifier unit. The first one. And the second one is construction of solar power plant with annual production capacity with renewable energy for charging batteries. The next one is equipping the charging station power supply system with energy storage. For example, with a capacity, let's say 100 kilowatt per hour for the purpose of supporting the supply of industrial drives during short interruption in energy supply from the industrial power network. If the local grid is able to use all renewable energy sources for the production processes, then in balance terms, it is a natural renewable energy storage for electric vehicles. The fourth one is the use of active front-end recuperative inverter for transmitting renewable energy from DC line to AC voltage side in order to reduce it to the power system. If in the peak load hours there is a need to improve the energy quality indicators of AC line. So the most important is the selection of type and nominal parameters of chargers using drive frequency converters and other necessary power converters depending on the topology of local charging station power supply system. So determining the number of location of points for simultaneous charging of electric vehicles and their power. So then it is important to use the appropriate algorithm software or PLC controller implementing selected strategies of battery charging, including maximizing the use of renewable energy and unloading the power system at peak loads for improving energy quality parameters in the industrial network. So at the end, I can say that the local hybrid electric vehicle battery charging system has significant environmental benefits and supports the power system during peak load hours that I presented. Ensuring renewable energy production, the local industrial plant at the level of electric vehicle demand doesn't increase the demand for system energy, whose transmission costs are significant, in particular while developing distribution lines. So use the microgrid provides the opportunity to integrate a hybrid power supply system for electric vehicle fast charging stations in such a way that the battery charging energy doesn't increase the load on the power system. And in addition, it's possible to improve the power quality indicators in the power system. By attaching a rectifier to the drive voltage frequency converter instead of the inductive motor of any electric motor, it is possible to create a DC-AC-DC converter for charging electric vehicle batteries and use our low voltage drive voltage frequency converters components to create an inverter for fast charging of electric vehicle doesn't require expansion of industrial plant AC grid. When the electric vehicle battery is planned to be charged, instead of a motor load, the battery load is being replaced. And when using low voltage drive frequency converter to create a battery charging converter, the power of electric vehicle battery charging station is derivative of frequency converter power and can reach power to 2 megawatts. Control the modulation factor of PWM inverter in voltage frequency converter enables the implementation of constant current or pulse charging strategies for electric vehicle. So controlling the basic harmonic frequency of the three-phase voltage and inverter above the grid voltage frequency, for example, 10 times, reduce the content of alternating components in the rectifier voltage. So the widespread occurrence of drive frequency converters prompt me to modify them for the needs of fast charging station for electric vehicle batteries. So the results obtained in these projects have also uncovered topics that give me motivation for further research that I'm doing now. So, for example, to analyze the possibility of using other different transport electric vehicles as temporary energy storages, you supporting DC microgrid supply by using bidirectional DC-DC converters for battery charging. I saw the different types of the studies or research in the literature. And the next one, I think that it can be possible to cooperate active filters and resonant parallel passive filters. So, because this may allow the use of lower power active filters if the 5th, 7th, 11th harmonics will significantly be filtered by the passive filters. And then I'd like to create an algorithm for renewable energy management in a hybrid power supply system of DC microgrid, for example, based on measurements of drive voltage frequency converters, currents, supplying motors and converters for electric vehicle fast battery charging, using artificial intelligence or learning machine methods. So I think that it will be possible to develop the AC-DC converters. I mean the drive voltage frequency converter connected with output rectifier for fast battery charging, and using it in real industrial systems. And that could be used alternatively, as you see in this picture, for motor drive or electric vehicle battery charging. So more about my research you can find here. This is the first paper published in 2020, and the second one related to ultra-fast charge and published in Microsystem Technologies. Yes, that's a good one. Okay. Our broader projects is related to hydrogen installation and waste heat recovery system, as I said, only briefly about this. Hydrogen hub, I mean this because the aim of this project is develop a water preparation system of appropriate quality intended to power to the electrolyzer or the hydrogen storage system, and it is presented here. Because the water suitable for electrolysis is commonly called ultra capture, but what is to be understood by this label? Several parameters influence that quality water must have to be suitable for electrolysis. That is very important. It can be any other. So this includes this type of electrolyzer. I mean, we use here membrane electrolyzer. And what's more, we integrate it also with power grid and other components with this hydrogen installation, but here it is mostly important, this part, because we would like to supply the electrolysis process with renewables. So I mean, at the effect, it's a green hydrogen. Of course, it is very difficult. Looking at some different troubles during this part and obstacles, especially in this part of system. And here there is a presented water treatment system for electrolysis supply. And then second one is the waste heat recovery systems. And we want to obtain maximum value of electric current power from the heat flux under the conditions of energy balance in the system and provide high temperature heat energy to the hot side of thermoelectric generator, taking into account the compensation on uneven temperature distribution on the surface of the waste heat source and maintaining the nominal operating temperature of thermoelectric generators. Here is presented here because we would like to develop a multivariant system of waste heat recovery in industrial conditions. And we develop also serious thermoelectric modules that allow the system to adapt to the user existing conditions here. And the figure presents a simple schema and construction and research station, as you see. What is the advantage of these systems? Of course, no moving parts, working in position, long service lives, or maintenance-free operation, and the most important refrigerant is water. So the test also confirmed that the correctness of operation of the system and ability to generate electricity as a result of temperature difference, as you presented here in the heat exchanger, between the cores of thermoelectric generators. And this research station can be used to verify operation of low power systems that use a small number of thermal generators in which the output products is only DC current. And presented solution also enables the conversion of thermal energy from waste heat sources with unstable parameters to thermal energy with utility parameters. And the system can be adopted in different specific conditions in the industry installations. Okay, briefly about it. So thank you very much for your attention. And they present some about my recent research work. If you have any questions, don't hesitate to contact me. Also, I will try to reply for all questions. And thank you very much. I think it is a very hard topic and a lot of information for you, but don't worry, you can contact me at any time. Excuse me, madam, I can't hear you.
Madam, unmute yourself. Swapna madam.
Thank you very much, madam, for your wonderful presentations. in the topic power electronics and EV. So now time for question and answer. If any participant have any questions, please write in the chat box, or you can directly ask the questions.
Of course. If they are, I can try to reply for all questions. If not, you can contact me later or and by the LinkedIn. You can follow my research in ResearchGate too. And nowadays, next week, I'm going to the University of Zagreb in Croatia, and then I will do some research on power supply of hydrogen installation. The first part, how to integrate different unstable renewable sources in a hybrid model to supply the electrolyzer. And this is really important for us because we would like to, how to say, make an installation that it can be used in different conditions, for example, in residual research areas. Yes, please, I hear something. Okay, I understand there is no questions. That means everything was clear or hard.
Any questions from the audience? Madam, please provide your email IDs in the chat box so that if anyone has any questions, they can directly mail you.
Sure. Or maybe I will present. Oh. Okay. Okay. Okay, so you can contact me directly
Share
by
your
the
email ID in the chat
Yes,
box.
it is shared. It's shared, so you can contact me by email and ask. Thank you, Pooja, for your comment. Thank you so much for your attendance.
Thank you, madam. Madam shared her email ID. If you have any question, please note down the email ID.
Yes, I shared.
Our next session will start at 7:30.
Okay, for now, I will just share the feedback link of the first session. Participants, please fill up the feedback and submit as early as possible. Thank you, ma'am.
Thank you so much. Okay, so thank you. Thank you for your invitation. That was a very wonderful to present you my experience and knowledge. So you can contact me directly by email. So this is time for me that I left this site and I leave now this session. So thank you so much again and see you next time, maybe personally in your university.
Okay, thank you, ma'am. Thank you very much.
Goodbye.
Am I audible? Hello? Hello?
Yes, sir. Yes, sir, you are audible.
Please
Yes,
give,
sir. Yes, sir.
Okay, thank you. Please give the rights of sharing the file. For sharing the files.
So our next speaker is Dr. Pradeep Kumar Sadhu from IIT Dhanbad. Sir, you can start your session.
Please give your the permission for sharing this.
Yeah. Okay.
Sharing this material.
Sir, you can now share your.
Yes. Just you will see that. Is it visible on your portal?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. One or two participants will be attentive whenever I shall ask. Yesterday, you have seen the technical hinge. For that reason, every time I am saying that you will please respond. If your answer is correct or not, no problem. You will respond, and that will be helpful for me. And wastage of time will be minimum. So actually, the battery, whatever the last day's heart of the EVs we have discussed. With your permission, I'm taking some sip of coffee, as because that after taking the 2 hours class, I am attending this ATAL FDP. So here that you will remember in the battery wing, this is the basic SOC characteristics, where the is 3-stage battery charge control for lead acid battery, as well as in case of lithium ion, the 3rd stage will not be there, only this much, this 2-stage. That in case of the lithium ion battery, what is the difference between that? The bulk stage is there, then absorption stage is there, but float stage is not there. Am I correct? Do you understand this? Please respond.
Yes, sir.
So in the lithium ion, this is the lithium ion battery, and this lithium ion battery, basically this battery is fitted. Where it is fitted in the car? It is under the bonnet or under the rear boot space or in the elsewhere. Anyone have any idea who have the EV, electric vehicle? Anyone can give this? If it is not known, I shall give you the information. Please respond. Hello? Hello?
No idea, sir.
That is, in case of EVs, the under the bonnet, in normal case, engine is there, IC engine. Not the exactly under the bonnet, lithium ion batteries are not there. Other drives applications are there, or electronic circuitry is there, but the lithium ion batteries are not present under the bonnet, or in the rear boot space is there, luggage compartment, under the luggage compartment also it is not there. What is the reasoning behind? That lithium ion battery is very, very dangerous for the explosion. That if head-on collision is there, due to accident, whatever the passenger's death is there, number of death, or in the rear, some vehicles will collide. So at that time, compared to the strike of the car, the explosion is very high. Like your bomb, time bomb. That whatever the explosion due to this, you have seen that in the Bangalore, Tata Nexon EV has caught fire. In Ola Scooty, that due to the battery management failure. Is it clear? Battery will be, if the cell will be heated much more, there is no control over this, then the battery management system, if the computerized battery management for each cell will fail, so at that time, maybe this cell will explode like your bomb. So you have to take the battery management system, IoT based battery management system. It is condition monitoring also. It is required. Next is the basic lithium ion battery charging. Here the two-stage, and what is the basic difference? One of the difference with charging lithium ion battery is that have a higher voltage per cell. In lead acid battery, how much voltage? Anyone? That I have given the highlighting over this. In lead acid battery, how much voltage per cell?
4 volts. 4 volts.
In lead acid battery. In lead acid battery,
It is 1.2.
It is 2 volt. Basically, in the SOC, I have discussed with SOC. Here you see the yesterday deep discharge chart. What is this? It is cell voltage is this much, is different. Per cell is fully charged 2.12. So full battery voltage is this type. 12 volt battery, 6 cell. So how it is calculated? 2 volt per cell into 6. So 12 into 12.70. That is the voltage of the battery. But the thing is, in case of lithium ion battery has massive change over this voltage. Per cell voltage is higher, double. More or less 3.724 volts. So charge density depends on that. Lithium ion cell also require much tighter voltage tolerance on detecting full charge, and once full charge, they do not allow or require to be trickle or float charged. Is it not? Already we have discussed. Is it highlighted on your portal? Please respond.
Yes, sir. Yes, sir.
So at the time of full charge and the ones fully charged, they do not allow or require the trickle or full float charge like your lead acid battery. That means 500 milliampere or 1 ampere charging is required for lead acid battery, but here it is not required. It is particularly important to be able to detect full charge state accurately because lithium ion batteries do not tolerate overcharging. Here you see in the lead acid battery, basically if sometimes in your inverter, if the overcharging kit will fail, so immediately the battery will not burst or immediately battery will not fail. But in case of the lithium ion battery, if it is overcharged, so the battery will, like a bomb, it will blast. So there is a chance of catch fire. They overheat. This reduces their life, but in extreme circumstances, it can lead to them catching fire. What happened in Bangalore, in Tata Nexon or Ola Scooty, it has been reported in Delhi newspaper, Times of India or that. Have you got this news? Anyone? Have you seen? In the social media also it has been attached. Is it clear? Please respond. show that lithium-ion battery charging precautions are there, overcharging protection. Then another thing, if it is lithium-ion battery fitted, then the atmospheric temperature, it will work in between that 0 degree centigrade to 45 degree centigrade. But in summer in Dhanbad, that 48 to 52 degree centigrade, in Kuwait 55 degree centigrade. So that must be controlled, or Leh Ladakh in the winter minus 40 degree centigrade. It will not work properly. Do you agree? Hello?
Yes, sir.
Yes.
So temperature
Yes, sir.
limit mentioned give the best charging and also extend the battery life as well. This is the main thing. I want to manage the battery life. Basically, if you do not know, as per the word of Swami Vivekananda, if you do not know the main knowledge, so you cannot stand in your own leg. Basically the battery life, it is depends on this criteria. Next is the discharge current. These are the normally battery packs. Actually, you are waiting for the wireless power transfer. There we will go, as because yesterday we have not completed the lithium-ion characteristics. So lithium-ion has over voltage protections are required, which is required in the household inverter also. This is overcharge protection and over voltage protections also there. So these are I shall give you this and slide for your preparation. So 4.30 volts is the maximum. Is it clear? Beyond 4.35, it will blast or battery will damage. So that thing very minutely, that means by means of the artificial intelligence or by means of the condition monitoring, online condition monitoring, you have to manage this voltage, that lithium-ion battery, if it will be charged in the shop, in the radio shop or the battery charging station, normal battery charging station, so battery will be damaged and battery will be, for lifelong it will be damaged. So this portion is there. Reverse polarity protection is required for every batteries. Over discharge, basically below about 2.3 volt dependent upon the manufacturer per cell voltage. If it is below that, so it is showing that like your lead acid battery, it is under the deep discharge condition. So voltage signal will come for this protection. Over temperature protection. So come to this point. These are the very, very important point for the lithium-ion batteries. Now come to the question of how to charge up this battery without any connection. So these are the most wanted mechanism, that these are the car. Is it visible on your portal? That selection of the circuit, is it visible? Single line diagram.
Yes, sir, visible. It is visible.
Yes, sir.
This is the road. Here you see this section is asphalt road. That means which is normal road. Yesterday I have shown the link, and that is the multimedia YouTube video which is uploaded by DST Government of India and the IIT Dhanbad. There this is the road, and over the road car is there. So in between the asphalt and air, I have to send the power to the car. Actually for wire charging, it is easy. That means in the car, like in the petrol cab, if you open the cap and point the socket, directly couple the car to the power supply. So from the grid, power will be transferred. That means by means of contact power transfer. Yesterday for train, the contact coupling, what is the value of K? Yesterday already you have discussed it. Anyone respond? For contact power transfer, what is the coupling coefficient?
0.8 to 0.9.
Contact power
Sorry,
transfer.
one unit.
Thank you for your response. So it is contact power transfer is 1 coupling coefficient, but in this system it is basically 0.3 to 0.4. This coupling coefficient will be achieved. But the one added advantage is there that air is in between that core materials, so the core loss is 0. Do you agree? That this is the primary coil. Here you see this is the primary circuit. Under the road, primary coil is there. It will generate the flux, and that flux will carry through air and some minimum portion through asphalt. So air gap, actually in the transformer protection of saturation of core, you have done the air slot, is it not? Transformer magnetic material, whenever it is not saturated, you have intentionally cut a air section. Here also, the air core will help the not to saturate the core, and core loss is here 0. Is it not? So primary coil will generate the flux, and that flux will couple the pickup coil. So this pickup coil is under the car. So it is primary coil, it is secondary coil. It is coupled with this like the transformer, primary and secondary, it is coupled with this. And here the induced EMF will be generated. And this capacitor bank in the secondary and this capacitor bank, actually this capacitor bank is not capacitor bank. Inside this, there is a which circuit compensation circuit is there. And this compensation, 4 type of compensation is there. Series compensation, series parallel compensation, parallel series compensation, and the parallel compensation. That means this compensation bank circuit in the primary also series compensation, secondary also series compensation. So at that time it is series compensation. If primary is series, secondary is parallel, so at that time series parallel compensation, and primary is parallel and secondary is series. So at that time parallel series compensation, and primary is parallel and secondary is parallel. So parallel compensation. So what is the frequency here? The power source, it is 50 Hz or 60 Hz. Here 2 blocks are there inside this. One is rectifier. It is a DC link inverter, and it is high frequency will be generated for model, laboratory model. We have done this 33 kilohertz, but in the practical cases, it may go up to 450 kilohertz. So this is the primary circuit, and through this capacitor bank, it will operate at resonant condition, actually resonant inverter. This primary coil, and in the capacitor bank, if it is in series, so series compensation, and that will inject the maximum current in the primary LP loop. So that will introduce the flux, generating of flux, and which will cut the LS, and across the LS the induced EMF will be generated. And here also that capacitor bank is there, which will create the resonating condition in the secondary. It may be series, show series compensation. After that, there is a rectifier unit. So this rectifier unit is not so simple rectifier, just like 1N4007. That's like, it is not like, or not your powered diode. It may be the 50 ampere, 60 ampere powered diode is not working. Why it is not working, anyone? Normal diode will not work. Why? Anyone can respond. Do you know? Please respond.
No, sir.
Okay, actually that rectifier, these rectifiers, it is a high frequency rectifier is required. In the primary coil, if 33 kilohertz, in the secondary coil, what is the frequency? Primary coil injection current is 33 kilohertz. Secondary coil?
415.
Why it is less? 33 kilohertz to here it is a transformer. In the transformer, frequency is changing. Any
No, sir.
transformer? So the secondary coil.
It is
Same, 33 kilohertz. So this 33 kilohertz, if you put to the IN4007 or IN4002 or 100 ampere diode, power diode, then also it will be zero. Why? The switching losses. High frequency diodes are required. In the BTech level, what high frequency diode? Do you know this name of the high frequency diode?
Yes, sir.
What is the
Tunnel
name?
diode, vector diode.
Schottky diode, is it not? What is the limit of this frequency of Schottky diode? Schottky diode can operate up to 1 kilohertz maximum, practically. Beyond 1 kilohertz, it will be again zero. So here we have used the S capital I small capital C, SiC. What is SiC? A special type of diode, silicon carbide diode for the high frequency operation. Is it clear? So this SiC, and if it is beyond 450 kilohertz, then SiC will fail. What is the requirement of this? GaN devices, gallium arsenide. So these devices can build for this rectifier. Then regulator is what? Regulator is basically buck boost. After this, here what is the voltage? Is it DC or AC? In this bar? Anyone?
AC, sir, AC.
Huh? Input of the rectifier is AC. Here it is AC. But right side, near the regulator, this bus is DC bus. As because DC is required for battery charging. And here the buck boost regulator is there and DC output for the battery. Up to this, is it clear? So
Yes, sir.
power, yes, power source is 50 Hertz. Then it will be rectified to DC, then high frequency inverter. Basically, high frequency inverter is resonant inverter. Then capacitor bank is required for compensation. Actually, this operation in primary also under resonant condition, in secondary also that resonant condition. So maximum power can be transferred. And then this rectifier, SiC rectifier will rectify, and then regulator will regulate the voltage for the battery charging. So next. So what is the details diagram? I shall show you this. In your circuit, is it visible? This is the details diagram. What is the details diagram? Please respond. Line is working or not?
Yes, sir. It is visible, sir.
So it is from grid. It is from grid. Three-phase power supply is given. It is 50 hertz. Then 380 volt to 440 volt. That is a step-up transformer is there for isolation between this right-hand side load and the grid side. Then what is this? It is basically the rectifier unit. And one block has been shown here, rectifier and inverter. This block, inside this block, this detailed circuit is this one. So next is LC filter. It is non-smooth filter for making it the VSI inverter, voltage source inverter. Next, which one is high frequency inverter? This one. So it is cascaded with the rectifier and the inverter, which is shown in this block. Rectifier and inverter. Is it clear? So inside this box, what is the circuitry? Here it is shown. That means first box is made of this one. Do you agree or not? And actually the 200 ampere current, it is injecting into the air core transformer. And it is basically this transformer is where this transformer single line, it is not core, air core transformer. This one, this is the primary and secondary coupling. This is the your transformer coil, primary coil, this is secondary coil. So here in the diagram, this is your transformer, and the secondary has number of turns 32. N1 turns is 4. So what is the turns ratio? 4:32. That means 1:8. Is it not? Clear? Next is the capacitor bank. We have discussed in the diagram. This is for compensation circuit. Primary compensation. This is secondary compensation. Which box? This box is here, the capacitor bank. So in the secondary, inside this circuitry, in the primary, this circuit is this. So this much part is there. Next is after the power transfer to the secondary, there is a secondary resonant circuit is there, and this is SIC diode rectifier, bridge rectifier. It is showing plain diode, but it is not plain diode. It is SIC or GAN devices are required for transferring this power. Do you agree? So here the frequency is primary frequency in this bus. Now it will be converted across this. Here you get the DC, and this capacitor is used for stabilize this voltage. And VL, actually this RL, whatever it is connected, it is the transfer impedance of the secondary side. What is this thing? With the battery, how it will be transferred impedance. This transferred impedance in high frequency, it will come. It is showing the battery, but it has a RLV circuit, just like your DC motor. RA is there, LA is there, back EMF is there. So here, whenever you charge the battery, so it is nothing but it will work as a RLV circuit. R is there in series, L is there, and V is there. And my question is, in the DC, here the DC bus, how the AL will come? Anyone? What is the frequency of DC?
0 hertz.
0 hertz. So how the AL will come? XL will be 0. 2 pi FL. How can you get the AL effect? Anyone? It is on the DC bus. How the plain voltage source as RA, LA, and V. In case of battery, in case of motor, it is back EMF. So how the AL will come to the scenario? Anyone?
Sir, L is the load resistance.
No. R is the load resistance, but AL is inductor. So inductor or reactance, XL, why it is coming in the DC circuit? Who will give the answer? Very fundamental question.
It is actually maybe the reactive power transfer or reactive power exchange between the AC side and DC side.
No. Actually, the converter output, suppose the 33 kilohertz frequency is here. What is the full wave? After the full wave conversion, what is the frequency here? In full bridge, double the frequency. It is a pulsating DC. It is not pure DC like battery. In the oscilloscope, you will set this output voltage of rectifier. It is nothing but, it is a 66 kilohertz. If the primary has 33, so output will get 66 kilohertz. Am I correct or not? Anyone respond? 50
Yes,
hertz.
sir. Yes, sir. It will be doubled.
Huh? It will be double. So 66 kilohertz. So this 66 kilohertz, this pulsating DC is nothing but it is a periodic wave. If it is a periodic wave, so everything will come. Inductance will come. So the power electronics converter output is not pure DC. Am I correct or not?
Yes, sir.
So that's why it is coming the scenario. Next. So for this thing, actually what is this thing? The development of efficient power converter, wireless power transfer. Actually wireless power transfer, I shall come back again here. This is the main figure. The one is transmitter coil. Is it not? 15 centimeter air gap. This is receiver coil. So whatever the flux will be generated depends on that. This type of flux distribution you will get through ANSYS software, 2-coil WPT system. But this gap, suppose that it is 15 centimeter gap, air gap. Now it is for normal sedan car, it is okay, 15 centimeter. In Tata Nexon 207 mm, that means 20.7 centimeter. But what about the military truck, off the road dumper in collieries? The electric dumpers are there. What is the diameter of the tire? Tire diameter is more than the 2 meter. Military truck, is it ground clearance is same like car? Anyone respond?
No.
No, sir, it is much higher. Much higher. So what is the technology? Physically, if we put this type of technology, which is not feasible for Indian road condition, it is European technology, that in between the transmitter coil and receiver coil, one repeater coil. So what is the mathematical modeling? Here the mathematical modeling is this one. For 3 coil, this is the equivalent circuit. This is the primary circuit. Is it clear? So this coil will transfer the energy to the repeater coil. This is the repeater coil. Then repeater coil will transfer this energy to the vehicle. So like your relay race, in 1600-meter relay race, first group will transfer the baton to second group, then third group, then fourth group. This is your circuit model of 3-coil WPT system or CPT system. So whatever the current injection, due to that I1 current will flow. But in the repeater coil, you will see, is there any source? No source. It is a closed loop. In the secondary, is there any grid source is there present? Anyone? Please respond.
No, sir.
But in the primary circuit, under the road, you have from the grid supply, you have the power, so it will be transferred to there and then. So this mathematical modeling is this one. You will show the impedance matrix. What is the impedance matrix? Here, this is impedance matrix. So first diagonal is the impedance matrix loop, RS, RA, JXA. Here you see R, that is your total loop. So RS is where it is the source resistance. Next JXA. JXA is here. That is LA part is there, JXA. So in that way, similar, that R1 and JX1, here in the secondary RB plus RL plus JXB. So RL plus RB plus JXLB, that means this part, imaginary part, JXB, multiplied by current matrix. Here, what is the current matrix? Here you see that current matrix, first loop current IA1, second loop current I1, IB. So that equal to voltage. So voltage is basically the primary loop has Vs, then all the loop has 0. So here you will see that efficiency will be enhanced for the n number of loop. So whenever n number of loop will come, n number of repeater coil, mathematically okay, but practically there is some constant. So here n number of coil much more efficient. So what is the mathematical modeling? Mathematical modeling for this is the impedance matrix. So RA plus RS plus JXA, and final is RB plus RL plus JXB, and other are R1 plus JX1, R2 plus JX2. So in this diagonal element, you will get, and both the sides, symmetrical side, minus J omega LA1, minus J omega LA1, minus J omega L12, minus J omega L12. In that way, it will be complete. And n number of loop current is this one, and whenever multiply this, here you see only the one loop has Vs and other loop has 0. Is it correct as per the mathematical modeling? Is it clear?
Yes, sir.
So the response, practical response of this curve, whenever you insert the repeater coil, here you see that is the loss portion. This is the not working flux. Here it is not working flux. Only working flux you will get from where? This area to this area. Is it not? But whenever repeater coil is there, this working flux area will enhance. Is it clear? So next is the 2 repeater coil. So much more clear. So 4 by 4 impedance matrix size here. So current matrix 1, IA1, and then the others current, but voltage. Transmitter coil Vs is there, other voltage are 0. Okay. So those are the equivalent circuit. So this is the contactless resonant circuit here. So what is the application for this? We'll see this. The next, efficiency enhancement of WPT system at extended coil width. This is the Indian technology. Earlier, the European technology will fail. Why? Suppose in European road and Indian road are not similar structure. That's why our prime ministers are saying that indigenous technology. So in national highway also you have seen that bumper is there, rumbler is there. So at that time that elongated repeater coil structure will be damaged from the car. Is it not? So ground clearance in this second method, that is the better. And here that is the primary side winding, then secondary side winding, and this is called shielding. That secondary side aluminium sealed, primary side aluminium sealed. Why it is needed? Anyone? Why it is needed? Shielding, why it is needed? Anyone? Do you know this thing? Shielding, why it is required?
Sir, I think to resist the interference, magnetic interference.
Magnetic interference, it is a auxiliary answer is correct, but another thing you will think, shielding in microwave oven. Do you insert your hand at the time of starting the microwave oven? Microwave oven is only operate when the door is closed, like lift, is it not? There is a shielding. That means shielding chamber is there, and you can make experiment that your microwave oven is fully sealed or not. What is the experiment? You switch off the microwave oven. Inside the turntable, you'll put your mobile phone and close the door. After that, from outside, you call the number. If call persists, your shielding is not proper. Am I correct or not? What is shielding? Outside the radiation, outside the flux will not enter. Is it not? Please respond.
Yes, sir.
So
Yes.
here
Yes,
what
sir,
is
perfect.
so what is the need? Basically need is here. Suppose someone is driving the car who have the pacemaker, or passengers are pacemaker. So what happen? You will pick up coil, will pick up the power, but at the same time, the leakage flux will cut the vehicle who are sitting in the car. If the pacemaker is there, pacemaker will be heated up, as because like your induction heating. So that can be controlled by means of shielding. So secondary coil, here we will put the shielding, and under the rod below the coil we will put the shielding, as because if the flux will go to the soil, so it is a wastage of flux. So that thing will remember. And in this case of wireless power transfer, I have shown for that patent certificate, a pacemaker battery recharger for enhancing this service life. How it is possible? In this diagram, basically wireless power transfer for battery charging. So this part will be under the bed of patient, not under the road, in case of pacemaker battery charging. And in place of the vehicle, there is patient body, where the coil is inserted inside the body. That means car periphery is your body shielding, skin. And inside the skin, you have the coil. So over the bed, whenever you take rest for 6 hours or 4 hours, so your pacemaker battery will be charged. Clear? So there this thing is there. Shielding is required. That means under the hospital bed, there is a requirement of shielding, magnetic flux shielding. And inside the body also, after the coil, whenever that coil will pick up the power, after that, it will be protected, that it will not radiate to the pacemaker body, stainless steel body, where it will be heated up. So the shielding is required. Do you understand this?
Yes,
Is
sir.
it clear?
Yes, sir. Yes.
So
Yes, sir.
these things are required, and so this part is over. Next is shielding. Already we have discussed this primary side winding shielding and secondary side shielding. Through air gap only flux will pass. So these are the result whenever the 2.5 centimeter to this variation of diameter. So inductance, mutual inductance will vary, and coupling coefficient also vary. So whenever the diameter will high, here you see that whenever the diameter is 20 centimeter, show that 0.538, and when the diameter is 42.5, here you see point coupling coefficient 0.788. So near to 1, like your power factor. So whenever much more coupling coefficient, much power will be delivered to through wireless power transfer. So these are your flux coupling. So much more is the 45 centimeter coil width I is there. So flux area will be maximum. Next is the coupling coefficient with the coil width. Here you see whenever coil width is increasing in centimeter, so coupling coefficient drastically increasing, and then it will saturate. And if it is 1 meter, then you will see maximum 0.85 or that it will go. Clear? So coupling coefficient, whenever it is nearer to this, so at that time, that is the maximum power can be transferred. And these are the efficiency of the system. So with the coil width, the much more efficient, near the 80% efficient is there in the 45 centimeter of coil diameter. So these are the Now next is impedance matching. That if the power will be transferred from primary to secondary, so what is the maximum power transfer theorem? Anyone can say? What is the condition in between Zi and ZL?
Those should be
They
equal,
must be
sir.
equal.
Equal. So it is physically Zi equal to ZL. It is okay. But the thing is, in case of high frequency converter or high frequency resistance, high frequency impedance, I shall show you that reflected resistance, reflected impedance will come to the primary. So from the load side, whatever the battery, whatever the loads are there, that will come to the primary. Then this will jump to the grid side. So here this block is required for impedance matching. That means this block is ZSI inverter, Z source inverter, and this Z source inverter always match the Zi equal to ZL, and so at that time maximum power can be transferred. Is it clear? Please respond.
Yes, sir.
So Zi is this side and that side is ZL. And another thing I want to mention, it is G to V. G to V means this side is grid. So grid to vehicle, vehicle side power transfer, this side is vehicle. So it is called G to V, capital G, numerical 2 and V. That is the vehicle. And nowadays in our patent application, it is V to G also possible. That means wireless power transfer, we do not complicate it, but for your information, you can note down that from the vehicle to grid, we can transfer the power also. In European country, they have surplus power. So surplus power country has no need. If the vehicle is overcharged, that you will see sometimes lorry, buses are switching on the headlight. What is the meaning? Battery is overcharged, so they are doing the discharge of the battery. It is a wastage of power. But in our case, we can deliver the power from this side to this side. In the same time, in V to G, we can transfer the power from this side to this side. That means through net metering. If I take the power for driving the car from Dhanbad to Kolkata, the 500 rupees, and if I discharge the battery and selling the power to grid for 100 rupees, my net metering will come for 400 rupees. So these are the charges for management. So we do not complex the lecture, as because G to V you will concentrate, and whenever G to V, their power transfer, whenever the power transfer is there, so whole thing will be transferred to the primary. So this thing is very interesting. If you go through this, I shall show you that show in the details diagram of this model how it will be transferred. The mathematical modeling is already over. We have discussed it. Now these are the effect that in case of ZB, that means load side, battery R and RL will come whenever this reflected impedance, that means from the battery side to primary side, it will come, can be calculated in the following manner. Under the resonance and reactance being 0, is it not? That ZB side, battery side or vehicle side, whatever the ZB, RB plus RL, but XL minus XC will be cancelled out as because the inverter will operate at resonant condition. Am I correct? If Z is R plus J XL minus XC, at resonance condition, what is Z equal to? Anyone? Anyone can respond?
Sir, purely resistive, sir.
Purely resistive. So that's why the equation number 6.5 is purely resistive. And here one thing I have to discuss, this reflected resistance or reflected, this part is very important, RFA. Whenever it is high frequency, in case of normal, it is not a problem. But in the reflected, if you put all the values, omega square, LAB square, LAB means the primary and secondary, in between that mutual. What is the mutual square? Divided by RB plus RL into IA, primary current. And so this part, apart from IA, this portion is basically which portion? It is the reflected resistance. Clear? And efficiency will come across this. The eta A, primary circuit efficiency, will come in this 6.7. That is RFA has vital role. That means the reflected resistance has vital role for eta A. And here this vital role for eta B, secondary, has efficiency. What efficiency? RL by RL plus RB. So RL has maximum role. So if this overall efficiency is nothing but, it is that overall efficiency is eta A, eta B. That means primary coil efficiency and secondary coil efficiency. Is it clear? Is there any requirement for further discussion? 6.10 is the final destination. Clear? Anyone is, please respond.
Yes, sir. Yes, sir.
Primary coil efficiency, secondary coil efficiency. In between that,
বাকিগুলো দেখো লিখে পাঠিয়ে দিয়েছি।
হ্যাঁ ঠিক আছে। আচ্ছা আপনি ওখান থেকে সিরিয়াল নাম্বার 29
so 6.10, if it is
29,
111
111 হ্যাঁ ঠিক আছে ঠিক আছে ঠিক আছে।
please mute the other microphone. So the eta A multiplied by eta B, when it is, this equation is valid, it is for 2 coil, is it not? A 2 coil system. But if it is 3 coil system, whatever we have discussed, here you see this 3 coil system. That eta A1, eta 1 repeater coil, it is the vehicle coil efficiency, and this is a multiplication product of eta A1, eta 1, eta B, it is the overall efficiency. Is it not? Clear? 6.16. So here you see, hence the overall efficiency eta E1, this is a 3 coil CPT system, is greater than the overall efficiency of eta E of 2 coil system. So these are the basic equation 6.17. When the repeater coil will increase, so efficiency will increase. So for multi-coil, this part is there. So this is for 5 coil. For n number of coil, these are the efficiency calculation. So 6.20, this equation is for the main equation for the multi-coil system. So these are the one. Another part is there. That is, this technology is not valid for Indian road. So this point is another, the coil width, how it will vary and how it will get the efficiency. What is the mathematical modeling change? The mutual inductance M, that is K coupling coefficient, M by root over L1, L2. So here diameter is changing. Diameter is changing means this is the equivalent circuit without the compensation. This is primary loop, this is secondary loop. Here no multi-loop. So 2 loops are there. And in the 2 loops, here you see the ZR, reflected impedance. Again, this is important for this, and Z, these are the reflected impedance is coming like this, and ZR in the rectangular form, ZR, this part is real, this part is imaginary, so this part is reflected resistance, real term, here it is imaginary term. So reflected reactance, reflected resistance, and reflected impedance is very, very important for the wireless power transfer. Do you understand this? The 2-part, reflected resistance, reflected reactance, it will club together and it will give this reflected impedance, ZR. Please respond.
Yes, sir. Yes, sir.
So these are the things, and here we will go through this only for this separate portion for maximum power transfer. This is the contactless wireless battery charging system for high power WPT application using impedance matching. What I'm telling now, this is important. So this part, basically, how can you detect? This is one part. This is the secondary part in the single line diagram. How it will match? Here you see, this is the load side. How this total block circuit, right hand side, is right hand side S2 switch. Do you agree? And this side, before that, this Z source, whatever the circuitry is there, that block is inside this part, VAC, and with this switching action, this part. Is it clear? Anyone respond? Hello?
Yes, sir.
Show that we have to focus over this part. What is Z source? This cross connection of this, the capacitor, just like your plugging circuit. You interchange this. Sometimes, whenever this thing, you will note down this, that S1 switch and S2 switch operation is alternative. That means whenever S1 is closed, S2 is open. Whenever S2 is closed, S1 is open. Do you agree? Otherwise, both the switches are on. So at that time, the source will be short circuited. Is it clear or not? If both the switches, how mathematically you can write S1 plus S2 equal to 1. So S1 equal to 1 minus S2. So 1 minus S2 operation means what? When S1 plus S2 equal to 1, so either S1 equal to 0 and S2 equal to 1, digital switch, so at that time 1, or S2 equal to 1, S1 equal to 0, that means off. So at that time, that will satisfy the mathematical equation that equal to 1. Is it clear? So
Yes, sir.
Separately we will do this thing for this figure 11A, figure 11B. What is figure 11B? Equivalent circuit during active state. What is called active state? S1 switch is closed. And at that time, as per the directives, S2 is open or close. What is the circuit?
Open, sir.
Open. So this is called active state. In this active state, this inductor will come to this, then this VC22 will come to complete this one circuit. Clear? If you take this, you will just follow the cursor movement. Whenever switch S1 is closed, this current will flow, that capacitor will charge, come back to this negative point, VS. Instantaneous. That is, the plus minus is given in AC. It is instantaneous signal. So next is S1 is closed. So this capacitor also charged, and through this inductor, it will come to the complete the circuit. So it will be charged the capacitor. Next time, 11C, you will see this circuit. So 11C, S1 is now open or on, switch off or switch on? Anyone?
S1 is off and S2 is
Off,
closed,
sir,
sir.
off.
Yes, yes. So this S2 is closed. Whenever S2 is closed, then this total loop will be separated WL11 and IC11. That will be a closed loop. Another closed loop is VL22 and IC22. So it will reflect, and it is the secondary total current will flow through this. So over this, depends on this coupling coefficient. Another thing is the misalignment. Why the misalignment study is required? In front of your car, if the under the road, whatever the coil is there, and over the vehicle coil is there, so in the same axis, maximum power can be transferred, coupling coefficient 0.24. Whenever right hand side 15 centimeter is shifted, or the left hand side 15 centimeter is shifted, so at that time, actually this is required. In front of the vehicle, some cycle is coming, some cattle is coming. So the operate the steering, is it not? And whenever operate the steering, the axis of transmitter coil and secondary that coil axis will be shifted, misaligned. So at that time, your power transfer will be reduced. So these are the technology that has been reported here. Yesterday already I have shown your video. These are the informations are shown in Times of India, which has been developed. The IIT ISM researchers developed dynamic EV charging for prototype. Next, we have you can take this. This is the Economic Times, leading newspapers. So that has been reported. So this, whenever you got the slide, you can get for your more information, you can take this. Next is, if you want to see the Hindi newspaper, you will get this, the Hindi newspaper report. So another reporting is there. So these are the report for this. Now, for your interest, I shall show you some work for different angle. That in this case, it is a new concept for pacemaker battery charging, but you can see this for different work. That is the pacemaker battery charging, who are the working partner in this concept. There is even the doctor is also there for pacemaker battery charging unit, Dr. Prabir Bhaumik. He is the director in Amri. And another fellow from B Pharmaceutical, that is another for the biocompatible materials. They have given the work. Here also the wireless power transfer system, a system for induction heated sterilization, surgical instrument and method for the same. That means you have seen that wireless power transfer also possible. In case of before operation, sterilization is required, but boiling in the water, that will take the much more, it will be dried up with steam. So that much more power has been taken from this. So these are the applications, these novel applications. So here also the name of the inventors and working partners, it is there. It is another application for wireless power transfer for diesel engine. How to that burn the unburned fuel. The blackish smoke is basically from the unburned fuel, and it is that patent has been granted from the 5th July 2022. That is also wireless power transfer. That means in the silencer, inside the silencer, so whatever the carbon particles are there, it is not electrostatic specificator. It will be burned due to high temperature rise. So these are also wireless power transfer. So some work you can think about this, and this is the hybrid particulate matter. That patent is already granted. Here the again wireless power transfer solar induction heating system with high frequency hybrid inverter, not the grid supply has been taken. It is also wireless power transfer. So different applications are there. All the inventors' names are there. I shall share this, all the things. If you want to do this thing, it is not related with wireless power transfer. So Another new thing has to be discussed as because the high frequency is required, one stage conversion. It is a high frequency full bridge series resonant inverter with what is the new thing it is mentioned here, with AC input source. That means inverter input is which type of source? Anyone? Any inverter, household inverter, what is the input source?
AC, sir.
Input. Battery is the input. AC. DC. So it is against the fundamental law. This is the novelty over this work. That high frequency I have shown you in earlier slide, that here you have seen that two-stage conversion. Inside this, there is a rectifier and inverter, but one-stage conversion, AC to AC, high frequency. No need of rectifier and inverter, so that patent has been granted for this. So here it is 25th March 2022. All the patents are applied in different time. It will take minimum 6 to 7 years for granting. So these are the another wireless power transfer system. And here also this part is there. That is, it is also solar induction heating. That is also wireless power transfer. Wireless AC power transfer, not for battery charging. In mobile battery also, lithium ion battery, like your pacemaker, you have seen Chinese make wireless charger is there. In here also high frequency modified half bridge series resonant inverter. But what is the novelty? Novelty with AC input source. So in the patent and journal, what is the difference between two? In the journal, if you do some modification, then it may be publishable, but in case of patent, you have to prove the novelty. So these are the whole work we have done. And for your information, just last night, it has been detected that Elsevier and Stanford University, the Stanford University stopped 2% work under this. It has been accepted for this year, 24. Actually, last year, also for 2023, we have received this certificate for top 2%. Here also the list of scientists that all over the world, that what is the working over this, the name is there. So this is the small presentation. Whenever you get this, you will get these references. All the references I have shown. This whole thesis, whole work is contactless power transfer. He has completed under my guidance. That faculty from Pune Military Engineering College, that college is under UPSC. He has completed this work, frequency converter and transformer for maximizing efficiency in contactless power transfer system. So he has submitted this thesis at 2017. So these are the small presentation for this topic. Now your platform is open for discussion. Thank you. Thank you all. Any question? Yes. So you can send the questions or related to this presentation. I can able to give your answers if you have. Don't make the hesitation that I have tried my best, but if you have any queries, you can ask. You send your coordinator and send the question to the coordinator, or you unmute one by one, you will unmute. If you raise your hand, so from that, coordinator will help you for the unmuting your mic. Thank you.
Sir, my question is, even
Yes.
in foreign countries, is it possible to have multi-layer of coils?
Yes, in the
And if
foreign
possible, then how?
countries, actually like you have seen earlier for antenna, radio antenna, it is collapsible. That means like your folding umbrella, rod is enhanced or rod of the umbrella will be reduced. So 4 rod will come out from the vehicle, and inside the layer you have the coil. But it is in foreign countries, European road condition is different than the Indian road condition. So in the Indian road, if the vehicle one wheel is under the hole, that means the damage of the road portion, if it is there, so it will be damaged, the elongated, that repeater coil management system, or it will strike with the rumbler or the bumper. So these are the condition for indigenous problem. Actually, that's why our Prime Minister is saying everywhere after the corona that indigenous technology is required. Do you understand this?
Yes, sir. But can this thing be automated so that whenever the bumper or some road condition?
But there is a lag in between the time. So in Indian scenario, in the DST project, we have done this thing. Over this, the coil diameter variation in the thesis also shown. I shall show you this. The one from some place. This is efficiency. Over this efficiency enhancement of WPT system and extended coil width. No repeater coil in between that. One coil is in the road, another coil is in the vehicle. If gap is much more, then also it is manageable by means of changing the diameter of the coil. So Q, whenever Q is changing, here you see that Q quality factor will change. This is the option. Here the multi-coil CPT system for multi-coil is different. It is next option is this one. So yes, in this repeater coil here you see that whenever we do that over the diameter, basically the reflected resistance, everything will change over the ZR value, and this ZR or M. What is the M? Whenever diameter is changing, so what is the M? It is a mutual inductance. And what is the formula? Formula for this mutual inductance, this one, that means here, whenever diameter is changing, L value, that inductor value will change. Diameter is much more, so L will be much more. Is it not? That whenever diameter of the coil will increase, so at that time, your M will be increased, as well as here you see omega square M square by Z2 I1. That means reflected part. This part is very, very important. One is frequency square, and it is M square. So depends on that, reflected impedances will be changed. And that's why all the things, power transfer will be changed according to this formula. If ZR will change, so at that time, whole thing will change. And here also another thing, VOC, IOC is there, omega 0. It is on the primary side resonant, and on the secondary side, basically the quality factor Q2 is changing. Whenever L2 is changing, Q2 will change. And in power, whatever the transfer, the power out, you will see that omega I1 square M square by L2 Q2. So Q is maximum, so power transfer will maximum, M will maximum, again power transfer will be maximum. Is it clear?
Yes, sir.
Anything
Yes, sir. Now it's clear, sir. Okay,
I
thank you, sir. Thank you, sir.
Thank you. Welcome. And for your any queries, you can ask this. You have the time, 5-10 minutes time, you can utilize.
Sir, in the chat box, there is another question, how it is possible to take power from V to G?
Okay, it is a bigger, yes, G to V is okay. Whole the thing will be calculated in the opposite manner. Actually, transfer impedance, everything is coming from this circuit, from that side to this side. Is it not? And whenever it is V to G, it is G to V. Whenever V to G, V is here. Is it not? So from here to here, it will transfer. All the circuit will change. We have to know this thing, that in the elaborate circuit, how V to G is possible. In this case, the V is here, and we have to send the power from this side to this side, grid side. So at that time, it will not work as a rectifier. It will work as an inverter, high frequency inverter. And that will send the power through this. That time it will work as a primary coil, and this will work as a secondary. Then after compensation, this high frequency inverter earlier, whatever the working is here, that will work as a rectifier unit. So here you see that anti-parallel diodes are there, that will work as a rectifier, and that rectifier will produce the DC bus, and this diode, three-phase diode, actually this will take the power from the DC bus, but it will not the diode. At that time you have a requirement of thyristors, and that will work as a 50 Hz inverter. So these are the changes, and whenever V to G, it has a requirement of every converter as which type of rectifier to inverter, inverter to rectifier. So converter is required. And what is the governing equation? The governing equation for changing the converter action by function, that in between 0 to 90 degree, it will work as a rectifier, and whenever it will operating triggering angle is 90, beyond 90, that means 90 to 180, that time it will work as an inverter. So same circuit will change over from right side to left side. Is it clear? So transfer impedance will come from grid side to this side. Whatever the flow of this, whatever the transfer impedance will be calculated from the grid side to this vehicle side. Is it clear? That is very easy for saying this thing, but V to G and G to V operation is a very critical operation. Anyone?
Yes, sir. Another question is there. What is the relationship between battery capacity and EV running in kilometer?
Okay. It is a totally battery. Inside this calculation is there that how much ampere hour or kilo ampere hour is there, more or less 15 kVAh. As per the Tata Nexon, it will run 312 kilometers. But there is some question, star point is there, that is the standard test condition. Standard test condition is what? That there is no flow of wind, that in the direction of the vehicle moving, if the wind is flowing, so it is added advantage. If the opposite direction of the wind, the vehicle is moving, so at that time, a less road kilometer will be given. So this type of everything, the variation is there. That depends on the, again, it will depends on the speed of the vehicle. Whenever speed is much more, so at that time, the resistance over this vehicle, that is air resistance, air dragging, that is maximum, and at that time, kilometer will be shortened. Is it clear? And battery calculation will come from the kilo ampere hour, and how much kilo ampere hour? Suppose 15 kilo ampere hour battery is there. There you have to reserve for Indian test condition 50% for the deep discharge. Yesterday we have discussed the deep discharge. So you can utilize the 7.5 kilo ampere hour for discharge. Is it clear? Either this vehicle is running in Europe, temperature, or the vehicle is running in Bangalore, the surrounding temperature is 25 degrees centigrade. So at that time it can discharge up to the, how much? 3/4 to 25%, 1/4 has to be stored in the battery for next time charging or battery health. Yesterday in details we have discussed about the battery. Any question?
Okay. Thank you, sir, for sharing your valuable insights and expertise with us today. Your presentation was truly enlightening and will surely benefit our academic growth. Your practical examples and experiences added immense value to the discussion. And also, we are very thankful that your contribution to our FDP is highly appreciated. Thank you, sir.
Welcome, madam.
So good night, sir, and good night, everybody.
After this, I shall send you the question, 10 questions. Dr. Dharmodas Mondal has said the 10 questions are required. Is there any requirement of question?
Yes, sir.
Okay.
At least 10 questions required. And
Okay,
also, sir, your PPT.
Yes, yes, I am sending.
Okay,
no.
okay.
And already earlier I have sent my cross check and the bank details. Everything I have sent.
Yes, sir.
Accordingly, you will calculate. Okay.
Okay, sir. Okay, thank you, sir.
Okay, immediately I am sharing this PPT.
Yes.
Not in the PPTX mode, it is in
PDF mode.
PDF mode, as because that
yes, sir.
It is a property of IIT ISM Dhanbad. Okay.
Thank you, everybody. Please leave for today, and tomorrow also we will start at 6 p.m.
In your WhatsApp, I am sending. Okay.
Yes, sir. No problem, sir.
Oh,
Okay, sir.
okay. Just a minute. I confirm over telephone that it is there or not.
Capacitors are quite common, but if we want to have a graphene doped with say titanium, for example, that makes a lot of difference in the its property of the quantum capacitance. The charge holding capacity increases if we use this kind of artificial doping of different elements to make a stronger electrode for the or suitable electrode for the supercapacitor storage. But as our research is not in that area, what we did, we have taken their, or also for you, if you have those kind of collaborations, you can take those kind of data and analyze them and finally apply different suitable machine learning models or AI tools where the actual predictability is not possible for the mathematical model always. There are dynamicity and the randomness. You can see here the feature selection we have done for the selection of the most suitable ML algorithm for individual case study of the titanium doping on the graphene, say based on concentration, say 2%, 3%, 5%, 8% of the concentration we have taken, and we understood that what is the best concentration we can think of by using machine learning models, and then finally achieving better quality or greater value of quantum capacitance. That is important. If we can have such kind of greater value of quantum capacitance prediction, then the estimation is beneficial to choose the sizing of the supercapacitor for such kind of EV application or defense application where there is a lightweight storage is required. So you can see the verification of robustness of the ML algorithms, which we have chosen out of multiple algorithms, then take that best algorithm and go for the robustness. Further, one more check over the range of titanium doping concentration on the graphene, so that the electrode is examined under different concentration level of the energy storage towards the better quantum capacitance we can get for which particular combination of the doping concentration. How machine learning helps us in predicting such kind of greater quantum capacitance, yield or the outcome for such combinations of the doping on the graphene, or you can say pure or pristine electrode. You can see here the ANN, ATABoost and XGBoost, as we have used, because these are again with respect to the voltage we applied, and then we measured the quantum capacitance by the formula of the V into Q is energy. So there you can see the energy stored in a quantum in a supercapacitor, how it is a function of the quantum capacitance. If the quantum capacitance increased, stored energy capacity is also increased. So in a smaller size, you can store more energy, electrical energy. That is the idea. You can see here the ANN model gives us better accuracy compared to the other two. As I said, here also XGBoost is here. You can see there are gaps which are the outliers, you can say. And here also it's almost accuracy level is very poor for the adaptive boost. But whereas the ANN is giving us better dense predicted values nearby the actual values. So here comes the deep learning methods. Remember, so far, whatever you have done is mostly time series data. And here you are doing the voltage versus the quantum capacitance, not a time series data. That is somewhat different. That's why here you can see the difference case to case. The algorithm choice is different. Here the ANN is become superior in these cases. You can see here the ANN output. We have seen the doping concentration of the titanium on the graphene body of the electrode of the quantum of the supercapacitor, and quantum capacitance is the parameter which we are predicting actually. And then the different algorithms we have taken where the doping concentration based results we have analyzed, and we understood that in all cases the ANN becomes superior-most algorithm compared to the others in terms of accuracy of prediction. Now, if you see here, compared to this one, say the previous cases, if we talk about, we have done the thermal as well as electrical optimization, electrical prediction. Power loss prediction as well as thermal prediction for the batteries. Now, looking into the optimization part, if we talk about optimization, what happens here? The AI-based performance optimization for the flow batteries. Look at these things. Optimization is again one more part. So far we have done all the ML, machine learning based, but now machine learning ultimately prediction result we are utilizing in optimization. That is important. For the storage, we have taken one case study here. If you think this is one important case study where the optimization has taken place, where you can see the flow battery means there are current voltage pump is important. As if you remember, there are micro pumps to carry the electrolyte flow inside the stack for charge transfer as well as the temperature exchange. So this pump power is important, which takes the power from the cell body. So it's a loss. We have to estimate that. Then internal resistance is also important. Flow battery, VRFB means vanadium redox flow battery. It's again the same battery I'm taking because to justify that, we are not using the lithium batteries here for optimization because we have started with the flow batteries. So we are still comparing with that. And then temperature is the, you can say, battery temperature. So these are the input parameters, input variable you have to choose. Remember, the machine learning needs large data points or data sets, but optimization does not need large data points. It needs the relationship between the different parameters. Interrelationship is very important. As close it would be in terms of the function of the input and the control variables to optimize the output variable, as better will be the optimization within lesser iterations. That is important. As inaccurate will be the equation, then and followed by which is a result of, say, machine learning based prediction. Those prediction inaccuracy will lead to also affecting the optimization results. That's why these input variables are important, where we have to fit to this algorithm. There are multiple algorithms we will talk about. There are a genetic algorithm, there is a particle swarm optimization, there is a nature inspired different optimization techniques. Remember, optimization also, why AI is required in optimization, because in some optimization which we have done earlier cases, say 10 years back, 20 years back, those are offline optimizations. Offline means we are having some set of equations, we are tallying the mean max, or say power minimization, for example, where the mean value comes, that's the corresponding point is optimal point. So in this way we could think of the optimization, but those are the time consuming as well as the limitations of randomness to handle. Such kind of cases we need the automatically finding the randomness is also incorporated in the iterations. Continuous iteration keep on happening in the algorithm, and then finally by following some biological, nature inspired say method, there are different optimization. Daily there are one optimization algorithm is being invented because of the nature inspired. People are now mimicking the nature to understand their system in power systems in renewable energy area. Largely these optimization techniques are being used. The genetic algorithm, genetic recombinations, then particle swarm intelligence. Then there is the ant colony optimization, how the in search of food, the ants make a colony and they make a proper goal setting within less iterations, quickly to search that and to carry that. These are the execution process, biomimicking, and then putting into mathematical modeling. And then we are finally mapping our system. Let's say in this system, these inputs are the battery parameters. Control is the electrolyte flow, because we have to identify. That's the trick of the usage. Even if we know the tools and the coding, we may not be able to use it properly if we do not have a mapping between the input and output parameters. So here, that's why, let's say in this example, the battery parameters are input variable. It's a control variable is flow rate, electrolyte flow rate, which will carry the heat as well as the charging, charge carrier ions in the battery. And there are the boundary conditions. Let's say state of charge, flow rate, as I discussed about the 3 to 18, remember, for this battery, it's a case study. Definitely case study wise, these thresholds will be changing. So 10 to 90% of the SOC, and then voltage also 20 to 32 volts. One more part is also can be added, that is the ambient temperature. We also have done by the time, I am not putting this result, it's under review, one journal. So we have also taken the ambient temperature. You have seen this battery performance largely gets affected by the seasonal variations also, not only the operational conditions. So that means the ambient temperature also matters a lot as a boundary conditions. And finally, we are optimizing the battery power loss as well as thermal management by deciding on the dynamically optimizing the flow rate, because that flow rate, remember, that decides the thermal temperature exchange as well as the charge carrier. So both act as a key factor for the power loss as well as internal resistance loss as well as the thermal behavior drop. So you can see here this picture, if you remember, we have discussed about it, where actually our controller, here is the optimization we are putting, where actually based on the all sensed data and based on the equation which you have built up, here is the equation. See, mean power loss. Target is always have maximum efficiency. That is the mean power loss. Mean power loss, Q optimal. Q is the flow rate, let us say optimal flow rate as a function. I square R is the internal battery stack loss and the pump consumption. As I said, for flow battery, this is the two major components. One is the battery electrode, one is the pump for the flow. But for the non-flow, all lithium ion and sodium ion, all batteries, lead acid, there is no flow factor. So this pump is not required there. So only the I square R loss can be optimized by as a function of the electrolyte flow inside that, because electrolyte is a charge carrier. That's the decision maker of the resistance will vary or not, along with, of course, temperature. So these are the interconnected. Let's say temperature optimization is also, see, Q optimal is here as well, one parameter, Q optimal. So it's a function of Q as well as I, charging current or discharging current. Here we are showing the discharging one because, as we know, the battery discharging is more prone to the temperature rise rather than charging, because charging is an endothermic reaction and discharging is the exothermic reaction. So temperature rise is more prone in the discharging side, and also randomness is more. So prediction is more required in the discharging side rather than charging side. This is the case where, as I told you, that optimal flow rate. You see the red one is the experimental one, means the manufacturer specified points, set points. Let's say when you buy a flow battery, there is a manufacturer specified set points, where these set points are actually this kind of different set points. What we have done is we have control in our simulation, we have modeled that, and data we have extracted, and we understood that the in ideal scenario of the optimization should have like this, should have been like this. If we could use this one, then our efficiency and thermal management could have been much better. But because we do not have these the dynamicity always to operate, then we have to use our entire controller to change. Then nearby parameters we are actually operating in the actual setup, which will give you the nearby optimization goal. So this is the area where the field application and the simulation environment differs. The simulation environment will give you the ideal condition, ideal scenarios, but field implementation will not give you the exactly what we wanted theoretically. So somewhat nearby we have to be happy with. That is the idea of optimization. So now multiple, as I said, the particle swarm optimizations, adaptive PSO, particle swarm optimization, genetic algorithm, and GAPSO hybrid. Sometimes we see that the hybrid methods are more useful compared to the single methods, because the features of both the somebody takes more time with better accuracy in optimizing, somebody takes less accuracy but with a faster convergence. Those things we actually have adopted. You see the adaptive PSO and this GAPS is very close to each other in the number of iterations. As less is the iteration, faster is the convergence. And you can see here the red one is the experimental one, which we actually are getting in the field by applying the optimization techniques. But this is the theoretical one, which we actually thought of. So you can see here the temperature is slightly neck to neck, but within the 40 degrees Celsius is the discharging 100% to 10%. Because we have started from 100% fully charged and restricted up to 10% as a window, safe window, did not deep discharge up to 0%. So we have done it up to 10% or 5% in some cases. So here you can see the red one is the actual one if it's happening, and the simulated optimization techniques gives us better results. Although we cannot achieve that always due to the system constraint and the hardware constraints. Now, the smart grid, last part. I won't take much time. We're almost 6:30. I'll have 5 minutes more to explain this one. This is the last part of the smart grid or a smart microgrid we have set up. And then multiple, if you remember the smart optimal, AI ML needs data. That is the one important part. Field data can be gathered by a couple of interfaces. One such case is smart meters, energy meters. These are important features. You can see load side in a, say, biosolar battery storage based hybrid microgrid we have. So where the load, the power grid or the distribution grid, the biomass, the solar photovoltaics, and the flow batteries. These are the things which we have in our interface to fetch the data. And with this Modbus TCP IP protocol, we are actually communicating with the internal architecture of the communication lines. And through that, a Raspberry Pi based processor is there where we are putting the energy management algorithm. And that is the idea. Now, how to optimize the, you can say, the capacity. So target is that here, the major part we have to use anyway the solar. That's the exhaustible source. At daytime only we get it, at night time we do not get it. So we have to use the solar, and also grid you have to pay for if you use that. So one more part where the capital investment is a concern, there is a biomass and the flow batteries. So again, flow battery I have used for the stationary storage because it is scalable and long life storage compatible to solar life. That's why we did not use lithium batteries here. But of course, because of the popularity as well as the availability, lithium ion batteries are still being used extensively. Upcoming years, we are expecting for large scale storage, this flow battery will be in a big way. So what happens here, the biogas and the battery are the major portion which involves the capital cost. So capital cost means their sizing is important. That's why we have taken the data collection, experimental data from the 10 kilowatt solar. It's a site data, 15 kV of biogas plant. It's a synchronous machine connected engine generator set of biogas. There is a digester of biogas and which can generate the methane, and then that methane is fed to the engine and the generators after purification to generate the electricity, AC electricity. And this 6 kilowatt hour of the flow battery storage, as we are taking the same setup, so it will be easier for us to discuss and correlate with the previous cases. And a building load, let's say one residential load we have taken for a hybrid integrated system. As you have seen, it's a interface I am showing, not the actual picture of the microgrid. Now, data cleaning and tuning is of course required because all the time multiple data, it's even critical because of the data which you have handled till last case, that is a single device, either battery storage or supercapacitor or solar like that. So here is multiple hybrid source. There is the actual challenge which face that data cleaning and pre-processing is very, very crucial. And then feature engineering, feature selection, input of features are very important. Their relationship is very important. ML model choice is also important. Remember, these are the hybrid models, hybrid data. That's why we are using mostly deep learning methods. The variational recurring neural network and the gated neural network, and also the long short-term memory analysis we are doing. These models as a both comes under the, three of them comes under the deep learning methods. Why you have chosen this one? Because there the regression methods actually failed we have studied, and we understood that these are the methods which will help us in hybrid data features. To handle them, we need the deep learning layer by layer analysis. And of course, the more layer will add the more accuracy, but at the cost of time. More iterations will be required. So computational time will be increased. We have to optimize there. That's the optimization where you should stop. That is the idea. Now, this is the result which we have found out. That is the reserve capacity. As we told that the battery and the biogas are the reserve capacity. Biogas means methane is generated. That's the reserve capacity whenever required. When solar is not available or less available and the load is more, then we can use biogas. And if also the solar is charging the battery also in the daytime with the surplus generation, that time the battery is discharging to the load. That is the idea to meet the load demand. And if that is also not available, then we are taking the help of the grid availability because you have to pay for it based on its tariff scenario. Now, understanding all those parameters inside, you can see here a third of, say, October 24, it's a data where you have taken, and then at 9 a.m., 12 noon, 15 means 3 p.m., 6 p.m., and 21 means 9 p.m. again, midnight. And again, this is the next day morning. So it's a whole day of say one day at 9 p.m. to 9 a.m. to next day 9, you can say, or 6 a.m., 9 a.m. to next day 6 a.m. We have taken a 24 hours of data as input to the system. Total for solar, for the biomass, for the battery storage, for the load, for the grid. We have taken all the data. Then we understood that how to actually estimate the reserve capacity. So we have predicted the solar, we have predicted the weather parameters using different models, machine learning models. We have used the biomass prediction calculated based on the capacity and the amount of waste generated in the biomass plant. And then the reserve capacity, we have predicted finally the battery power plus the biomass power, which is acting as a reserve capacity. Whenever the load demand is required, that time the reserve capacity can be utilized if the solar is not available. That is the idea. So this ML-based prediction actually helps in further optimization of the scheduling of when battery storage to be kept in the picture because of this battery power is already predicted, available power, and then biogas available energy is predicted, then solar availability energy is predicted. Those are the predicted parameters which will help us to decide further in the algorithm. Here, in this case, we have to code this one and embed so that decision can be taken of the scheduling of this kind of biogas or solar or battery or solar battery both, biogas battery both, or grid, or all of them together to meet the load demand. That is the idea. Ultimately, goal is to meet the dynamic load demand using this multiple coordination among the sources and the storage. With the help of ML-based predictive analysis, then decide according to that. There comes the optimization, which optimally can utilize the energy so that the losses are less and efficiency is more, and also economic aspects. These are the couple of results for the correlation coefficient, close to 1. You can see most of them are, but the gated recurring neural network is giving us a better result compared to the other two, LSTM and VRNN. But remember, again, this also have important. If you give more iterations, the scenario may be changed. That's why I'm telling that area specific and the data pattern matters a lot in choice of the machine learning algorithm. But the goal is wherever there's a mathematical model has limitations of handling those nonlinearities, there comes the data-driven models and becomes reliable in those cases. So challenges which we face in some cases in a nutshell, if we talk about towards the end. Now, you can see data concerns. Again, as I told, data is the most important part, which is a challenge of the ML algorithms. Security concern and the other concern comes the cost of the data collection tools and different interfacing processes might cost computational burden. And then different renewable energy cases, regularity, regulations are there, policies where always data collection may not be allowed. That's one more challenge. And then you can see uncertainty, which is of course important. Uncertainty in demand, uncertainty in storage life, uncertainty in the influence of the renewable energy onto the existing grid. There are multiple cases might occur, and complexity of the interconnected systems, as I told you. Clustering is important. Those are the challenges in the other peripheral cases. But majorly this data concern and the security concern. That's why cyber security is one more big area in this renewable energy and electrical and power system area, where the cyber security is a big factor to protect the data which you are getting fetched in real time. Otherwise, the data deep analysis during that time, the security concern, if we do not care about, that is a big issue in case of, because data is more precious than money nowadays. We have to secure it. And then the future aspects which we can think of as a researcher, that is the data availability. We can put sufficient data for the renewable energy system, but synthetically also you can generate the data which has less reliability in the prediction results, because we have to then artificially use different noises to make it more realistic. That is the one more way which we can manage. And then explainability and interoperability. It is important. ML models need explainability because the training has to be much more data driven, and then interoperability for better decision and understanding is important. How their hybrid models can come in the picture, not only single stage models. So domain-based knowledge. Domain knowledge is important because the computer science people, they can be better coder, better algorithm developer, but the system understanding is important, because machine learning in renewable energy can be understood if the need for the renewable energy and the storage integration, the goals in the electrical engineering aspect is not known, then that does not make any sense. So we have to have a proper knowledge of the domain specific, the need specific, application specific renewable energy based areas, followed by the tools to be used under different data scenarios. We can make a comprehensive collaborative research in that. So new technologies, of course, novel combinations, as I said, though that hybrid methods are also better sometimes by single optimization techniques. So then pre-processing and cleaning, that's also important. Online and data pre-processing are important, where we can talk about the anomaly detection and the data, raw data, cleaning, as well as the missing value imputation, impute the false values somewhere to have a missing data interpretation so that the outliers can be avoided in some cases. But those are, of course, judiciously to be done. We cannot just do wherever, say, solar power is being generated, but suddenly if there is a long gap, we have to investigate whether that is due to cloud or due to soiling loss, or due to the other cases where the data logger is also not functional. We have to understand those kind of unpredictable scenarios. Then only the missing value imputation can be decided. So data feature engineering is a big challenging part. These are the things which we thought of in a nutshell to discuss. So in a last point, I must say that the machine learning models are not unique. We have to understand the data pattern and profile-based choice of machine learning models. There are some rules and the tutorials. For that, choice of machine learning models can be also anticipated, but not always true. We have to understand that the data sufficiency is a matter, and as well as the data pre-processing and tuned data is also required for training and beta testing to have a new environmental conditions for the same system. We can have a better prediction and followed by optimization. That's the idea. Thank you so much. I think we are already late a couple of minutes. Yeah. So if you have any query later on, definitely in this email I am sharing, you can send me emails or further research opportunities or collaboration which you have, or any ideas or any queries to share with me, you can discuss definitely. Thank you so much. I would be happy to have a couple of questions if time permits. Thank you so much.
Okay, participants, do you have any query? Okay. So thank you, sir, for sharing your invaluable insights and expertise with us today. Your presentation is truly helpful, and we appreciate the time and effort you took to prepare and deliver such an engaging session. We are grateful for your participation in our ATAL FDP as a resource person. Thank you once again for your valuable time and expertise. If you do not have any problem, so sir, please stay in our valedictory session with us.
Okay, madam. Thank you so much for the time and then such a beautiful hosting. I'll be happy to be here for a while to have this session. Yeah.
Okay, thank you, sir. Okay. So respected Dr. Bhattacharya, our HOD sir, and my dear participants, as we gather here for the valedictory session of this enriching ATAL FDP program, I am filled with a deep sense of gratitude, pride, and fulfillment. Over the past 6 days, we have collectively embarked on a journey of knowledge, curiosity, and collaboration. And today, as we reach the destination of that journey, it is both a time for reflection and celebration. This FDP was not just a schedule of lectures, it was a meeting of ideas, innovations, and intellectual exchange. Each session brought with it a unique perspective, adding value not just to our understanding of the subject, but also to our capacity as educators, mentors, and lifelong learners. I am truly grateful to AICTE and the ATAL Academy for their unwavering commitment to faculty empowerment and for entrusting us with this opportunity to host a program of such academic significance. To our invited experts and speakers, thank you for taking time out of your busy schedules to be with us. Your insights, grounded in both theory and practice, have not only educated but inspired every participant. The engagement and enthusiasm you brought to your sessions are deeply appreciated. To our participants, I offer my heartful congratulations. Your energy, punctuality, interaction, and thirst for knowledge made this program vibrant and truly meaningful. Behind the scene, no program is possible without a strong support system. I extend my sincere thanks to our management and HOD sir, co-coordinator ma'am, technical team, and also administrative staff. Let this FDP help us learn more, try new ideas, and work together. Let's not only teach what we know, but also help others find new things to learn. Once again, thank you all for making this FDP a memorable success. Wishing you continued success, good health, and inspiring journeys ahead. Happy Durga Puja. Thank you.
Thank you, madam. Now, we would like to hear from the participant. I would like to request Professor Parthasarathi Pal from our institute to share his views.
I am audible. Am I audible?
Yes, sir.
Okay. Thank you, madam. And firstly, I thank AICTE to giving me the opportunity to attend the ATAL FDP. And it is my, I also extend my gratitude toward all experts. And without them, the no FDP really cannot be successful. And here we have got a lot of knowledgeable person who are very much familiar with this theme of the FDP, and they provided lot of insights and of their latest research. And the session or the schedule has covered like this way. They covered the wide range of topics, including the EV, battery storage, battery charging, wire and wireless way, and the control strategy, as well as the implementation of use of AI/ML for better accuracy and the microgrid. And we have also seen a lot of practical implementation from the various industry as well as the academician. And I believe that all the participants have gained a valuable knowledge in this emerging field. And we also know that in our BTech curriculum, the AICTE also included this topic. So I think all of us, we can transfer this knowledge to our students, as well as we may start our research in this field. And I once again, I sincerely thank the AICTE. It is my special thanks to coordinator madam, Professor Shampa and coordinator madam, Professor Swapna Roy, for their continuous dedication from morning to night to make this FDP fruitful to us. So once again, thank you all and happy Durga Puja.
Thank you, sir.
Thank you, sir. And happy Durga Puja also.
Presently, 88 participants are there.
Happy Durga Puja, sir.
Please, anyone interested to share his views, his or her views. Okay. Anuradha madam, please share your views.
Good evening, everyone. Am I audible?
Yes.
Okay. So first of all, good afternoon, good evening, everyone. I must say that I belong to Netaji Subhash Engineering College family, and I'm truly grateful to have this wonderful opportunity to attend this ATAL FDP, because this FDP has been a truly enriching experience for me. Although I am not from the electrical engineering background, so that is why I found that all the sessions were very much insightful for me, very much new, very much fresh concept for me. And all the resource persons were excellent, and the coordination was extremely seamless. So I have gained valuable knowledge and perspectives that will surely help me in my research background, in my field of study, so that I can get some idea to integrate my knowledge with this new emerging areas. So that is why I just want to say my sincere thanks to AICTE ATAL Academy and the organizing team and my management and the HOD sir of Electrical Engineering Department, the coordinator ma'am, the co-coordinator ma'am, and everyone for this wonderful opportunity. So thank you and happy Durga Puja to everyone.
Thank you. Thank you, madam. Now I would like to request Professor Dharmodas Mondol from Techno India. Please share your views, sir.
Can you hear my voice?
Yes, you are audible properly.
Yes. Good evening to all of you. I am honored to share my thoughts on the concluding day of ATAL FDP as a participant. This program has been a truly enriching experience for me.
Can I interrupt you, sir? Please switch on your camera.
I'm a little bit outside, so very difficult to switch on.
Then it's okay.
So providing valuable insights, practical knowledge, and networking opportunities. I would like to express my heartfelt gratitude to the organizers, resource person, and the AICTE ATAL Academy for their chance to give to organize these events and their tireless efforts and expertise. These sessions were engaging, informative, and thought-provoking this FDP. I am taking back many valuable ideas, perspective, and experiences that will surely enhance my teaching, research, and leadership skill. Happy Durga Puja to all of you. Thank you.
Thank you. Thank you so much. Now, Dr. Bilash Samaro Bugade. Sir, please. Dr. Bilash. Just a minute, sir. You are muted. Sir, you are muted, sir.
Good,
Just a minute.
Good
Yeah,
evening to all
now
of you.
it's okay. Okay.
Is that I'm audible?
Good evening.
Yeah.
Yes.
Yeah, I'm Dr. Vilas Bogde from Maharashtra, Pune. I wholehearted thank you to all the organizers because the topic was very nice, e-mobility and what we need is an electrical vehicle. I want to mention here that I was happy to listen that wireless charging from the IIT professor, and he has shown one kind of thing is the directly laboratory testing one demo he has shown. That was remarkable. So what we need to bridge the gap between technology and practical approach. So that was covered in this particularly FDP. And from the day first to inauguration function to the valedictory section. So all are nicely arranged. Even so the chat of this Banerjee sir's session was very nice, where AIML is included in the electrical engineering. So that was in today's need, because electrical engineering we used to say it's a wired network, and we have to switch towards the wireless network because that was the upcoming generation's need, and they want to that wireless technology most probably. So again, I thanks to all the organizers and the resource persons, those who are given the insights of this particularly e-mobility and the electrical vehicle technologies. Thank you for the opportunity, and happy Durga Puja to all of you.
Thank you,
Thank you, sir. Now I would like to request Nikki Ved. Nikki Ved. Hello. Okay.
Yeah, good evening, ma'am. Good
Good
evening, ma'am.
evening.
I am from GS Raisoni College, Jalgaon, Maharashtra. I would really say that all of the resource person were very nicely explained each and every topic. Obviously, this was a new topic for me to learn because I am a communication professor and I even teach French. But for me, this topic was completely new. But I really enjoyed every single session from the resource person, and I was really understanding each and every part because it was explained very nicely. That was what I wanted to say. And from the starting day to the validity, everything was well organized, ma'am. And I'm really appreciating. Thank you so much for the 6 days FDP program. Thank you, ma'am. And happy Durga Puja.
Thank you. Same to you. Now, Dr. Shubhendu Guhonyugi. Please, sir.
Yeah, am I audible?
Yes, sir.
Yeah. Thank you, ma'am. So I am Dr. Shubhendu Guhaniki, Professor and Head of the Department MCA in Technoman Salt Lake. So it is my pleasure to stand before you to say few words on the valedictory program, which actually give me an immense sense of satisfaction, because a good combination of industry and academia with distinguished research persons actually which Netaji Subhash Engineering College has organized such wonderful FDP, where we have learned also the implementation of AI, also the emerging field of this electrical vehicles, and it is a combination of theory and practices which gives us a lot of new research, innovation, and ideas. A true sense of industry oriented and research oriented such FDP is really helpful for us, so that the takeaway of this workshop, FDP program, is basically helpful to enhance our teaching and research skill. So my heartful gratitude to Netaji Subhash Engineering College, AICTE, and ATAL. Thank you very much. Thank you all, and happy Durga Puja to all of you.
Thank you, sir. Same to you, sir. From the resource person side, I would like to request Professor Ankur Bhattacharya, sir.
Yes, first of all, Madam, thank you so much for organizing such a beautiful event. And I must say that from West Bengal, you have been able to gather people across the country. It seems from the participants range, as well as speakers from outside India as well. I was going through the list of speakers. We are very happy to share a bit of our knowledge to the people who are interested, especially in Saturday's evening and in the eve of Durga Puja of Mahapancham. We are here at almost 90 participants here. It's very remarkable to see the enthusiasm. Also, it motivates us as a speaker to give such more interactive sessions to discuss with people. And also I'll be happy to interact in future as well with some of the interested participants here present. And I must thank Dr. Shampa and Dr. Swapna Roy for organizing such a beautiful comprehensive event, emerging technologies involving as well as the professors and then the industry people to have a blend which is the need of the hour, the academia industry blending in such kind of workshops or the FDP under the sponsorship of the AICTE. So which is really a remarkable effort, and the fruit has come out with such kind of participation, which I must say. Thank you so much for inviting me and keeping me with you in this event. Thank you so much. Yeah.
Thank you, sir.
Thank you, sir.
Thank you so much. Is there anyone else from the participant side who wants to say a few words? Then I would like to request our HOD sir, Dr. Tridivesh sir, Tridivesh Nag sir, to say a few words.
Okay, thank you, Swapna ma'am. Is my voice audible?
Yes, yes.
Okay, so good evening, everyone. Like every good thing comes to an end, this FDP is also coming to an end today. So over the past 6 days, this FDP has provided an excellent platform for academic exchange and meaningful deliberation of some of the most significant advancement in electric mobility, microgrids, energy management, and sustainable technologies. The active participation of faculty members from across the country has enriched the discussions and enhanced the overall success of this program. So I thank all the participants for joining. At this juncture, I take the opportunity to extend my sincere appreciation to AICTE and ATAL Academy for the support in capacity building through such initiatives. I also extend my heartfelt gratitude to all the eminent resource persons who shared their experience and insights with such clarity and depth. A special word of congratulations to Professor Shampa. Ma'am, first of all, both of you are looking fantastic today. Okay, Professor Shampa, the coordinator, and
Thank you,
Professor
sir.
Swapna Roy, the co-coordinator of this FDP, for the meticulous planning and seamless execution that have ensured the resounding success of this program. I know that how much pain both of them has taken to organize. First of all, it is a festive time, arranging the resource person, then the main thing is arranging so many participants is really hard. So it is not offline. Otherwise, I would request everyone to give a big round of applause for both of you. Anyways, it is a great achievement done, ma'am. Thank you so much for this. And the commitment and dedication of the entire organizing team deserve equal recognition. So thank you all for your valuable presence and contribution. I wish you continued success in your academic and professional endeavors. I hope that we will meet again whenever we organize FDPs like this. Our department organizes, our college organizes. I hope that you will be part of that, and we actually would like to meet you offline. So if there is offline FDP organized by Department of Electrical Engineering, Netaji Subhash Engineering College, be part of that, because the thing that is missed, I know that there was fantastic lectures, the resource person are really fantastic, and the sessions were good, but what was missed is good food was missed, right? So that is due on us. So if there is offline FDP, please join us, and wish you all a very happy Durga Puja and Navratri. Thank you so much.
Thank you, sir, and
Thank you,
happy
sir.
Durga Puja also.
Good evening to all. As we reach the conclusion of this FDP, I am pleased to offer a few reflections and words of thanks. This is no doubt an enriching faculty development program. Over the first few days from 22nd September, we have explored the transformative potential of electric mobility and microgrid in creating a greener, smarter, more sustainable future. For advanced battery technologies and EV integration to smart grid management and renewable energy synergy, each session has broadened our outstanding and sparked meaningful dialogue. I extend my heartfelt gratitude to our esteemed speaker and resource person, Dr. Shivanishan Balakrishnan, sir, Mr. Shomnath Sirkar, sir, Dr. Ankur Bhattacharya, sir, Mr. Rajiv Das, sir, Dr. Shumon De, sir, Dr. Ritesh Kumar Keshi, sir, Madam Dr. Martha Surek Morkha, Dr. Pradeep Kumar Sadhu, sir. I would like to thank our principal, sir, Dr. Amol Kumar Ghosh, our dean, sir, Dr. Sukumar Roy, our HOD, sir, Dr. Tridivesh Nag, sir, for their wholehearted support. A special thanks to our participants for your active involvement, insightful questions, and enthusiasm to take this knowledge forward into your teaching and research. As we move ahead, let us strive to implement this learning for our institution and inspire the next generation of engineers to innovate for